introduction. And now this is a very mixed attendance here. So some of you may have some experience with quantum Monte Carlo. Some of you have absolutely none. So I mean, I believe I should make some introduction so that we all are aligned. This will be very hand-waving. I will not give you any details, but I will try to walk you through different aspects of correlation and accuracy issue, efficiency issues, etc., so that then the next speakers who will come, Claudia and Anthony, will actually be able to give you all the necessary details, which I will not bother actually to tell you. Okay, it works. Right. So, okay, so this is the motivation talk which I would like to share with you. So maybe the first thing, I compiled few references here. There are 2 books there which you may like and may actually want to read. The one is more general by Richard Martin, Lucia Reining, and David Sepperli. The other one is by Sandro Sorella, who is actually part of our TREX project. Then there is there are few references there which are very subjective. Those are the ones I actually read and like. The first one is a classic introduction into the methods. It's a little bit old now. We have a pointer. Okay. Okay, never mind. So, so this one is old, but still very good. Okay, these other ones are somewhat newer, so they contain also more recent material. So that's what I would like to do. So I will introduce the electronic structure problem, the possible methods, how to actually tackle the solution. I will tell you a little bit about, like I said, accuracy issues, correlation accuracy issues, and efficiency, how we can actually solve the problem. Okay, so this is what we want to solve is the zero temperature Schrödinger equation for molecular or solid state system, and we want to solve it exactly and possibly cheaply. So we have the Schrödinger equation, kinetic energy of the electrons, electron-ion energy, and the electron-electron energy. And as we all know, the electron-electron term is actually the one which is difficult to treat. And one complication, and this is the major complication here, is that we deal with fermions, and that means the wave function is antisymmetric. That means if you exchange 2 electrons, including their spins, the wave function changes the sign. And I will come to that point that that's the reason why the solution of that problem is really hard. Okay, so this is the selection of methods how to actually solve the finite temperature Schrödinger equation. We have density functional theory, post-Hartree-Fock methods, and quantum Monte Carlo methods. Essentially, that's what we have. By far, the most popular methods is the group number 1, the density functional methods. They are based on the density. So the density of electrons is the principal quantity on which all the theory is based. This is a little bit, I mean, if you have bothered actually to look at the electron density, this is actually a very featureless quantity. So it's actually strange that you base all your calculations on a quantity which is rather featureless and not very sensitive. But anyway, I mean, at least in some occasions, it works pretty well. So you basically transform the many-body problem to a single problem. The electron then moves in some sort of mean field generated by all the other electrons. And you can solve pretty large systems with that, but that also has its limits. Everybody who has tried to use these density functional techniques will actually find that they also, many of them lose brass at around somewhere in the region of 200, 300 coarse. And the scaling is essentially n cubed. Okay, that's because you need to keep the orbitals orthonormal. That brings that n cubed term there. Then we have all kind of post-Hartree-Fock methods such as MCSCF, coupled cluster CI. That's a wave function based group of methods. So you have the wave function which really is behind this approach. Essentially, you do expansion in many determinants. That's very nice and very accurate for systems where you can afford doing that, but depending on how and for which system, etc., you do that, it may scale actually exponentially, which is a pathetic scaling, which prevents you from using this method. Then this third group actually represents a complete change of the paradigm. This is still a wave function based method, but you are not really trying to get the best accurate wave function you can imagine to construct, but you rather try to somehow sample it. You walk through you sample the space of the wave function, and from doing billions of measurements on that wave function, you can actually get the properties or the energies, for example, and some properties of the system under consideration. And the good thing here is that it actually scales not very much different from the density functional techniques in the large system size, but actually there is another problem there that brings the cost, which may be actually quite substantial, and we will come to that later in this talk and in all the other ones. So I said there are several issues. One is that the system may show strong correlation, in which case it may be important which choice you made out of these three groups, which I outlined on the previous slide. And there are some examples here. For example, local Coulomb repulsion. Okay, I will show a MOT insulator, MOT transition, metal insulator transition. That's a manifestation of a strong correlation of that part, or for a chemist, typically molecular dissociation limit is where the correlation actually manifests itself. And then there may be systems with charge and spin fluctuations such as MOT phases, magnetic phases, etc. I actually had here, I forgot to show it. Sorry. Here, that's an error. This is nitrogen atom, N2 molecule. This is a crystal, a molecular crystal, atomic crystal. So you actually see the correlations, the corrections there, and they are quite sizable. And the largest ones are actually for either the atomic or the molecular system. N2 is actually a very difficult system, which every quantum chemist will confirm. That's not an easy system to deal with. Okay, we need high accuracy on many occasions. For example, you may have different phases, and occasionally very small energy differences may actually decide the phase which will be realized under given thermodynamic conditions. Another field, vast field, is actually dispersive forces, dispersive interactions, which some of these, especially density functional theories, have very hard time to actually get right. And there is a plethora of other occasions where the correlation and accuracy are very important. So this is now back to the Coulomb repulsion, which typically realizes if you have d or f orbitals, and typically there are transitions there which actually try to minimize that integral there, which is the Hubbard U, so-called. And these are the electronic wave functions there. And typically this is a MOT transition, which is a metal to insulator transition, which forces the electrons to actually localize in space. So you get something which initially looks like that, and you get it localized, and that happens to minimize that repulsion energy there. Okay. It's a textbook phenomenon, really. This is more from our own work. which is ionic system. This is titanium oxide, and under normal circumstances, everything is totally balanced, so you will not see any spins, any excess charges anywhere. But if you introduce defects there, such as, for example, hydrogen defects, which are very common in this material, then you actually get these charges localized on the lattice. They form polarons, and they localize on the lattice, they deform the lattice. And this is a phenomenon which, again, you cannot get by these, you know, simple DFT approaches. I mean, it would be completely smeared out rather than localized as it should. Okay. Now, chemical accuracy, that's the magic word for every chemist. And there is a good reason for that, because it's extremely difficult to actually achieve. And it's extremely important because very often, like, the stability of the phases is decided on that energy scale. 1 kcal per mole, 400ths of an electron volt, or 1 millihartley. Take whichever unit you like. And I will now show you a few examples where that obviously doesn't work, okay? So I will take my main reference here will be DFT model, and I will compare typically with respect to that model. So this actually got me into quantum Monte Carlo. Look at the date there. This is 95, which is almost 30 years old. At that time, I was very happy doing all kinds of DFT calculation. I thought I could do everything in the world. Then there was this Trieste workshop, total energy and force methods, which at that time was very popular. I was every year there. Maybe they still run it these times, I don't know. And I saw that and I said, gosh, I mean, there is something, I mean, very, very, very strange here. Look at the energy scale. The energy scale is 4 electron volts. That's a huge energy difference. Okay, not 400ths of it. The energy scale is 2 orders of magnitude larger here. System is extremely small. 20 carbon atoms, okay? First row element, nothing really very complicated at the first glance. And there are 3 structures here, ring, ball, and cage. They all are minima on the potential energy surface. And the question is, which one is the lowest energy structure? And now, if you take LDA, which is the simplest density functional theory approximation, you find that the cage is the ground state. It's not surprising because that approach always tends to compact the system because it has borrowed all the genes from the LDA, and hence the solution is compact, make the system compact. If you do Hartree-Fock, just and the cage is actually running in LDA. If you take Hartree-Fock, just the opposite is the case. You want to heterogenize the system, and this ring structure will win. And then if you do things properly, if you do quantum Monte Carlo, you find that the ball structure is, as often also in real life, the compromise is the best solution. So you see it here. The ball structure is the lowest energy. And again, the energy scale is 4 electron volts here, you know, simple system. This here is more from our own, you know, work, a little bit early, a little bit younger. So this is now, you take a very simple system. You take a benzene molecule, you take a vanadium atom and you put it on top of it, and you form what is called half sandwich. And vanadium is, of course, 3D metal, so metal atoms, so you actually have a lot of ways how you can stack up the electrons in the d orbitals, and the question is, what is the lowest energy spin multiplet of that system? Okay, so now we have newer functionals, not LDA anymore, but again, I mean, if you take this one, which is the Perdue-Wank-91, you find that the duplet is the ground state structure. If you take bisphylid, which is a global hybrid, you find that the sextet is the ground state. And if you do quantum Monte Carlo, you find that there is practically no winner whatsoever. They are quasi-degenerate here. And again, the scale here is now 1 order of magnitude smaller than on the previous graph, but again, 1 order of magnitude larger than what we would like to see. Still huge differences, okay? Okay, this is yet another example. With all these mean field methods, the problem is that the single particle energies, they are Lagrange multipliers, typically having no physical meaning whatsoever. Hence, for example, calculation of band gaps is very, very difficult. And in most cases, you get complete rubbish out of it, okay? And this is band gap, I mean, in material science is the principal property. You need to know what in the semiconductor, what the band gap is, that every engineer is the first engineer would ask you. And there are different methods. This is a 2D system, 2D single layer phosphorine. These are crystals, two-dimensional crystals, but they are just one atomic, they have one atomic thickness. They are one atom thick, okay? And now, obviously, there are billions of calculations for all kinds of systems, including the phosphorine. If you do DFT, you see the spread, 1 electron volt. You can hope to do something better, which is GW. I am not going into that. That's a perturbative technique which you can build on top of, say, DFT. You spend 1 order of magnitude more work, both human and machine, and you find that there is actually tremendous scatter as well, from 1.6 to 2.4. Again, almost at 1 electron volt scatter. If you then do DMC, I'm not going to tell you what those are. Those are different approaches, not so important. So actually, you end up with a band gap of the order of 2.4 electron volt. Okay, and that's much larger than most of the other approaches, including the GW is actually predicting. Okay, this is yet another, that's the same system, but now I am actually looking at 2 sheets of that very same material, and these materials have very strong bonds in layer and much weaker dispersive forces which keep these layers together, which is van der Waals bond. And the question here is how that bond actually behaves. And this is now the quantum Monte Carlo calculation, and there is a plethora of several different DFT approaches, and if you look closely, you will see that none of them is really doing very well here. Okay, even though they have been specifically tuned to describe the van der Waals interaction, and this is just the bottom line. That somewhere I read that there are about 300 density functionals, exchange correlation functionals out there. So you always can choose the one which may eventually fit your wish, but you never know which one, unless you know the result beforehand, you never know which one to really use. And there are many: local hybrid, meta hybrid, double hybrid, scan, and you tell me, I mean, there are many. There are just different groups. Okay. Okay. Now I'm coming to the efficiency of the methods. So that will be extremely hand-waving, this next 5 slides roughly. So we want, this is the equation we want, that's the same from the first view graph, and we all know that the formal solution will expand in the determinants which form the many-body basis. That's formally correct. If you can do that, that scales exponentially. If you can do that, then you get eventually the correct result. And then actually, in order to do that, you need to solve these single particle equations and feed the orbitals up there into the determinants. And then you need to construct these single body orbitals, which you can construct from atomic basis, Gaussians, or even plane waves. It depends on you, how you really want to do that. And then you do the typically from the bottom up. So that defines the hierarchy. The problem is that these methods are very inefficient typically. I mean, there is a lot of work there now, and of course, things are constantly improving. But if you now think of this new HPC infrastructure ecosystem out there, so these are probably not the methods you would like to use in order to make a good use of tens of thousands of cores and tens of thousands of GPUs, etc., etc. So this, even though there is also work along this line, but this is probably not your first choice with respect to the exascale computing, okay? Okay, so now we change completely the paradigm, and again, this will be extremely hand-waving, and my esteemed colleagues will go much, much deeper than I have the ambition to do so, to do here. So basically, we want to use projection technique. So we start some track, and now I am in it. This is now many-body Hamiltonian, and R stands for 3n. If I have 10 electrons, I'm in 30-dimensional space. And I want to, rather than trying to construct the wave function by brute force, by doing these determinants and everything, I do something different. I start with a trial wave function. The only requirement is it must not be orthogonal to the ground state I would like to achieve. And I do projection. And I use this operator here. This t is either imaginary time or is just a label to basically mark the projector parameter there. It is very easy to actually show, if you expand the wave function into eigenstates, that if you do this projection for a long time enough, you will actually end up in the ground state. Okay? So that's the basis of these projection methods. And it seems that you can only converge to the ground state, but I said you can also calculate band gaps, which means at least the Lumos state. So you can actually prepare this trial wave function so that it is orthogonal to the ground state, and you can actually converge also to an excited state. Okay, if you make the proper initial choice, and that's how it is done if you want to. Or something similar if you want to get the, okay. You can rewrite it in terms of the imaginary time Schrödinger equation. That's a formal solution. You need the propagator, the Green's function, which you know for short times. For short times, you actually know that Green's function explicitly, analytically, and you can actually propagate this function to get the long time behavior. That's the formal, solution. And these equations actually can be solved via stochastic methods. That's a knowledge which is known for decades, and you can apply it here. Okay, so basically that's the equation, and I want to map it onto equivalent stochastic process. And the way how I do that is that I expand this wave function in terms of sampling points in this 3n dimensional space, and that defines me a new basis set, which is these delta functions. Okay, and every quantum chemist will tell you that this is probably the best basis set you can have, not having many problems associated with the other basis sets. Okay, so you essentially take the short time approximation, and then you evolve that wave function. That is nice, but let's think of what was in the first. Okay, so that's how it works. That's an example which you will find in every textbook. So essentially, this propagator contains diffusion. So given that potential there, which is something like harmonic potential, you start with something which is a homogeneous distribution of these Walkers, which are just points in the space, and you do the diffusion. Okay, and then there is yet another term here which defines the so-called death and birth processes, where the potential energy is high. These points are dying, and they are duplicated at points where the potential energy is low. So in the end, you can actually get a numerical sample of your wave function. That's a very simple procedure. And that's actually where the problem starts, because the wave function must be anti-symmetric. And that's what makes the whole thing difficult, because that's not the ground state. Actually, in that propagation, the ground state is a bosonic wave function. So if you do nothing, you will converge to the bosonic state, which is completely wrong. So, and you will lose that fermionic signal exponentially fast. Okay, so that is what we don't want to have. So basically what we do, we introduce one approximation. This is the only fundamental approximation in the whole procedure here. And that means that we tell the wave function where the nodes of the wave function are. And there must be nodes, obviously, if we have a fermionic wave function, because like I said, if I exchange the particles, I change the sign. So somewhere in the middle or somewhere on the wave from here to there must be a zero, obviously. And we tell the wave function where the nodes of that wave function are. And that's the only fundamental approximation we have here. And that defines a 3n-1 dimensional space. And typically, the typical procedure is that you actually start with something very similar, something very simple. Say, I'm not saying you should do that, but let's imagine you start with Hartree-Fock. That's very easy to do. That will give you some some nodes there. Nodal hypersurface is there. And then you actually do the propagation as I outlined based on this Hartree-Fock. No, the bottom line is that you are making, if it is not completely wrong, like completely, right? So you are making errors where it matters least, because where there is a zero, so the workers won't go there anyway. So they will want to stay away from those nodes. So that probably is the reason why these simple approximations are actually quite efficient. And this is actually what happens here. You fix these nodes, you know, and then you do the evolution. And so the only thing which will change is actually the weight, the shape of the wave function somewhere inside the nodal, the spaces which are outlined by the nodes. And okay, so these are now, I said this also, I mean, we changed now the paradigm. Instead of diagonalization and exact construction of the wave function, we have something else. We somehow, using cheaper methods, we outline somehow the nodes, and then we do the evolution. Typically, these methods, I mean, again, this is a rough number, it's a hand waving, is typically an order of magnitude more accurate than, say, the DFT, which is my main comparison benchmark here. Unfortunately, they are roughly 1,000 times, 3 orders of magnitude more expensive. The reason is simple, because we are doing stochastic sampling, so we have some error bars associated with those processes. And in order to get the error bars down, that goes very slowly, because that goes like 1 over square root of m, when m is the number of points I have sampled. Okay, and however, having said that, the scaling is perfect. You know, this is the speed up versus the number of cores here. This is the ideal scaling, and this is the scaling we have measured on that phosphorine system, going to quite large, you know, sizes, numbers of cores. There is some degradation past about 40,000 cores, but I mean, that was a code which is now not, that was QWalk, which is not really used very much these days. So I suspect that if we did it with TREX codes, the scaling probably would be a little bit better than the one here. And this is why actually this is efficient, because you can basically take those these walkers and the Markov chains, as we will learn, and you can basically put them on the cores or GPUs, and they run more or less independently. You don't need to communicate a lot. They are pretty much, the measurements are pretty much independent. There is one thing there, that if due to the bears and death processes, you will eventually have a disbalance of these walkers after a while, but the codes will take care of that, and they will rebalance the calculation. Okay, so this is a general slide how we can actually proceed. So this is the computational cost, and here is the accuracy. So this is the point we would like to be. Obviously that cannot, both systems cannot be done, or if then it's exponentially expensive. So we start with something very simple. You just take, say, a single, you know, determinant or something, and you can actually improve by improving that wave function in several different ways. Then there is, you will hear about all that. Then you can do what is called diffusion Monte Carlo, and you can improve further, you know. And then there is a limit there, which you have some finite budget, both in terms of human time, because your PhD student cannot take 7 or 10 years to get one result. He rather has to get it in half a year. So, and there are also much machine, because the cost may be tremendous. We are talking tens of millions of core hours in really ambitious applications. So there is some fixed budget you have, so you will probably have to stop somewhere, okay? Where the accuracies, or, I mean, these methods are systematically improvable. The question is how much time you are willing to put into that improvement. Okay, few examples. This is G1 set. This is quite famous set, and this is the accuracy. This is the chemical accuracy here, and you see this is the DFT. So in all cases, this is not up to the accuracy we would like to have. Then these are MP2, again, not much improvement. Then there are coupled clusters, and these coupled clusters, then if you improve the basis set, you can actually come quite close to the chemical accuracy. Then there is again an improvement over, I'm not going into that. If you do VMC, then this is not really what we would like to have, because this is almost worse than the DFT. But then if you do the DMC on top of that, depending on how accurately this is the increasing number of determinants, you can actually eventually get it below the chemical accuracy. This is an extended system, oxides. Again, these are simple DFT approximation. The error are quite sizable. It's always overbinding, actually, LDA. And then these other functionals, which are GGAs and hybrids, etc. The errors are much smaller, but still much larger than we would like to have it. And here is what we get from some QMC modeling. And this is the last slide I want to share with you. This is an old result we had, and that also gives you some insight as to what may actually be going on. This is again this vanadium benzene simple molecule. And there are different approaches here, different nodal hyper surfaces, be it DFT or post R3-FOC, and we were basically trying to find the minimum of where this vanadium atom sits above the benzene molecule. And if you do DFT, don't pay much attention. These are different DFT functionals. You see that this actually jumps quite a lot. This is 0.2 electron volts, so the differences are by no means small. And actually here, this is CAS-SCF in a decent but rather limited space. And so actually this one here appears to give the worst results. The distance is by far too large. However, if you now run the QMC on top of that, you actually see these are these red arrows here. So actually you get something which is wobbling in a very limited range. So that actually says it all, that you know, I mean, if you are, whatever you are using, if it is halfway decent, then you are making the errors where it doesn't really matter that much. Okay, I'm done. Okay, thank you very much. And I'm happy to take questions. This was all very hand waving, right? So. Yeah, go ahead.
Just to mention that the second error, the first node error is not the only error. I think there is also the time step error, which is systematically.
Yes, there is time step error, but that goes far beyond these, you know, very hand waving arguments. Yeah, sure, there is there is
So I just
fine.
wanted to mention that.
There is, yes, and that has to do with the fact that this propagator there is valid only for very infinitesimally short time steps, which these time steps never really are. Yes, certainly, yeah. Okay, so if there are, if I don't see, okay. Yeah. Can you please comment on what?
Can you please comment more on Walker's and their selection are these diffusing orbitals? No. So she's confused which person.
Comment on Walker's? Oh, Walker's, how many Walker's, etc., right?
No, she's asking what you're diffusing.
Oh, what I mean, I thought it was quite clear. So we need to shoot at the beginning some distribution of workers there, okay? And these workers there is a diffusion term, so they will move in the space of the wave function, okay? They will search the space of the wave function. They will be diffusing, and from that you can actually reconstruct the energies, etc., etc. They eventually will die if they happen to wander in the part of the space of the wave function where the energy is large. It will die, and another will be rebirthed somewhere where the energy is small. So it's the Walkers which diffuse. Diffusing, okay, I think you can actually look at that. You can actually try different. I mean, you have seen it in the last slide. You know, I have used different actually DFT nodes there, and it changes the results a little bit. But in that particular case, at the least, the differences were not huge. And you can actually look at total energies, and you can actually look at the functional, which gives you the lowest energy if you really wish to do so. Mm-hmm. Yeah, sure. Okay, maybe here, I mean, that's probably enough to actually see what's going on, right? So we somehow need to, that's a complementary, basically, information to the number of determinants. I mean, you can outline your many-body problems in terms of these, you know, billions of determinants, or alternatively, you can do something very similar in terms of the nodes. I think the information there is somehow complementary. So, yeah. It is simple because, you know, in the simplest case, you take, say, Hartree-Fock orbitals, you do vanadium benzene, for example. That was one of the examples shown there. You solve, say, I want to do the simplest possible approximation, so I solve the Hartree-Fock equation. That will give me a set of single particle orbitals. I put these orbitals into a determinant, and that basically already tells me where the nodes are. Then there is I mean, if you do QMC, there are other factors around, but basically the nodes are determined by zeros of the determinant.
So does that mean the force going to Monte Carlo in order to determine the node, we have to first?
Yes, you need to. Yes, I actually did it very quickly. So basically, you construct somehow this trial wave function, and the trial wave function will tell you where the nodes are. And you can construct it in many possible. I mean, there is a lot of freedom there, and you can work on a systematic improvement. You may start with a single determinant, and you may shoot more determinants there, etc., etc. You can try different DFT functionals, for example. There is a lot of freedom there. And it depends on your patience and you know, time you want to spend with that, and you can systematically improve.
There was a question about market properties.
I don't see the question. Or maybe I have to. No, I don't see it. Ah, okay, it's there. I am DFT person and use linearization and magnetic force theorem to that, but we don't know that this is correct or not. Well, I'm afraid I have no answer to that question. Okay, okay, yeah. Yeah, but there is a question there specifically with DFT, so I don't know. Yes, I think it is definitely possible. Yes, you can do that and you should do that. Yes.
Should we do the next?
Sorry? Yeah, sure. Go ahead. Yeah, sure. Yeah. Oh, I see. Okay, I will stop the, okay, so thank you very much for your attention, and we get now things much more accurate than my ambition was here. Okay, thank you.
Can you move the table closer to the?
I don't think.
Yeah.
Yes,
Yeah,
yes, yes.
and also this one.
Probably it helps for the Zoom, right? Yes,
Yes,
yes.
yes.
It's just due to Zoom, yes. Not due to this. Yeah, also this one. Please stay. This is so. So put it this somewhere. This is microphone.
Okay, one second, God is gonna, I'm gonna lose my pants.
This
the
one.
way. There, very good, very good, very good. Good, so fine, like that. And that's for mine, so there's something like that.
Okay.
Okay. Okay, so attention, please. Okay, good. So I will go through what Ivan described in a bit more slowly. Okay, so that's the first part for before coffee break. So let me see, it works. Okay, so Monte Carlo methods are a very large class of approaches, okay? And what they do is they make repeated use of random numbers. So you can do so to simulate something which is truly stochastic, okay? But what we are doing here, we are mainly using it to solve a deterministic problem using probabilities. Now, Monte Carlo methods are very much used in statistical mechanics, so for classical simulations, okay? That maybe they are where they're mostly used. And the idea there would be that you sample the Boltzmann distribution and then you are computing averages, okay? So, and by averages, I mean integrals in many dimensions, and if you are in a finite space like, you know, spins, it would be very, very big sums, okay, over many configurations. Now, if you go to quantum mechanics, we put a quantum in front of Monte Carlo, okay, and that's what we are going to cover today. So the simplest example you find if you go to Wikipedia for a Monte Carlo simulation is the idea to have, you know, to compute essentially the area of a circle, okay? So what you do, you inscribe your circle in a square, and now you start to throw darts, okay? And you assume that, you know, you're good enough, you're always going to be within your square, and you're going to do so in a uniform manner, okay? So you're really not making, let's say, so uniformly in the square, Okay, so some of the points will be inside the circle, that's the red points, and some will be aside. Okay, so you're doing randomly, and then what you do, you count how many times you have been inside the circle, divided the total number of hits in the square, and you have the ratio that's proportional to the ratio of the areas. Okay, and that's if you're doing many hits in this limit, you're actually going to estimate, the value of pi. Okay, so that's something quite simple, but what you want to do here, as I said, I talked about integrals. Okay, so you're having a function f of x defined between a and b, and now you want to compute, the area of the function. You could do the same. You could inscribe your function inside the rectangle and then start to hitch with random numbers. But that's not, that would be a rejection method, but that's not what we will do here. Okay. So what you have is you're having your integral, which is the integral of this function. And now what we do is we do something very simple. We multiply and divide by the length of the integral. Okay. So you're having b minus a outside. And here what you're doing, you're computing the average of the function in the range AB. Okay. So, okay, so we are computing this object. We can forget about the b minus a that we can do. Okay, so this is what we are trying to do. And now you can notice that you're rewritten your integral as the integral of f of x times p of x. Okay, that's probability distribution is uniform. Okay, so this is your segment. P of x is 1 divided by b minus a, and you can that's positive, integrates to 1, and that's a probability distribution. So what you can do, you can actually draw a bunch of random numbers, m of them, distributing according to p of x. Okay, so you're throwing them uniformly. That's a uniform distribution, and you're having many points. And what you can do is you can compute your function, which is here over those points. So that's an f of xi. You sum over all points and you divide by the total number of points. Okay, and that's an estimate of your integral. Okay, everybody okay with this? So now, if you're having something is still within, yes, Jean-Baptiste, we will save the presentation. So now we're having an integral of this function, which is not like, is much more peaked, okay? So using a uniform distribution is not the best thing you can do, because your function is really, let's say, very much, confined to the central part of your segment AB, okay? So what you can do, let's assume you can sample something which is more similar to it. You are in a much better position. You can rewrite your integral as f of x divided by p of x multiplied by p of x. Nicola Zazzari, can you just turn off the chat, otherwise it's very distracting. Okay, Zazzari, go. Nicola, bravo. Okay, so we are sampling p of x. Okay, so it's not the same. I mean, if you can sample f of x, that would be the best. You're done because you already know the integral. But let's assume you can sample p of x still in E and B is a much better way of computing the integral. And now what you would do, you would still draw m random numbers. So these are points, in x between A and B. You will have many more close to the maximum, fewer in the tails. And then again, you do the same game. You say, what do I need to compute now? It's no longer f of x, but it's f of x divided by p of x. So I sum over the points of this quantity, divide by m, and I have an estimate of my integral. Okay? Okay, so if you're doing Monte Carlo integration in a nutshell, you have a function of which you want to compute, the average, so you're having a of x, p of x, for instance, between A and B. Then you are having p of x is a probability density, is greater or equal than 0, integrates to 1. You sample, and we're going to see how we sample. I haven't yet told you how. We sample a bunch of points in the dimension where you are, in the space where you are, x1, xm, from p of x. And then you estimate the integral just by summing A over all the points, okay? And in statistical physics, what you will have the Boltzmann distribution, okay? So you would do it to compute, thermal averages. So, okay, Ivan already covered. So we are in quantum chemistry or electronic structure, how you wish to call it. And that's what we are going to cover
today. Okay, so even already explained it, there is DFT. Look, is really very powerful and it's much cheaper. So if you can, you should do DFT. Okay, so let's be honest. Okay, but then if you cannot because it doesn't work, you have to resort to quantum chemical post-Trifoc, or you can try to use quantum Monte Carlo. Okay, so and where we are solving the Schrödinger equation stochastically, and we are having contributed to generate, quite accurate calculation for medium to large system. We can also do solids. So this is an example. So why should you do it? If I look at talking about quantum Monte Carlo here, we're going to talk about real space quantum Monte Carlo. Okay, so I will mention at the end that there are also different flavors of quantum Monte Carlo. Okay, so what we do is we are working in first quantization, not in second quantization. Okay, so it has a favorable scaling. The energy, for instance, is order n to the fourth. You have a lot of flexibility in which many body wave function you can use because you're using Monte Carlo to compute integrals. Parallelization is easy, and as I said, we can routinely do relatively large system, molecules with up to 100 atoms. Most of the experience is on second row. There is a bit less experience on transition metal overall. And this is already a few years ago, is a work by Dario Alfé on relatively large system where he was interested in benchmarking van der Waals to understand, how to build a DFT functional and, what is right and what is wrong. So now, as I said, we are quantum, so we have an Hamiltonian. And you're having an expectation value, of the Hamiltonian, that's the energy. So you take your Hamiltonian and you sandwich between the wave function divided by the normal wave function. Okay, so you're having two integrals, one in the numerator, one in the denominator. Okay, so that's written like that. And then what you do is you start to look at the numerator and you multiply and divide by psi. Okay, so here we are in real space. R can be whatever dimension. It depends if a 10 electron will be 30. Okay, so but what you do here is you multiply, divide by psi of R. So you end up with psi R squared. And what we do is we bring the denominator, so this quantity here inside the integral, and I put a box around it. Okay, and this is your probability density. Okay, so this object is positive. Is a wave function squared, even if your fermions is positive, integrates to 1, so you can interpret it as a probability density, okay? And then you can call this object, which you can always compute for every configuration of your electrons, is a local quantity, your local energy. So that's simply the operator acting on the wave function divided by the wave function, okay? That's your local energy, you integrate over all space. And what you're going to do what I showed you before in one dimension, but now in many dimensions. You will try to draw a number from P of R and cumulate EL of R along your path, okay, around your random walk. Okay, so is this clear? Because that's the basis for the rest. Is it clear what we've done here? If not, you got to, well, no, Otto, of course it's clear to you. So to the people who are not in TREX, it's good? Victor? Okay, so we are using Monte Carlo again to compute an integral at the end of the day, okay? So what you do, you sample a bunch of configuration R, they are in 3n dimension, if you're having, n electrons, okay? So R is R1, Rn, and now you are sampling a bunch of points, so, all configuration of your electrons, using, from P of R. And we're going to do so by using Metropolis algorithm. I will explain it in one moment, okay? And then what you do, you collect your average, your local quantity, that's your local energy. And again, you do, as said before, you sum all the local energy around these points, and you divide by the total number of Monte Carlo steps, okay? So here, that's the basic let's say, realization of quantum Monte Carlo, that's called variation of Monte Carlo, and essentially it's just a trick to evaluate integrals in many dimensions. Okay, very much like you're doing in classical mechanics. Okay, so of course, this is just, I don't know, some cluster of silicon 21, so the dimension can really be many. Okay, so even if you throw away the core, you're keeping 4 electrons per silicon, you end up, 4 times 21 silicon, 22 hydrogen, you end up with 106. So the number of dimension you multiply by 3 is 318. So that's a large integral, okay? Now you can say, well, fine, you know, look, I don't want to use Monte Carlo. I'm gonna just place 10 points per dimension on a grid, okay? And then you end up with 10 to the 318 points on which you would need to compute your local energy. So that's not possible, okay? So then that's the reason why Monte Carlo is a very powerful trick to actually do so, okay? To compute in many dimensions for whatever functional form you actually wish. So if you have a very good idea of how your wave function should look like, you can easily test using Monte Carlo, okay? So again, so we're having an integral at the end of the day here, an integral which we rewrote as a local energy, A psi over psi. P of r essentially is proportional to the wave function square. It tells us where the point should be. We sample P of r and we do the sum, okay? So the question is, does the trick always work and how efficient is it? Now, to actually answer this question, we resort to the central limit theorem. We are having a probability density P and a function f, okay? So we are in a situation like that, that's our integral. Here I just did it in one dimension for simplicity. Okay, just think about many dimension x. So mu is your integral, and f of x, let's assume, has a finite, not only a finite mean, that what you want to get, but also finite variance. Okay, so that's the fluctuation of f of x. I'm sorry, the square should be outside the bracket. Apologies, that's a type. Okay, so I will fix it for when we upload the. So it's f of x minus mu squared. Okay, so or f of x squared minus mu squared. Okay, so p of x. So what you do is now you're sampling a bunch of random variables from p of x, and you're computing a mean. Okay, so for up to some values of n. Okay, so you choose, I do whatever, 1,000 sampling. Okay, so as n increases, the central limit theorem tells us that f of m is normally distributed. Okay, so with a mean of mu and a variance which goes like the original variance of your function f, and divided by the total number of steps n you have taken. Okay, sigma squared divided by m. Everybody okay with it? So, and this is true irrespective of the choice of p. Okay, so that's what we know. So that gives us a way. So you have your f of x, p of x you sample somehow, and you compute an average, and you know that the average for large m will go to your mean, sorry, mu, and you know how the variance actually is. Okay, which you can use to estimate your error. Okay, indeed, so if you're having Monte Carlo, this means that if you're sampling NC Monte Carlo points, your error will go like 1 over square root of the number of points. Okay, so we saw it here. You can use this as your estimate of your error. Okay, so sigma m will be sigma divided the square root of n. Okay, guys, good? So you're having that the error will be proportional to 1 over the square root of the number of Monte Carlo steps, and this dependence is independent from the dimension. Okay, so there is not really, this is 1 over the square root of a number of Monte Carlo steps, independent of whether you are in 1, 2, 3, or 318 dimensions. Okay, and this follows from the central limit theorem, follow from the fact that your Gaussian, for your average goes like sigma divided the square root of n. Okay, so, and we're assuming the sigma is actually finite. Now, let's see how it compares to a deterministic integration method. You can choose, one you wish, so here we are having in one dimension, the Simpson rule, and you're having that your error will be like 1 over the number of points, or your integration points, to the power of 4. Okay, you say, well, it's better than a square root of n. Okay, but now let's go beyond one dimension. So, okay, thank you very much. I'm not sure, what did you ask? Whether we can have yes. Good. We do everything. Just let me go on. So, meaning, ask a question about the talk. That's nice, but we give you all the material, so no worry. Okay. So Monte Carlo, we are having a behavior which is 1 over square root of the number of points, Monte Carlo steps. Deterministic integration, you choose something, Simpson rule, and you're having 1 over m to the 4th. You say, well, it wins, but now we go to d dimensions, so we increase the number of dimensions. Okay, the error is additive actually, but what happens is that now your dimensions are more, and you're putting many more integration. So your integration, you keep your integration per dimension, but the total number of integration points will be the integration in 1 dimension to the power of d. Okay, so it means that in 1 dimension will be m inch to 1 over the power of d, and for d large, it means that this guy will go very slowly. Okay, so generally, let's say speaking, you would say that Monte Carlo integration is advantageous if you are in more than roughly 8 dimensions. Okay, but now for a many-body wave function, recall we are trying to compute integrals which correspond to the observables, so they are expectation value of operators, and your dimension here is 3 times the number of electrons, so you are very quickly above h. Okay. So now let's see, therefore, let's say again, we keep comparing, let's say, an integration using a grid with a Monte Carlo integration. Again, we stick to Simpson. We are having an integral integration points. And what you do, you say, fine, I want a certain error bar. I want whatever, a millihartry of my energy. Okay. And then you say, fine, d is 3 an electron, there will be some constant, and now this is the number of Monte Carlo integration. So it means that for a fixed request on accuracy, your number of integration steps grows exponentially with the number of electrons, okay, with the dimension of your system. Now, if you do the same thing with Monte Carlo integration, you say, fine, I have epsilon, sigma, the square root. And now I need to have a bit of a feeling how sigma goes with the number of electrons. And now the variance, so sigma squared, is an extensive quantity and grows with the number of electrons. Okay, so we can discuss it later if somebody has some question. It's not difficult to prove, assuming that you're having the repetition of independent system. Okay, so if you guys want to try it out, we can discuss it. Okay, but so again, so I establish, I say I want 1 millihartry, sigma will grow as my system grows. So, and sigma square goes like an electron, so sigma goes like the square root as some constant, we don't care. And now you just try to invert and the number of Monte Carlo steps as a function of electron, and you find a linear relation, okay, which is surely much more convenient than an exponential growth. All okay with this? In the back? Good? Nicola? Oops. I don't know. How do I get it out? Oh, God. Let me make it maybe like that. So maybe here. Like that.
Andato su partecipanti, vedrai.
Oh, just make it small and just put it outside the screen, and we're okay. That's okay. Let me do it. Let me do it. Just put it outside the screen. Move it on.
Yeah, can we do it? Ah, it's on the other.
It's here.
Ah, so.
Okay. Okay. I was wondering.
Oh, no.
Oh, now it's even bigger. Sorry, we fix it. That's what I was saying, that Zoom adds a layer of complication. Just click the white, otherwise we don't get the white. It's strange, I didn't touch that, huh?
No, it was strange. Can I record? Can I record?
Oh, very good. Make it,
Just put it somewhere.
I cannot.
just put it outside or below. Very good, like that. Thank you. Okay. Now though.
Screen.
Good. Okay, it would be nice to be able to eliminate the bar at the bottom, but okay, let's not do it. So, sorry, it's a bit chopped. Okay, so summary. So as I said, expectation value of the Hamiltonian could be a different operator, but Hamiltonian, you write it as a local quantity times your probability density. So something proportional to the wave function squared, okay? Then you can write down the variance, it is correctly written, as the fluctuation of L around the average. All okay? Okay. And then you can estimate your value by computing EL of R, assuming you can sample P of R, and you can get sigma squared, an estimate of your variance, from the fluctuation of the local energy to your final average energy. So you can final average energy along the path. Okay. So okay. So what is nice is you can do so for any computable wave function. Okay, we need to be able to apply the operator to it. So should be continuous, normalizable. Otherwise, we have a problem. And usually, you would choose it on the proper symmetry. If you're doing a singlet, you choose a singlet, a triplet, an S state, a P state, whatever your system requires. And what we also ask is for the finite, for the variance to be finite. So the second moment of the Hamiltonian or the fluctuation of the local energy around your average energy got to be finite, okay? Because your Monte Carlo error goes like sigma divided by the square root of n. So it's kind of handy if sigma is actually finite, okay? If it is not, you can still compute the integral thanks to the law of large number, but then your, how is it called? Your convergence will be slower than the square root of n. Okay, so but let's assume you always want sigma finite. Look, okay. So and what is nice here in quantum Monte Carlo is that if your wave function becomes very, very good and approaches an eigenstate, then h psi over psi becomes what? So the local energy becomes. So it becomes exact, which means has no fluctuations, I wrote, which means it's a constant, okay, which is your eigenvalue. It's, h psi equal to h psi. H psi is constant, is correct, is the real eigenstate, okay? So h psi divided by psi will be equal to a constant. So which means that you can take one Monte Carlo step and you're done, okay? And indeed, you can see that, as the local energy becomes, if your wave function becomes better, your local energy will become closer to the average energy, so just a constant, and you will have a sigma which goes to 0. Okay, so that's something nice. So we're having a so-called zero variance principle, and it is worth to put some effort in the construction of psi. Okay, not just because not only you get a better result, but also you get it faster. Okay. I don't know why this one does it. Okay, very good. So this is like a typical VNC variation of Monte Carlo run will look like. Okay, so again, we are computing the energy, just some molecule, doesn't matter. And what I'm showing here is the Monte Carlo step, and all those dots are local energies. Okay, so you start, you place down your electron, then somehow we're assuming we're able to move them in such a way that you are resembling psi squared. Okay, so and every time we compute a local energy, we are averaging and we're getting an error. It was mentioned by Ivan. You always have a statistical error. Okay, and then you're also having, you can compute your variance, and indeed you can see it. So sigma is there, it's quite large. That's almost 1/3. Okay, so it's not small. And you can see that most of the points will be within few values of sigma. Okay. Because, okay, so what you would do is, you would throw away the beginning, the first few steps, and then you would cumulate your average energy, which is the blue line, which will become this result with an estimate of the error bar. Okay? Therefore, okay, so what we need to do, okay, fine, roughly we explain the method, but now we always talked about sampling P of R, so psi squared. So we need to tell you how to do it. So you want to obtain a set of configuration in 3n dimension, which are distributed according to P of R, okay? Very much like in classical Monte Carlo. Then you need to build your wave function. You must make choices, okay? So what do I do? Do I start from a DFT? Do I need multi-determinant? And in all honesty, at least for our group, that's where we spend most of our time. Okay, and that's very much an open topic of research. You know, what is a good wave function? Then you need to compute the expectation value, and you wish to do so for an expression of the local estimator which fluctuates little. Okay, so you would like to reduce the fluctuations, not just by using a better wave function if you're doing the energy, but also for operators where naturally you have a finite variance. Okay, try to rewrite your local object, your sampling, in such a way that your variance is reduced and it takes you less to converge your Monte Carlo integration. Okay, and that's also an open topic of research. Okay, so now, let me see, So how do we sample P of R? Okay, so what we do is we generate a Markov chain. Okay, we start from some configuration and we move it using a transition probability starting from I and go an initial configuration to the final using this function, okay, which only has memory of where you were before. Okay, so you start from R0, you go, you keep moving from R prime, R second, and you generate a random walk in 3n dimensions, okay? M is given an arise, a conditional probability, you are sampling, this is what brings you from Ri to Rf, okay? So you're in Ri, with some probability you will move to a final value, okay? So M has to be greater or equal than 0, therefore. And then what you're asking is that if I start from somewhere and I integrate over all the final configuration, I get 1. So it means that my walker doesn't die, doesn't get lost. I have a probability 1 to go somewhere, okay? I could also stay, that's also a good move, okay? I could stay, I could move, but let's say I'm gonna go somewhere, okay? And this is the definition for what we call a stochastic matrix. Moreover, what we want is at the beginning you have no idea. You place down your electron and then you start to evolve them, okay? And therefore what you would like is that, you know, independently on where you start, whatever is your P initial, maybe you put them uniformly in a box around your atom, okay, you want that, you know, if you keep applying M, eventually this configuration evolve to P. So that's what we want, because you want to compute the integral, you want to average with respect to P. Okay, where P tells you where psi squared, where my configuration are actually important. Are there questions? Good.
When you say that we go in a random walk, there can be
configuration, sure. No, but that's good. I mean, suppose you're suppose you're in a very good, no, you don't want to avoid it. Okay, so suppose you're really in a good place, okay, where the wave function is happy large. And now I propose my M sends me to the tail of my molecule. I mean, that's the probability to go there will be the psi of R there will be very, very small. Okay, so most likely I will reject the move. Okay, but that's good. It means that where I am will count twice. Okay, because it's an important configuration. So sometimes actually you want to stay where you are. You want to sample more around where you are. Okay, then maybe go somewhere where you have a psi of R squared, which is of little importance. You're going to see how this comes in the actual algorithm. But it's a good question. So repetition is not bad. Okay, other questions? Can somebody read it? Because if I start to open the chat, then we are dead. I keep going? Okay. Very good. So okay, so M, so P of R is given, psi squared, somehow I gave it to you, okay? You know, you take the Conish determinant, I'm not sure why squared, okay? So for instance, M is what we want to generate, okay? So, and we want to have these properties being satisfied, and we do so by imposing the stationarity condition. Okay, so we have P, and what we do is we build a stochastic matrix M, so greater or equal than 0, the probability of going somewhere is 1, and now what we're imposing is that if I start from P over I integrate over all initial using M, at the end of the day, so I have a P over I and apply M, I get P, okay, and this is true for every final point. Okay, you can view it as an integral, but you can think in a finite space is like a matrix vector multiplication. Okay, I start from somewhere and I end up in the same distribution. Okay, so if I have what is telling me, the condition is that if I start with the right distribution P, my wave function squared, and my M is such to satisfy this condition, so we must build an M which satisfies this condition, we continue to sample P. Okay, that's good. Okay, so I have all my electrons are finally resampling psi squared, and if I move them more, I want to keep psi squared, not change distribution, okay? Nevertheless, also what we want is that even if you start from a P initial, which is bad, you eventually get P over. Okay, now I'm not going to prove it mathematically, but this condition, together with the fact that any stochastic matrix, plus the fact that, you know, I have an algorithm which allows me to visit the whole space. And if I have a somewhere, I'm go somewhere, I also have a possibility to come back. Okay, so it's not like I get stuck in regions of space. Okay, so ergodicity. Then the three condition ensures that any initial distribution will evolve to P. Okay, so imposing the stationary condition, stochastic ergodicity, not only I keep P if I'm sampling it, but also if I start from something wrong, I'm going to end up in P. Okay, so, and I'm not going to prove it to you. So believe me, okay? But now still, you say, okay, fantastic, great, but I end up with another integral. How do I impose it, okay? And what we do also in classical Monte Carlo, you impose detail balance, okay? You impose a condition which is stronger than the stationarity condition. You're imposing that if you're starting from I and you go to F, is equal starting from F and going to I. So you're imposing the flux in both directions is the same. Okay, so it's a stronger condition. Okay, it's a stronger condition. But you can see that, you know, such a condition, if M, so P is given, I'm trying to build M, okay? So if I impose detail balance, the stationary condition is automatically satisfied, okay? So let's write what is the stationarity condition. So I have P over I have from Ri to Rf, and I integrate over all I, okay? Now I use this condition, so I can flip I and F, okay? This P over I becomes P over F. You guys see it, you know, just plug in that equation, okay? And now you're using, though, you're integrating over I, and here there is F, so this one doesn't care, I can do my integral. And since N is stochastic, the integral over this value, so here I'm starting from F and going somewhere, is equal to 1. So here I end up with P over F. Okay, so if I can build, given P, an M which satisfies detail balance, I also have stationary condition being satisfied. Okay, but this is a stronger condition. It's not necessary, but it's surely sufficient to ensure stationarity. Okay. So, but now, okay, still you're saying, God, you know, fine, greater, and simplify, but I still don't know how to go about, given P, to construct the M. And now what we do is what was suggested in the original Metropolis paper. So we are splitting M into a proposal, transition matrix, and an acceptance. Okay, so I write M as T from I to F and an acceptance from I to F. Okay, so the point is you need to have something which, given I, you can an initial position, you are able to sample. Okay, you need to be able to sample this object. So you choose T. It can be a Gaussian, you can sample a Gaussian. It can be a box around your electron, you can sample a uniform distribution. So you need to use something which you can sample. You must be able, otherwise you cannot use Metropolis to do Metropolis. We get into an infinite loop, okay? So you choose T, you can sample, but T will not satisfy detail balance. It will be something, okay? something that you can actually put on a computer. But then what you do, you say, okay, fine, I do what I can as a poor, whatever, man or woman. And I chose t, which brings him from I to f, so is greater or equal than 0, integrates to 1. So I always go somewhere is a stochastic matrix, but then what I will do to impose little balance, I will decide whether the move is good or bad, okay? So what you will do is you will say, fine, sigma is the detailed balance condition, so is a stronger condition than stationarity. So P is given, and now I split it in something which I decide. I put a box around every electron, you know, and I just move the electron inside the box. That's my T, good or bad, that's what I do. And now I need to determine A. So I write A, I write the ratio. So I try to reshuffle everything to have all what I know. So P and T, okay, T I choose, P is given, your Connechan determinant squared. And now I have to choose an A which satisfies this condition, okay? That the ratio is equal to this, let's say, from the probability, the ratio of the probabilities from initial to final, and this is your transition probability from final to initial and from initial to final. Okay, so it's a little math. Everybody okay with this? Now, what we will do is to actually, so there are multiple choices you can do, but you know the one which maximizes the acceptance is to choose the minimum between 1 and the quantity which was on the right-hand side of the previous equation, okay? So it's having this equation, and now if you're choosing this A, you are satisfying detailed balance, okay? So what you can try to do, you can try to do it yourself. There are two situations. So let's assume that this one is to go from I and F, and that the object is ratio is greater than 1. Then you will go from I to F. The acceptance is 1, okay? But then it means that the acceptance for the reverse move will be the ratio flipped, so it will be less than 1. And you're going to see then that the ratio satisfies detailed balance. Try to do it. There are two situations, that you're greater than 1 or less than 1. Okay, and the acceptance in the other direction is always 1 over. Okay, so you will satisfy the equation on the previous page. Do you believe it? Do you want to try in the afternoon as homework? I don't know. But okay, so you need to, so this is given, P is given, and now you need to choose from I to F, and you choose the minimum between 1 and this object, and you're having that if it is greater than 1, the A from F to I is 1 over, and if it is less than 1, the acceptance from F to I will be greater than 1, and there are two possibilities, the ratio is satisfied. Please do it, okay? Convince yourself. So, okay, so now, so this choice has also a very great advantage that P of R does not have to be normalized, okay? So, as I said, you can choose your P of R being the wave function, well, it's the wave function square, but in principle, there is a denominator, which is an integral. So, if I have the Connechan, I'm happy, okay, it's normalized. Okay, but now I will see we do something more complicated. We try to introduce a dependence on Rij, electron-electron distances. Okay, and then you can no longer do the integral. And therefore, if you need to do an integral to actually compute P, you are in a bad situation because we are computing an integral containing P. Okay, but now here, the P of R, if there is a normalization, that cancels out. So we can just assume that my P of R is the wave function square. Forget about normalization, it's irrelevant. Okay? No, no, yes. Yes, okay, because I saw no, I was like, okay. Therefore, okay, so therefore what do you do? P is given, we neglect the normalization, now we are choosing T, and as I said, what you can do is, you could also choose something as simple that for every electron you put a little box, okay? And then you move them uniformly inside the box, okay? So now the transition probability from I to F, if you view all little boxes around all the electrons, will be 1 over d to the 3n. So the volume of this box, so each electron has a little box, the volume of the complete box is 1 over delta to the 3n. Well, delta to the 3n, apologies. Okay, are we okay with this? And therefore, is a uniform distribution, and for a given array, okay, so an I is fixed, okay, this transition probability will be 1 over the volume, okay? Remember when we did at the beginning the uniform distribution between A and B, the height, because it has to integrate to 1, was 1 over B minus A. Okay, that object got to be integrated to 1, okay, if I do the whole little volumes around, okay? But now if I choose such a transition, is actually symmetric, because let's assume that I move my electron here, then I draw another box around the new position, and the T will be the same, 1 over the volume, okay? Which means that the T there would cancel, and your acceptance will be just the minimum between 1 and the ratio of the P, which is reasonable. Okay, that's going back to your question. So if my final, so I'm in some position initial, and I propose a move to a P which is greater, I'm going to accept it. I'm very happy, okay? I will accept it. But now if P is less, there is a very big difference if the ratio is 0.9 or if it is 10 to the minus 3. 10 to the minus 3 maybe tell you, well, you're really going somewhere crazy, stay where you are, okay? 0.9, yeah, you can move. Maybe, we're going to see how, okay? Okay, so now, so as I said, so again, P is given, now we construct T. So how you move in space, my transition matrix, transition probability. And a big problem is that, as we said, you're somewhere, you propose a very big moves, for instance, somewhere crazy. You keep staying, which is good, but then your moves are also sequentially correlated. They are not independent realization of P of R, okay? So, so it means that they are not independent data, they're not independent observation, okay? So if you sample P of R 1,000 times, but let's say you're having correlation on your data, your effective number of moves will be the 1,000 times, divided by the autocorrelation time of the desired observable. Okay, so maybe my local energy changes a lot or doesn't change a lot. Okay, so what you want to do, you want to choose T, which moves you as far as possible in space. Okay, that's what you would like, to really to sample, to take large moves. But also you want to reduce the correlation times. You don't want to be always rejected, for instance, okay? And therefore, what you must do is to use some freedom in the choice of T. You have it, you choose. A P is given, T you choose. And for instance, an example which is motivated by diffusion, Monte Carlo, is to use some information about the trial wave function which you're actually having. You're sampling it. And that's going to tell you where the electron should be or shouldn't be. Okay? So one way is simply saying, for example, I can sample a Gaussian, I diffuse. But in addition, I can use a quantum velocity. I can use a drift, we call it. Okay, so the gradient of psi divided by psi will push me where the wave function is large. So my T is I'm somewhere, I drift where the wave function is large, and then I diffuse. Okay, that's a transition probability. Okay, and that's probably much better than just choosing something in a box. Everybody agrees with that? And so here I'm showing an example from the an all-electron beryllium atom. The wave function is very simple, it's not very good. And then what you can say, well, I'm using the box. Okay, so I put a box around. Okay, so delta is the side of the box for every electron, and I can choose. Let's start from. I can choose a very large box. Okay, then I'm going to propose some move which make me maybe really explore space. My sentence will be very small, 0.17. I will tend to stay where I am. Even though I'm trying to move a lot, I'm not going to move. Okay, and indeed the correlation time between subsequent moves in the estimation of your local energy is very high, it's 40. It takes you at least 40 moves to have a local energy which is different than the one you started from. Okay? Then you say, fine, I reduce delta. my acceptance start to go up. Okay, 0.28, 0.46, my correlation time goes down. So now it takes me 20 moves to have a local energy which is decorrelated, okay, roughly. And now I go much, much lower. I think the box very, very small. Okay, now my acceptance is great because I know move, you know, I'm proposing so tiny moves. And again, the correlation time will go up. Now for the different reason, I'm accepting the whole time, but I'm moving very little. So it will take me a lot of moves to decorrelate. Okay, guys? Danny? Good? Okay. But now what you can do, you can choose, you can say, fine, but this is really silly. I have a wave function and I'm not using no information of it. Okay? And I can instead use the drift diffusion transition. That's what I had on the previous page, you know, when I was trying to use information about the velocity, which pushes me in regions where the wave function is large. And what you observe already, so tau is what enters in the Gaussian, so find that the scale is not quite the same, but let's say you're moving a different parameter, okay? And you can see that already that the overall T correlation have gone down a lot, okay? So they're not quite comparable. So my point is the range of acceptances is not totally, I have also much higher acceptances. And again, the game is the same. I'm going from high acceptance if I diffuse little to, low acceptance because I move very little. Let me see, no, I'm saying very wrong, apologies. So this is a large tau, so I move a lot. And the acceptance is 0.4. The correlation time is large because I reject. Then I reduce how much I'm diffusing. Okay, so here you can see again a minimum. I go from 13 to 7.8. So my minimum is already much smaller than 21. Okay, so I decorrelate much faster. Okay, and my acceptance is growing. So now I choose a very small for diffusion. I have a very high acceptance, and again, my correlation time is up. But you can see that the minimum is a much smaller values than that one there. Everybody okay with this? So it means that I have a better way of moving through space. So now, what is the algorithm? The algorithm is very simple. So P of R is given, you're chosen, your wave function squared. Forget about the normalization. You choose a proposal matrix, T, from I to go to F, must be something you are able to sample. You initialize, you place down, if you wish, uniformly or something better. And then you sample, given I, you sample R prime. Okay, so you sample T of R prime. Okay, so it can be the Gaussian, drift diffusion, can be the box. Then generally I compute this ratio. And now you want to accept or reject with a probability P. Okay, so if P is very large, you will want to accept, okay? And indeed what you do is you draw a random number between 0 and 1. Okay, so if P is 0.9, the likelihood that your random number falls between 0 and 0.9 is very high because you have lots of this segment between 0 and 1 is covered by P. So I have 0, 1, let's assume the P is 0.9, then the likelihood that you get a random number in between is very large, you're gonna accept it, okay? But then if chi instead falls in the 0.1 in the other part of the segment, you're gonna reject it, it may happen, okay, still may happen. You reject it, but when you reject it, you keep the same position, you count it twice, okay, also in your averages. And then you might throw away the initial configuration and then collect the averages. Okay, question on this? Good. Okay, so now, as I said, all of this is not very different, except, maybe you're using a wave function, a quantum velocity, and it's not very different from classical Monte Carlo, but now we need to choose psi, okay? And what we would like to have a compact representation of the wave function. And we would like to use a few thousands, many thousands, but not millions of determinants. If you're doing like a configuration interaction, where given a set of orbitals, you write an expansion in terms of single particle determinants. Everybody okay? Let me show you. Okay, so now what we do you can do various things, and in the second part of the, I think Wednesday, you will be introduced to different type of wave function, okay? But let's say if you look in the literature, most people use Jastrow Slater. And Jastrow is something which J Jastrow, and it has an explicit dependence on the electron-electron distances, okay, Rij. And then you're having the summation of the determinants, which is the usual thing. You start from your Hartree-Fock, your Kohn-Sham, but you also have all the virtual. And you can build a single, double, whatever it is. This is also, I think, a single from below. This is a two electrons jumping from different orbital height. And you can build a lot. And that's an exponential scale, okay? And the hope is that if I have that J in front, I don't need millions, but I need fewer. Okay, now we are going to see how what fewer is in towards the end of the lecture, or maybe tomorrow also. So, and just to be clear, also what Eva was talking about, the part of the wave function which changes sign, which is a fermionic, is a summation of determinants. Is the Slater part. Is the one which will determine your nodes in the diffusion Monte Carlo. Okay, so we're going to get to diffusion Monte Carlo again in a little while. Okay, so now the Jastrow factor contains one aspect which is very simple. Okay, so it can be used to cure, let's say, divergences in the potential. Okay, so let's assume that you are having two particles of masses mi and j, and the charges qi, qj. So it can be two electrons or an electron and a nucleus. And let's assume that these two particles are getting close. While the other particles are all happy, they're all far away, they're somewhere where they don't interfere, okay? They don't see each other much, whatever, they're all happy, okay? Now, two of them are getting closer, so I have Rij that goes to 0 for these two guys on, okay? And now we look at the local energy, recall, we are computing A psi divided by psi, and in principle, we would like psi to be as good as possible, that A psi over psi is actually constant, which we can never achieve, okay? Because then you have the eigenstage. Good? Okay. So now you want to look what's happening in the potential. So what will happen is that if two charges get close to each other, the potential will diverge. Okay, minus infinity plus infinity, it will diverge. So we are really far away from something constant. Okay. And now let's see what's happened if R equal to Rij close to when they're really collapsing on top of each other. So we are keeping all the other electrons don't care, so nuclei don't care. So we go to relative coordinate and center of mass for those two particles. Okay, and we only keep the relative coordinates part. Okay, so you're having the kinetic component. Now we are in relative coordinate, and therefore you're getting, you know, the reduced mass mu ij. Okay, so mi mj divided mi plus mj. And and we keep the potential, which is again in relative coordinate. Okay, so electron nucleus, electron electron. Okay, so now we go to spherical coordinates. So we're assuming that the wave function is not 0 when the two particles get close to each other. Okay, so we're looking at the S wave. There will be an L equal to, you could expand the wave function in angular momentum. Okay, so let's assume it has a non-zero component. We're looking at an S stage. Okay, so I don't have the L times L plus 1 divided by whatever 2 mu ij Rij squared. Okay, so we're assuming L equal to 0. Are you okay with this? It's an assumption for the moment. Okay, so we are keeping what diverges. Okay, so this is the second derivative of the psi with respect to Rij. This is the first derivative, and I'm having a 1 over R. This is Rij. Okay, so I called R Rij, and that's the potential which is diverging. Okay, now this guy will be something. The second derivative will be 5. 5. Who cares 5 compared to an infinity? I can just neglect this guy. Okay, I'm just writing. I'm just looking at what is diverging. Okay, and then I end up with these two quantities. Okay, I have a 1 over R, and here also I have a 1 over R. Okay. And now if you want to, what you would like the local energy to be finite, but at least you would like, well, you would like to be constant, but at least you would like it to be finite, okay? So you would like that guy there is finite. And the easiest way to do so is to impose that the two quantities cancel, okay? So if the potential goes to plus infinity, the kinetic goes to minus infinity, and vice versa. Okay, these are the task conditions, okay? What you're imposing, the derivative of psi. I put an average, a spherical average with respect to Rij. So that's this term here. So let's put it equal to 0. Let's bring this guy on the other side. Okay, you end up with x sine delta Rij, mu Ij, Qi, Qj, psi. And I remove the r's. Everybody sees that? Good? Okay. Good in the back? Okay. And these are the task conditions, okay? So again, we assume that psi is different than 0. We are in an L equal to 0 state, okay? And you've seen it. I mean, you've seen it for the electrons on the nucleus. I mean, you've done the hydrogen atom. Is a Slater, okay? He has a finite flow. Well, the nuclei, we treat them at the moment as classical particles, but you know, you're right. Well, okay, so we're gonna get in one more. Let me go ahead, two slides, and then I get back to the speeds, okay? Okay, so now, this is the condition. So when the two particles get close to each other, and now you're having the electron nucleus, which are familiar. So we're assuming that the nucleus is very, very heavy. So the mass of the electron is 1. We are in atomic units, and therefore, if one of the two masses is very heavy, you get the smaller mass out from the reduced mass. Okay, so you get mu equal to 1. You're having Qi equal to 1, Qj equal to minus z, and you're having that the ratio of the derivative divided by psi is minus z. Hydrogen atom, guys. Okay, so a to the minus r for z equal to 1. Okay, good. Now, if the electron, that's what is a bit new, you get mu equal to a half. The Q are the same, and therefore you're having that also for the electrons, you're having a cusp. Okay, you're having a derivative which is fine. Okay, so your Jastro, as Rij goes to 0, will look something like that. Okay, so it's not unnatural, it will keep the electrons far away, but will also have this behavior to have well, this non-analytical behavior if you go to X, Y, Z, but in R is, of course, okay, but you have a finite derivative in R, okay? And, okay, now getting back to the spin, so we said a half, which is what we had here. We said, you know, that's the half, but we're assuming that psi is different than 0. So we're assuming we are in a single edge. Okay, we're assuming if you go to two particles, you're having that the spin component of the wave function is antisymmetric, and that's the one which gives you the 0, but the spatial part is symmetric. Okay, so it's like an L equal to 0, so it's going to be finite. Okay, but now if you go to a triplet, you have that the spin part is symmetric and the space part is antisymmetric. So the spatial part of the wave function goes to 0. And we need to do a different treatment, okay? And indeed, you will still have a cusp, it's a higher order cusp, and your value of the derivative will become a quarter, okay? So spin of the electrons enters in the way that we are imposing the cusp condition, okay, for parallel and anti-parallel. Did you guys follow? Okay. And then the electron nucleus cusp, you can do it in various ways. You can just put them in your orbitals, or I think, you know, in TurboRVB, I think you put it in your Jastro factor. You can, but okay, but let's assume that, you know, we are using pseudo potentials, and then we have no cusp at the nucleus. Okay, so because we smoothen it, we do something nice. We don't do diverging pseudo potential. Okay, so a pseudo potential or oh God, an ECP, okay, like the chemist college is the same thing. Okay. Okay, so now the effect of the Jastro factor. So what I'm plotting here is not the Jastro factor, it's an old work by Matthew Fuchs group. And what they were doing is they were doing a solid And they are looking at the pair correlation function, okay? So I think it's a silicon, they put themselves in the 1-1-0 plane, they place one electron at the nucleus, the middle of the bond, and then they are checking what is the pair correlation function, probability to find electrons around, okay? And you can see that, you know, if they get it through quantum Monte Carlo, they get something which is really having this shape, you know, meaning it keeps the electron apart, and it also has this cusp, okay? But this is done in QMC, it's actually coming out of the calculation. So now the question is, why just rho D? Okay, so the just rho fine, we impose a cusp condition, we keep electrons apart, so you have a small Rij, a medium Rij effect, okay? But let's say, why then the D, you know? So what is our hope to have a small expansion? Okay, so what we are doing is we have a wave function, an Hamiltonian, and we are trying to solve this equation. Okay, now you're factorizing in reality. So let's assume you're factorizing the wave function. Okay, so at the moment I'm still dealing with the exact wave function. Somebody gave it to me. Okay, and I write it as J phi, where phi is everything else. And now I can define an effective Hamiltonian. It's not Hermitian, but okay, let's go with it. I take this equation, I plug in J phi, and now I divide by J. Okay, and I can rewrite this as an effective Hamiltonian acting on everything else equal to E5. I still get, you know, the right eigenstate of this operator, whatever that is. Okay, and now the idea is that, well, you come in, you have H had a diverging object, and the J, the effect of the J, is also to cancel these divergences. Okay, true for instance the cusp condition, imposition of the cusp condition. Okay, and therefore you can view H effective as a weaker Hamiltonian than the original Hamiltonian. And therefore, our hope is that phi, because of that, can be better approximated with a non-interacting wave function, okay? Like a determinant, a single determinant, or a few thousand determinants, but hopefully not million determinants, okay? And that's a bit what we're hoping. And that's, let's say, the reasoning behind the just translator ansatz, okay? So it's a bit hand waving, but okay, maybe you get a bit the gist of it, okay? Good, huh? Okay, now it seems beyond BNC. How many hours do we have after? 1. It's coffee. Huh? Very good, that's a very good moment. So are there questions before I go beyond? Well, maybe, yeah, other question, and then I can show one slide. Oh, can somebody else open the chat? Because if I open, then it goes into confusion. Okay. Either it was super clear or it was super confusing. Okay. You can also ask me questions during the coffee. Okay. Too fast, madam. Yeah. Yeah, what can I say? You can listen it over. But okay, so but let's ask a question. Too fast, guys? Some people say no. Yes or no? So? It's okay? Okay, but you are not, you don't count, Otto. Okay. Good. Kind of, good. Kind of is good enough. Yeah. So, okay, guys, do you have questions, seriously? Yeah. So you must have a linear. So okay. So as I said, you must have a finite, for instance, a finite derivative. Okay. And you can see that if you're expanding the exponential, you get something. If you neglect what is downstairs, you get something which is proportional to B0 Ij. Okay. But then what we often do, cusp condition. Very good, very good, very good. That's good. The question is good. I explain it 1 second. So, but then what you can do is you can put plus, and you can put, you know, polynomial, ratios of polynomials, and yeah, that's what we usually do. We start from zeros, so we impose these, and then we start from 0, and then we optimize them by minimizing the energy. Well, what we do is we make sure that it doesn't diverge. Okay, so for instance, we don't use Rij, but we're using scale variables. Okay, scale variables which for instance, go to a constant as Rij, or you can use exponential of minus b Rij. What you can, okay, you can use something like that, for instance, for the additional terms. Okay, so the ratio ensures that you're okay for a Rij that goes become very large, but you don't want a wave function which is, you know, changing it a lot. Okay, so you could use a polynomial where your Rij becomes an R tilde Ij, which is the exponential minus kappa Rij. Okay, so it's a very good question. Yeah, because otherwise you get crazy things, especially because you will be optimizing and you will have maybe not so much in the tails of your wave function, and then you could get something very crazy. Very good question. So I was asked to re-explain it. Okay, so he's asking how you get b in the denominator of the exponential. We optimize it. You will do it in the afternoon. You start from a 1, and then you're going to optimize it. It will become 0.6, I don't know, 1.2. Will become something, okay, which minimizes your energy. So the parameters are variationally obtained. Okay, so I was asked to re-explain things. That was too fast, madam. So I will do it again. And so, okay, so guys, but you esteem it really when you're done quantum mechanics. I don't know if you use Griffiths, Atkins, whatever you used it. When you did the hydrogen atom and you did the expansion at small distances of the electrons from the nucleus. It's the same thing, okay? Now I'm not saying it's an electron in a nucleus, I say you're having two particles I and J with different masses, different charges. And if you simplify your thinking, think about an electron in a nucleus, okay? And then the problem is that you know that the potential diverges. Okay, you know, you have a minus Z over R or 1 over Rij, there are two electrons, okay? And now what we are doing is we are looking how the kinetic energy must diverge in an opposite direction to compensate for this behavior of the potential, okay? So that's all we are doing. So, and then you say, okay, fine, you're having maybe not 2 particles, you have 100 particles, but let's put ourselves in a situation where 98 of the particles are happy, they're very far apart from each other, only 2 of them get close to each other. It could be an electron approaching a nucleus, or could be 2 electrons approaching each other, okay? Now let's say, again, you're done it in quantum mechanics, if you're in such a situation, you're looking only at 2 particles, you put yourself in relative coordinates and center of mass, okay? You do it for Newton's equation when you're doing planetary motion. You can also do it for the quantum mechanics, talking about Laplacians, okay? It's the same thing, okay? So you can have a classical derivation, a quantum derivation, and your kinetic energy changes, okay? So, but then, you know, if you're looking at the relative coordinate, that's what we care. That's when the 2 of them go close to each other. You end up with a reduced mass. While the center of mass, we don't care. We'll have the total mass of the system. Okay, we don't care about that. That's good. Okay, and then you say fine. Then you know this diverges, this must also diverge. Okay, now we go to spherical coordinates. Okay, and you have a second derivative of psi with respect to r. You have a first derivative of psi with respect to r, and r is Rij. And then you will have also an L times L plus 1. An L squared, an angular momentum squared in relative coordinates divided by R squared, okay, which also diverge. And you're telling me, why don't you consider that? For a moment, let's assume that L equal to 0, okay? So I'm taking a spherical average of my wave function for simplicity, okay? And therefore, I only keep the d psi in delta R squared and d psi in delta R, and now here you have a happy 1 over R, you have a 1 over R here, a 1 over R there, okay? So now the derivative, this part is happy, something, is a second derivative, whatever it is, okay? Is equal to some number. But now we are looking at divergences, and a number doesn't matter with respect to a plus or minus infinity. So we only keep the 2 terms, okay? 1 over R, 1 over R. And now you want it to be finite. So you make the 2 divergences cancel, okay? And that's what we do in the next slide, okay? So you say this thing should be finite. But now instead of the finite, we put 0, okay? Because you have a plus infinity or a minus infinity, depends on Qi, Qj, and you want the kinetic to diverge in the other direction, okay? And that gives you C's equation, where here I put a spherical average because I didn't consider the L-squared term, okay? Assume the L equal to 0. And this is called Katos conditions, which is telling you how the derivative of the wave function must behave as two particles get close to each other, okay? And one situation, you've seen it, again, in your introductory quantum course, and was the electron nucleus, okay? Where in atomic units, the mass of the electron is 1. Now you're assuming that your proton is so much larger that is an infinity compared to the electron. Okay, it's not really an infinity, it's a few thousand, but let's say we take it infinity. And therefore your mu ij becomes, the smallest mass becomes 1. So you're having the electron is coming close to the nucleus, which is a charge minus z, and the ratio of the derivatives divided by the wave function is minus that, which is your cusp on your Slater orbitals. Your Slater orbitals, guys, okay? So that's all what it is, the S component of the Slater, of a Slater orbital, okay? And it is not a Gaussian, like we do usually, it's actually a Slater, okay? And now, for the electron-electron, you also have a sort of Slater in Rij, okay? And it's telling you that the derivative is a half, okay? So it's increasing, okay? So it's actually it has actually this type of shape. Okay, so it has also like a finite derivative, and it's pushing the electrons apart. Okay, and now what we are doing here, I'm sorry, maybe here I went a bit fast indeed, although you caught it. So I'm writing down the simplest possible just. Okay, and is an exponential. That's what you're going to use. You're having B0, which can be a half, but if they're in a triple, I'm not going to prove it, is a quarter, okay? So it's a half for up, down, and a quarter for up, up, and down, down, okay? Now, if you expand it, you can see they are having a finite derivative if Rij is small, okay? So it's constant 1 plus B0 Rij, because we can neglect the denominator for Rij, which is small, okay? So you're having your finite derivative, and you're imposing the Kac condition, and you're also keeping your electrons apart. The person who had asked to re-explain it, did he understand it? He or she understand it? No. Yes? There's a sound problem. Oh God. Okay, no, I cannot. Okay, very good. Very nice explained. Okay, fine. Thank you. You got it. The other person didn't get it. We can do the maybe in the afternoon. The person who didn't get it, ask me, and I go through while we do the hands-on tutorial. I can go through with this person on Zoom. Okay? But there was a sound problem only now, or for the whole hour and 20 minutes, or even, huh? Yeah, it's from his side. Okay, so you got, I'm not sure who was the person with sound problem, asked me in the afternoon, okay? He hasn't heard that. He has to, yeah. Okay, maybe you can write him in the chat, I explain it to him. Thank you. Good. Other questions? Can remotely log in for exercises? Yes, of course. Oh God. Of course. Well, okay. So people in the chat should have an access to the Slovakian cluster. So yes, the answer is yes. We tell you how later. Okay. So there was a question on Cs, okay? So, I mean, some people, for instance, I think Victor uses, was mentioning, people can also use MD, okay, a molecular dynamics, you can also use it to sample space and to do averages. And there also, of course, you want to move fast, okay? There are many situations where you're sampling and you want to move, okay? So, and of course, you know, if you move too crazily, you will reject a lot, and it's bad. Okay, so there is so there is always a compromise, okay, between having a large delta or a large tau if you're having a Gaussian from which you're sampling, and having a small correlation time. Okay, so and is also related to the acceptance. Okay, so if you accept, if the move is too small, you accept a lot, but you don't move, and therefore your correlation time or your local energy are all the same. You have a large move, maybe you reject a lot, and your local energy, yes, are different if you eventually move, but it might take a long time to move anyhow, so your correlation time is high. Is it clear? Okay. Other questions?
To MD, is it ergodic? So can you run MD on this, or I don't know. You said you could do
no, I just no. No. So I'm talking about the fact that some people use molecular dynamics. Okay, so if you are in classical simulations, you can do Monte Carlo, but you can also do molecular dynamics. Okay, and okay, you might want to do molecular dynamics because you're actually looking at something which is happening to your system, or you can just do it for the sake of sampling and you compute averages. Okay, and even there, your moves are correlated naturally. I mean, so what I'm saying, this problem of correlation also happens in classical sampling approaches. Okay, that's all what I was saying. This was just a comparison. So, other questions? Oh God, I don't have a lot of experience. I think maybe MC maybe it correlates faster if you have a good transition matrix, but depends on this. I don't know. I'm not sure. Usually, the few times, okay, I'm not really a classical person, but let's say a few times I use MD to do averages for a bio thing, because you have a reasonable way of moving, which is Newton's equation. If your system, if you have spins, then you do Monte Carlo. I think it's just that Newton equation brings you in reasonable part of space, but you can also do Langevin equation to sample a distribution, which is a Newton equation a bit modified. Let's say, okay, you can do different things. But let's say what we are doing here, we are really computing an integral using Monte Carlo techniques. Is that clear? Okay, good guys. The back. Don't be shy. No? Okay. Good. Okay, so transition matrix. Okay, so somebody wants more on the transition matrix. Okay, so the point is, okay, so the point is the following. Okay, so we are creating this Markov chain, okay? And so P is the wave function squared, okay? So it's a bit different than, some of you do DFT or quantum chemistry, then you don't really ever see the wave function, okay? Well, you kind of see it, but here we are really computing the wave function squared in all points, okay? And we need to move, in a way that we are sampling psi squared. And so that's the way we are choosing M. And I said, and here I agree, I told you to trust me, but we are imposing little balance, and M must be chosen so that, given P, you're satisfying. I'm sorry, I'm pointing at the wrong screen. You're satisfied this guy, okay? And now the best way to do it is to actually choose a transition matrix, okay? And so that's what you're splitting. You're somewhere in space, and now you say, fine, now I move my electron. Okay, I move my electron, and as I said, I can use a box around each electron and move each of them. Okay, and that's a transition probability, but then you will not be satisfying little balance because it's something I choose. Okay, and therefore that's where you say, fine, T is, if I choose a T, like a box, you will not be satisfying this equation here in the box. Okay, where there is the little hand. Okay, so now you choose T, that's the best you can do. P is given, so wave function squared, which I keep computing every time. And now let's say you say, I choose T, I choose the best I can. It could be drift diffusion, it could be a box if computing the gradient is too costly, or I don't know how to do it because I'm I don't know, or I'm too lazy, okay? But then you introduce an acceptance, and the acceptance, you introduce it in a way that this one is actually satisfied, okay? And so you're getting to this equation where you compute on this side, everything is known. The wave function is known, and t is known because you have chosen it, okay? And the other side, you're choosing it so that the ratio is equal to that, and you do so in Metropolis. And agree here, I also told you to trust me to get the minimum. Okay, your acceptance got to be less than 1, okay, to be the minimum between 1 and that object, okay. And so you're moving your electron in space. Every time you compute p, t is something you chose. In this very simple example is actually 1 over the volume, okay, is uniform. Is a uniform distribution, so it cancels, and I have the ratio, so I can just compute, you know, what is my wave function squared initially, what is the final, and for sure, if I go somewhere where my wave function squared is greater than 1, I'm gonna set, because it's a good place to go, okay, because I'm going somewhere where psi squared is greater. Did guys, is that okay? So did I answer the person in the chat? Yes, very good. Other questions? Good, I keep going. Good. Now, the big problem is that, of course, you've chosen a wave function. Okay, you've chosen a wave function, you've done maybe the best calculation you could, you did DFT, you got out your determinant, you placed a Jastrow factor, you impose the Cas condition, you maybe, like we discussed, you add some polynomials to make it, to give a bit more swing to the Jastrow, and then you have it. And is arbitrarily orbital good? Is one determinant enough? Okay, so you have a bias. What you put in comes out. Okay, and so to remove the bias, at least partially, we use what we call projection methods, okay? So what I'm showing here is some old calculation by Kwon, Sepperly, and Martin. So this is a three-dimensional electron gas, okay? So what they did is they're plotting it as a function of the variance. So you have a wave function, you have an energy, but you also have a variance. You can compute it. You know how bad is, how large are the fluctuation of my local energy for the given wave function. Okay. And then what they did is they said, okay, fine. I start from a just translator, JS, and I'm up there. Okay, so that's a three-dimensional electron gas. Then you say, it is a very simple Jastrow factor, and now I put in three bodies. So some polynomials where I have electron, electron, electron correlation. Okay, so it's good, you know, I'm going beyond the Cas conditions. I'm putting in auto stuff, and your energy, the variational energy goes down, your variance goes down. Okay, you're very close. This is a very, how can I say, they're already good wave function. Okay, you're very close to the zero variance. If you have an eigenstate, you have zero variance. Okay. And now they said, okay, fine. Now I put on backflows. Backflows means that you take your determinant and you insert a dependence on the Rij, so electron-electron distances, directly inside the determinant in your orbitals. Okay, so it becomes a more complicated wave function, okay, which is physically motivated. Okay, and boom, you know, they go down in energy and they go down in variance. And then they say, well, fine, I take a just translator backflow, and now I put a three body on the just. And you can see that, you know, your VNC, what you gain, you start to be less, okay? And of course, you can go on and on and on, but, you know, and what you can do is you can actually extrapolate. Both of them are extensive quantities. You can try to extrapolate, and you will extrapolate here, okay? Now on the same plot, so forget is, I place it in 0, I should have placed it maybe somewhere else. On the same plot, I'm plotting some diffusion Monte Carlo. Ivan already explained it, well, it touched on it. So what is being done here is this wave function is being taken, and it's being done at DMC on it. And your energy drops immediately from here to here. And then here what they did is they took this wave function, which is the best they could do, a variational level. That's the best they could do. You know, they decided to stop. They were tired. They were playing. Too much noise in the background. Okay, now we're all chatting and discussing whether there is or there is no background noise. So now everybody's silent. Can you tell us if there is background noise? Well, I am talking, but somebody beyond besides me. Aha, on the Zoom. Got it. Thank you. Sorry. Okay, so now, so what we are doing here is not really zero variance, okay? What we are doing here is, what they are doing here is taking the wave function, the worst wave function, and go down here in energy. You're taking the best wave function, they end up here in energy, okay? Actually happens to be on the extrapolation, okay? So the point is you do the best you can at the variational level, and then eventually you do a diffusion Monte Carlo, which is a projection method. I'll come in a second to explain what it is. Okay, so why going beyond VNC? As I said, you know, what goes in comes out. You have a bad wave function, you will have a bad solution, you know? And so what we do is we do projection, and what I cover here is diffusion Monte Carlo. And we construct an operator which is a function of the Hamiltonian, okay? And in diffusion Monte Carlo, we are choosing the exponential of minus tau h, and we shift it by a constant. Anyhow, it's the energy, who cares? We can always shift, okay? And I will explain in a second why we are actually shifting, okay? Now, this one you can say that there's a minus, so the energies which are higher, okay, will die faster, okay? So you're kind of inverting the spectrum. The high energy will die, the low energy will survive. You're doing a power method, okay? I'm not sure maybe if some of you have seen it in other, to solve an eigenvalue problem, okay? Maybe you have seen it in numerical methods, okay, some of you. But let's say we're doing this power method in a stochastic manner. Again, that's where the Monte Carlo comes in. Okay, so now what you're doing is, okay, at the moment you're doing it mathematically, okay? We are doing mathematically, and of course we are not going to do it mathematically, but let's see what's happening, okay? So you are at step n-1, okay? And you go to step n, and you apply the operator a to the minus tau, h minus ref, okay? Now you're doing it many, many times, so you start from 0, you apply n times, and you go to psi n. Everybody okay? Okay, so psi 0 is my variation of Monte Carlo, okay? Wave function, where I work very hard. But now, again, this is theoretical. Let's assume that we are expanding psi 0 on the eigenstates psi I of the Hamiltonian. Okay, so it's all a thought experiment. If you could do it, we wouldn't be here talking, okay? So let's assume that psi 0 I expand. Okay, so psi I are the eigenstate with energy EI, and this is the coefficient, your CI coefficient, okay? So how large is the component psi I in psi 0, okay? So we are doing a thought experiment, okay? Now you're having this operator, and the operator depends on the Hamiltonian, okay? Now, if you have a function of the Hamiltonian, this guy will come here, go through the sum, and will encounter an eigenstage. Okay, the function of the operator acting on the eigenstage is the function of the eigenvalue multiplied by the eigenstate. Have you guys seen it in quantum mechanics? Okay, so here I have the operator, but here I have the eigenvalue. Okay, so of course, you know, okay, so have you seen it, guys? Good. See some. So just if you are a bit confused, just think. You take H, you apply to psi I, you get the energy times psi I. You take H squared, you get the energy squared. You get H cube, energy eigenvalue cube. You can do it for every polynomial, and therefore the exponential you can just write it as a summation over x to the n, blah blah blah, and you're gonna get it. Okay, so okay, that's a bit of a. So by induction is true for every polynomial order, and therefore is also true for an exponential. Okay, so if you have a function of an operator, the physicists, let's assume the function is reasonable. Okay, a function, an operator acting on the eigenstage is the function of the eigenvalue times the eigenstage. All right, and therefore you end up with this exponential. And now what you do is you send n to infinity. Okay, and therefore, because the EI greater than 0, so the excited stage higher, they will die much faster. Okay? The Hamiltonian is an operator, is a matrix. The Hamiltonian is not an outlet. Okay, so here we are the operator. Okay, so okay, so the Hamiltonian is an operator. Usually we are okay. You're used to write down the Schrödinger equation, and most of the time you're using as your basis real space. Okay, you can think of your bases are a lot of delta functions. Okay, is a lot of bases. Okay, and that's what you're doing when you're writing down the Schrödinger equation. Okay, so but now here you're still in a formal way. Okay, but you can think it also as a matrix if you indeed over these delta functions. Or you choose a different basis to express your Hamiltonian, okay? But here we are writing it as just an operator, okay? But so it's just a formal manipulation of the application. We get that in a, okay, so it's just a formal manipulation of an operator acting on its own eigenstates. Are people okay with it? Okay, so now to answer your question, you will wait for me to get into real space, okay? So now the energies are all higher than the ground state, so they die faster. And if we can neglect them because they're already dead, okay? So as n goes to infinity, you're having that this guy is the one which is surviving, meaning I'm assuming that, you know, my original wave function has some overlap with the ground state wave function. Okay, which is not unreasonable. I start from a B3 determinant times a Jastrow. I mean, God, I mean, I'm doing the ground state of I don't know, benzene. Hopefully, has some overlap with the B3 determinant. Otherwise, it means that the B3 is off. Okay, so so I'm assuming that this guy has some overlap, and now you can see what is the role of the shift. The shift is such that if, you know, I'm doing this application, and let's assume that as I go, I'm actually estimating the energy. Okay, so if I can estimate somehow the energy and set it equal to E naught, I'm actually can control the the magnitude of this exponential and avoid, you know, that the norm goes to 0. Okay, and therefore in the limit of n that goes to infinity, my psi n goes to psi 0. Everybody okay with the formal derivation? Of course, we can do much with it, okay? Because we don't know the eigenstate, otherwise we will be done. Clear? Okay. Okay, so now we go from this generic expression. So we go from psi n minus 1 to psi n via tau, that operator. But, you know, so we got to choose a basis. And we're going to real space. As I said, we do real space QMC, okay? And therefore, what you are doing, you are going from time t to times t plus tau. Now your wave function at times t is a wave function of R. Okay, I'm introducing the delta functions now, basis, okay, the real space basis. And between R and R prime, I will have sandwich the operator between these delta function, which brings me from R to R prime. And because you can view it as a matrix over this delta function, in reality is an integral over all possible R. Okay, so I chose a basis and I went from a, let's say, general representation in terms of eigenstates and eigenstates and an operator to an expression which is in real space. Okay, and you can see. So is everybody okay? At least, you know, can you feel it? And we can also prove it with the Brian catch and the identities. I don't know. Are you guys? Do you believe it? Okay, good. Very good. So is the same. I go from t to t plus tau. I use the operator, but I chosen a basis. Okay. And now the question is, okay. Oh my God, it's an integral. It's an integral. Yeah. Vj. G also depends on EREF. If EREF is constant, who cares, okay? Because you're shifting your energy. The problem is we're going to change EREF, so as part of what we call the population control bias, okay? But, okay, so, indeed, in your code, you will give an EREF, which you have done the VNC, you roughly know what your energy is. You can put in your variational energy or maybe a bit below, and then it will be adjusted during your run, okay? Because at the beginning you have no idea where your energy is, and eventually you start to discover it, and you're going to change the EREF. But then it means that you're doing something which is not quite legal on your green function, okay? But there are ways to estimate how large the error is, okay? And that's a bit more advanced, but let's say fine. But now let's get to that, okay? So now the beauty of this is I have expressed everything as an integral. Integrals, we know how to do, you know? So I mean, I hope by now you're convinced you can do integrals with Monte Carlo, okay? So now there are two aspects though. I must be able to sample the wave function psi, and therefore it would be handy if psi were greater than 0. It would be very handy, but we are having fermions, okay? So psi is not greater than 0. So for the moment we do bosons. Okay, so the ground state of bosons is positive, and then we worry about the fermionic sign problem later. So one thing at a time. Okay, so let's assume that psi is positive. Okay, so we're going to the bosonic ground state. Okay, so and now the question is, can I actually view really things as something where I keep applying G and G brings me through space? Okay, so can I interpret a G from R to R prime tau as a transition probability? Before what you had, you were given, okay, so I do it in a second. So, okay, so here, indeed. So, okay, so the VNC and DNC are related, but very different at the same time, okay? So in variational Monte Carlo, you are given the wave function, okay? You have done your B-slip, you multiply by adjusted factor, you have psi. You don't care about the denominator because you're doing metropolis, but you're happy. P of R, so you can compute your Slater determinant, your B-slip determinant for every configuration of the electrons, okay, as they move around. Everybody okay with this? I can always compute it. I compute all the orbitals on where the electrons are, and I get my P of R, okay? And what you're doing is you're constructing M. M, we did it as a product of T and the acceptance. You construct M so that if I start from a distribution which is not P of R, so I place down the electrons randomly, uniformly in a box around each of your atoms, by keeping applying M, I'm going to get out P. Okay, you do so by imposing the stationarity condition, actually by imposing detail balance, which is stronger. Okay, guys? Good? That's what we did in the first part. So P is given, M you choose, but you choose so that, independently of where you start, you're going to actually compute. You're going to have a bunch of snapshots of all your electrons, which are distributed according to P of R. Now here is vice versa. Okay, the matrix time is given. That's G. That is the imaginary time propagator. Okay, but who cares? We don't need to give it a name. It's this thing here. Okay, so it's a sandwich between R and R prime of this operator, and that's given. Okay, and what you don't know is P. But what you do is that you place down your electron according to psi of R. You can sample, well, you place them down somehow. And what you want is that if I keep using G many times, there's a tau here which I neglected, otherwise was not fitting in the line. I apply G many times, and I end up with psi naught. Okay, so the situation is opposite. In one case, you have, let's say, P, and here, but you don't have, and you construct M. Here you're having M, and you get P out. Everybody okay with this? And but they are both power methods, meaning you are finding the dominant eigenvalue in eigenstate of a given matrix. In one case, the matrix is given. In the other case, you construct it. Okay? Okay, so this last part maybe is a bit lost on some people, but okay. But is it clear the similarity and opposite nature of the two? Okay. Now you say, okay, fine, I have this green function, this object, this matrix, which brings me through space and which I will keep applying stochastically. Let's see how I do it. And but to have a feeling of how to write down G, let's write down something where we know with the Schrödinger equation. Okay, so G actually, if you take G actually, if you take a derivative, okay, you're going to get H minus E will come down. So take a derivative with respect to t time, let's assume a tau. Okay, so you get H minus E ref with a minus sign. Okay, you kind of can relate to the fact that G will satisfy a somewhat modified Schrödinger equation. There is no I, no imaginary component, and there is minus d in dt. Okay, so you can kind of believe it. I take the derivative, the guy comes out down, okay, and then I can rewrite it in this way. Okay, so now we are fully in real space. This is what you're used to. This is a Hamiltonian with a Laplacian, okay? And then, of course, if I set t equal to 0, I have the two delta function in R prime, and they have to be equal. Okay, so I have delta R minus R prime. Okay, that's the condition on G. Okay. Now, so if you understand the behavior of this equation, so how G behaves, we can, of course, also understand, how the distribution psi is actually evolving, because psi just taken G from R0 to R for an infinite sufficient time. I can view it as I keep applying, I keep doing a lot of integration, or I do one integration with a very long time. It's the same, okay? Because we're having the exact one here. And now you're having that the psi indeed satisfies the imaginary time Schrödinger equation, okay? So if you're again bothered by this, it's very simple. Take the derivative, imagine you get an H minus E ref out, do some magic with your delta functions, okay? And you get H minus E ref acting on G, and what you've done dg in dt with a minus sign. That much you can believe me, okay? Good? Victor, good? Okay. Okay. Now, okay, so fine. So we know the equation, and look at that. I have the Laplacian now here. Just write it down all in real space like you're used. But now, I still, okay, fine, I have the equation, but I get back to a complicated equation. Is the Hamiltonian, and there is a d in dt. How on earth am I going to solve it? Okay, so let's simplify. Okay, so the first thing is to say, fine, let's assume I have no potential. Okay, so the Hamiltonian is kinetic. I have 3 electrons. Well, actually, I have 3 bosons. I'm still assuming that psi is positive. I have 3 bosons. Okay, so they're helium-4 and they don't interact. Okay, no as this potential. They don't interact. They're happy. Okay, so they're all there. These bosons, and they only have kinetic. Now you write down the equation I had on the previous page, which is the equation in the green box. Okay. And now, fine, here for simplicity, I remove the ref. I can always shift it later. I worry about that later, about shifting or whatever. But what I have is I have minus a half Laplacian and minus on the other side, okay? So that's a diffusion equation. You multiply by minus both of them, you go back to some fluids. If you've done some course in fluids, that's a diffusion equation, okay? And the solution is a Gaussian. Now here I'm asking you to believe me, and otherwise you try by yourself to differentiate and double check that it actually satisfies the equation, okay? And that's fantastic because a Gaussian is positive, and moreover, I can sample it, okay? Being in R, I can sample a Gaussian. There are, in Python, you can call probably some predefined, how can I say, a function to do it. In Fortran probably as well, but you can also just write down an algorithm which samples numbers according to a Gaussian, okay? It's called the box Muller algorithm. So again, believe me a bitch, but okay, so fine, but we're happy, okay? So what we're doing is, we said we have psi, we keep applying G, okay? Psi, we took it positive for the moment, bosons, otherwise we can sample it, okay? And now we are seeing whether we can interpret G as something which brings me through space, okay? And a Gaussian is doing that, we're happy. So if you're having non-interacting bosons, we are in shape, okay? Now you say, fine, now we do the other one. You say, let's assume I can do whatever I want, that I don't have kinetic energy, okay, but I have potential energy only. So I'm playing with the equation to figure out how G looks like, okay? So I have only potential, it flew away, I can do it, I'm doing mathematics, I can do whatever I want, and you kind of believe me that if I have dg in dt, and I have this object, that's gonna be, the solution will be an exponential of what is on that side. Okay, so I end up with an exponential minus t, v of r minus e ref. That's where I put it back my reference energy. And then there is a delta function because the potential is diagonal in space. Okay, but if it bothers you, the delta function, neglect it. Okay, the important thing is that you see that these are exponential. Okay, so we're having, if kinetic only, Gaussian. If you're having potential only, exponential. Okay, exponential is nice, it's positive. Okay, so it's good, let's check, okay? Of course, exponential does not preserve normalization, okay? So you can view it as an additional factor by which we multiply the distribution psi of RT, okay? So having a diffusion plus a weight. It's positive, they don't change sign, the bosons remain bosons, okay? Remain positive. I start from psi at t equal to 0 positive, I keep going, keeps being positive, thank God, okay? And, but now we need to put everything together. So because generally speaking, you're having a kinetic and you're having a potential, okay? And then you say, well, you know, I try and I write it as a product. Okay, so I'm gonna write a diffusion multiplied by something which will tell me whether that's a group part of space or not. So is my potential much higher than my reference energy? For instance, my reference energy started to be the variation of Monte Carlo energy and then improves as I move it. As my distribution becomes lower and lower in energy, ERF will be updated. But for the moment, let's assume you start from your VNC. If the potential is much higher, that's not a good place in space. You can think about the harmonic oscillator, which I'm also going to show that Ivan showed you. If you are having some walkers where the potential is skyrocketing to plus infinity, you don't want to be, you know, your distribution should die, okay? And instead, you know, if you are, you know, below, you say, well, that's great, you know, my exponential is, I'm going to get lots of children, okay? So you clone your walkers, okay? So that's a diffusion process with a reweight. And the reweight tells you, should you die or should you survive? And maybe you should also clone yourself. If this guy is much, if I get a 10, maybe it's a very good place to be, but then what do? You can keep the weight, or you can say, fine, I generate more walkers from the walker I have, like Ivan was showing, okay? Now, we got to see is a bit hand waving, okay? But let's say in reality, you can also do it mathematically and say, if I have an exponential, the sum of two operators, I can actually split it as an exponential of operator A and exponential operator B. One is the kinetic, the other one is the potential. Okay? So, questions? Well, that's a very good question. Let me answer him. So what am I doing here? As I said, you know, I am splitting it. I was about to get there, but there is an order tau square, okay? So that's not exact. I mean, the operator is exponential of the sum. It's not the product of two exponentials of two operators. It's only valid if tau is small, okay? So now, so we used our intuition, we put kinetic, we put potential, we combine them. I'm telling you, you can go mathematically. But mathematically, as was asked, you're having also this order tau square. So it's a short time approximation of the green function. Okay, so because the green function is more complicated than that. Andrew in the back, you're puzzled. Okay, diffusion, you're happy. Very good. Now, okay, I know that the problem is there is R and R, there is a 0 and R, but you agree that you see that if you're having a minus d in dt equal to d in dt of a function, something times a function is the exponential of minus tau VR. You get that, okay? So that's intuitive. It is a delta function because we're dealing with operators, and the potential is diagonal in space, okay? So we can do it a bit better, okay? But let's say for the moment, let's say view it like that, and view it like that, and then here you put them together, okay? So you start from R, you go to R prime, and okay, so you can branch, so you can use your reweight to say, am I in a good position or not? And then you diffuse, and then you keep doing the reweight, and then you diffuse, and then you do your reweight, and you diffuse. Okay, that's the way you're going to do it. Now, what I'm doing here is just mathematically showing that, you know, the exponential of a sum can be written as like that, but is an approximate writing. It's not an equal. It's not really an equal. There is an order, tau squared. Okay, but now we're going back to our interpretation of doing the pieces separately and putting them together. So mathematically, what you would do then, to write your green function, you could write, you know, R and R prime, you know, Brian catch, put an identity in between, use what you have in the previous pages, and get out your green function. Okay, at the moment we have done it a bit waving our hands. Is it clearer? That's very good. That's very good. The higher order depends on the commutation properties of the two operators. So there's going to be commutations of A and B, and then commutation of A and B with A. So all the higher order will be a combination of commutations of A, B with A with B, and then you go on to higher order. Very good point. Indeed, they don't commute. That's a problem. They don't commute, and so you're having higher order, but in the limit of tau that goes to 0, that's okay. Okay? So what we're getting a short time approximation of the green function. At least, do you have a feeling? Good? Okay, so, but that means, like was pointed out by VJ in the first part of the first talk. So I do a diffusion Monte Carlo. Here is just some old paper by Cyrus Umrigan, and he's looking at different whatever algorithm. He's taking a wave function, and you have to extrapolate for the time step, which goes to 0. Okay? So you need to do more than one diffusion Monte Carlo calculation. Then there are some properties which are depending less. For instance, if you do excited state, you're having, you know, the same system, and you have a very good cancellation also for large time step. Because let's recall that you're having a diffusion with tau. Actually, talking about it, having the diffusion with tau. Remember that we did the variation of Monte Carlo. We also could use a diffusion to move, and tau was, you would like tau to be big because I move a lot, okay? But then you have a time step error. because you're approximating your green function. And the smaller tau, the more correlated your move will become, but you have no choice. You've got to go to tau that goes to 0. And as tau goes to 0, the more expensive your simulation will become, because you must do more Monte Carlo steps. Is that clear? Okay. So the basic algorithm, here we are having just the wave function, because we're having bosons, okay? So you do a metropolis, so P of R is psi 0 of R, okay? So you do metropolis not on psi square, on psi 0. You can do it on whatever you want metropolis, okay? Whatever distribution you give me. And then you generate a bunch of walkers. So it means that you throw out your electrons, and you get m naught of them. So that's your zeroth generation. Okay, so you do a metropolis on psi 0, and then you need to apply the algorithm. And the algorithm, we said, is a diffusion times a reweight. Okay, so you diffuse each walker. So you go from R to R prime by sampling psi from a Gaussian. So it's a Gaussian distributed object. And then for each walker, you compute P. And then P, if it is very small, you might have that your walker is not really a good walker to keep carrying around if you have a 10 to minus 12 as P, you know. But if you're having a P equal to 10, my God, you know, maybe you will do that, you will generate something of the order of 10 walkers. Okay, and you will have to adjust ERF as you go to make sure you don't end up with 0 walker or 1,000,000 walkers, because that would be very inconvenient. Or your computer will die the simulation. Okay, all of a sudden you have an explosion of walkers, everything will die. Do people have questions on that? Okay. So P tells you, is this good or is this bad? Okay, so it's something you add to your wage. So you have a wage. So you start all the walkers at weight 1, and then they get multiplied by this P. If P is very small, your weight or your walker will go down. If P is very large, oh my God, that's a good, you know, let's proliferate. Let's make a lot of children. Okay, there. But of course, you don't want to do it uncontrolled. And so there are various tricks we use to keep that. If you're having, okay, you can even run, I think TurboRVB actually runs with a finite, with a fixed population size, while we have a fluctuating population size. But we make sure that if you start from 100, you go to 120, 90, 80, but you don't go to 0 and 1,000,000. Okay, so you adjust the ref, and maybe also you make sure that the sum of the weights of the walker is always not too far away from your target, 100. Okay, so there are some tricks we must play. Everybody okay with this? Okay, so ERF got to be adjusted, because we know even mathematically that if your ERF is too high, you got to go down to what is your ground stage. Everybody clear with that? You got to keep the norm under control, because otherwise also your ground stage component will die. Okay? Good, guys? Now, after many, many iterations, your walkers will be distributed according to psi 0. So you get your bosonic ground stage. Okay? Now, okay, so this is what Ivan showed. So that's a bosonic system, because you only have one particle, so more bosonic than that it doesn't get. Okay, so one particle is in you start, you know, by sampling uniformly, so that's not a good start. And eventually, what is for a very large V compared to your initial ref will die. The one in between, instead, they're more happy, and they will generate, you know, this guy generates 2 children, whatever. Also here, he generates more, and they move around, and eventually you're going to have fewer walkers here and more walkers here. Okay, and so you proliferate or you die depending on whether your potential is lower or higher than your F. Okay, does it make more sense now what Ivan showed, or some questions? As I keep going, guys. No question? I keep going. Eh? Dangerous. Let me see the chart. Nothing. Very good. Okay, there is a problem though with a simple algorithm. This is inefficient and unstable. Something like God. Inefficient and unstable. Why? because I have an exponential of minus tau v. The potential diverges if two electrons comes too close to plus infinity. If it comes close to a nucleus, it diverges to minus infinity. So I'm going to get some amazing kicks in the weights of my walkers. They all die. One of them will generate I don't know how many children. It will be extremely hard to keep a stable simulation. Okay. Moreover, the potential is an extensive quantity. Okay. So as my system grows, also this guy will grow. Their fluctuations will grow, generally speaking, even if you were not to have any, which you will have, but even if you, yeah, so you have a problem, okay? So you have so the V can jump to plus infinity, minus infinity, and is in general larger and larger with increasing system size, okay? So we cannot use it. Okay, we cannot use it, but now you go back and you say, yeah, but look, I mean, I spend a month to get a good wave function in variation of Monte Carlo by trying out all sorts of wave function, optimization, and everything. And now I move to diffusion Monte Carlo and I use absolutely no information on my wave function. That's not smart. So it would be nice to put back some information on your wave function because it tells you where the walkers should preferably be and where they shouldn't be. Okay, plus, the wave function with the Jastrow factor will satisfy the Cas condition. So you can imagine that I'm going to get to something better. So let's do it, okay? So now, okay, so we started from G. G was given. G was the sandwich of a to the minus tau h. Okay, there's a shift in the energy, but we don't worry, between R and R prime. Okay, we splitted it, kinetic and potential, diffusion, reweighting, and we were going with it. But now you say, fine, let's do that. We multiply each side by the psi trial. So I've done a lot of work on my VNC. Psi trial is your VNC wave function, is your bit lead determinant times a Jastrow factor. Okay? So what I do is I multiply the left by psi trial over prime. So I have it here. Psi trial over prime. Now here I want to have pi, which is not which is I think I even called it F, okay, to keep the notation the same, which is psi trial whatever I'm evolving. So here I will have to multiply and divide by psi trial of R. Everybody okay with this? So I multiply by both sides by psi trial over prime, and here I divided by psi trial of R and multiply by psi trial of R, so that I end up with pi on both sides. Okay, so I have pi here, but now I have something different. I have a G tilde. Okay, I have a G tilde which contains mathematically psi trial over prime divided psi trial of R. So I must approximate something which is a bit different. Okay, but now mathematically I've done nothing. In the limit of very large n, what will happen is that the pi will end up being the trial wave function times your psi naught. Okay? So I'm still doing bosons for the moment, okay? But now, even for bosons, that's not a good green function. So I've done some variation of Monte Carlo for my helium-4, and I'm going to use the wave function. Okay? Good? But mathematically, I've done nothing. So the limit, as I keep projecting, as I go, I start from my psi trial, and then I keep going, will be psi trial times psi naught. Everybody okay with this? Good, huh? Good? Okay. Sure? Good. You're cold? Yeah, I'm actually moving a lot, and I'm doing kilometers and kilometers here, yeah. Okay, so now, there are various ways to get to this, okay? You could try to do Trotter here, and then start to assume the R and R prime are not very different, try to write it as the exponential logarithm. You could do some manipulation at this level, but maybe the simplest way is to just write down what is the imaginary time for this guy, okay? So So you just write what is delta G tilde and delta tau. And what you will get again an imaginary time evolution. Okay? So for the moment, let's neglect all of these terms, but you see you get your Laplacian, you have minus the G tilde and delta tau. It looks like a Schrödinger equation, of course, in imaginary time. Okay? But now I have that if you do all the manipulation, the mathematical manipulation, you no longer have the potential, but you have the local energy. Oh, that's nice. Okay. And then I have this object, which is gradient dotted into G tilde, and V is the quantum velocity. And we like those because they contain information about your wave function. Okay. So why do we like them? Well, since V pushes me towards large region of psi. So if my bosons were to stay in some positions, they're gonna go there, okay? And the local energy is much better because the trial wave function satisfies the Cas condition, for instance. It does no longer diverges when two particles get close to each other. Okay, so remember that in variation of Monte Carlo, we wrote it as we introduced a Jastrow factor to make sure that the divergences of the potential are cancelled by the divergences of the kinetic energy. So H psi over psi, when two particles get close to each other, will be finite. Will not be. It will be still, you know, so you still don't have an eigenstate, but at least you don't have divergences. Okay? Is that clear? Is it clear that having the local energy is better than having the potential? The two guys over there, is it clear? No, but don't really seriously, if it's not you got to say it. You clear? Yeah. Okay, what is, I don't know if it is a true yeah or is an intimidated, extorted yeah, but okay, so the point is, okay, you're still having that the local energy is extensive, okay? And that you haven't cured. Of course, actually, Saverio Moroni looked into it. This is more severe for actually bosons. For fermions, we're gonna get to fermions in a moment, usually our wave function are good enough that we don't see a drastic deterioration of the algorithm as the system becomes larger. Okay, because you might still say, well, yeah, fine, but locally, if I make the system larger, the fluctuation will become larger, which is true. But it's still under control, okay, for pretty large sizes. Okay? So now what we do is we do the same game as before, okay? You do Trotter's theorem, but let's say we can do it a bit like that, okay? You can say, first I consider the Laplacian diffusion. Then I consider this term. That's gonna give me an exponential, but now there is not gonna be the potential there, but the local energy, okay? And now the one in between is a bit more hard to see, but that's something which pushes your electron where the wave function is large, okay? And now here, yes, I know you have to believe me. Sorry, Anthony, but you know, if you do everything, I'm here, you skip lunch. So I don't know, it's a, but we can discuss it in more detail. So, okay, so I'm kind of giving you an intuitive thing so that, you know, you still, now you have 3 terms instead of 2, okay? The first one diffusion, last one REH, but now with a local energy, not with a potential, much better, much better. Particles close to each other, local energy fine, a potential diverges instead, okay? So much more stable algorithm. And now the term in between tells you that if you're starting somewhere, you first go where the quantum velocity pushes you, so the gradient of the wave function divided by the wave function. So it's a drift diffusion. That's the reason why also we are using that T in variation of Monte Carlo. So often variational and diffusion Monte Carlo share the T part, okay? So the first part, but then you're having again your REH, and you're having your local energy, and your reference, this object which you shift, okay? So as I already said, it is much better. VR pushes you where the wave function is large, You satisfy the Cass condition, so you don't have a potential which goes to plus and minus infinity, but you have something which is finite, okay? And also what you can show is that if the trial wave function becomes better and better and better and better, okay, the local energy becomes constant. And then I have no longer a rewage. So essentially I'm doing a variation of Monte Carlo with a time step error, okay? And I would need to send tau that goes to 0. But then there are tricks we do, okay? Everybody okay with this? This was a lot of hand waving and a bit of, how can I say, feeling, but did you guys get the feeling? Danny, do you get the feeling? Yeah? Means, but okay, so the first part where you had drift and rewage was clear. And it's clear to you the potential is not good. Because the two electrons goes to each other, plus infinity, electrons on a nucleus, minus infinity. Clear? Not good. Simulation unstable. Okay? And then you say, what you say is mathematically, you say, I don't want to work with the first equation, and I try to introduce what we call important sampling, which is we try to push back in our equation some information about the trial wave function. So we don't sample only psi as we evolve, but we sample psi times psi trial. Who cares? Fine, at the end of the day, you have psi trial times psi naught, but it's okay. You still have psi naught, okay? But because of having introduced it, and here I sketched some quite a lot of steps, okay, guys, you got to believe me, because I introduced it, I have that my equation now has 3 terms. 2 of them are clear. One is the kinetic diffusion, the other one is the rewage, but now I have the local energy, Cass condition, no divergences if two-particle approach. And then I have that other object, which mathematically you can see that, you know, for small time, you can end up having it as a drift. So I'm somewhere, I drift somewhere where the wave function is large, and then I do a rewage. Okay? Good, guys? Then there are more tricks, but let's say then you can, yeah. The point is, okay, if you look at papers in the literature, you can do a lot of modification on your green function to improve its time step behavior. But whatever you do as modifications, they must disappear as tau that goes to 0. Okay, so as tau that goes to 0, you know what you have. Okay, for finite tau, sometimes people do modification to make sure that your time step error is smaller. Okay, but let's say the tau that goes to 0 limit has to be what it is. Okay. Now, so now what is nice now compared to before, you're sampling psi, that's what you want to obtain. Okay, so that's what you want to project. Psi RT times psi trial. At time 0, you have only psi t twice. So it's a square. Psi trial squared. At t equal to 0, I can take as my pi psi trial squared. I did the variation of Monte Carlo. I can take that. Why not? Okay. So for t equal to 0, I just do a variation of Monte Carlo. I will know my energy, and I can also write in one file a lot of snapshots of my electrons, sampling pi at tau equal to 0, so psi trial squared. So you can just sample psi trial squared, and you can start a diffusion Monte Carlo. Okay, but as you go on, you will go from psi trial squared to psi trial, psi 0. Are people okay with it? Okay? It's okay? No, Victor, it's not okay. Okay, so no, it's not okay. I can see that. So, okay, so are we okay with the first equation? Okay, in the first equation, you have some psi of r at times t equal to 0. Okay, and then you use g of r, which is diffusion, and then you use your potential. You say, oh, good place, bad place. Okay, so let's create 10 copies of me, or let me die. Okay, or just let me survive as one, or it's 2, depends on the weight, okay? But as we saw, this reweight is pretty bad because it's exponential the potential. So the electron nucleus, you get minus infinity. So P will become 1 million. What do I do? On the computer, I create now my array, got to contain 1 million walkers. Or maybe I'm very unlucky, I get 10 to the minus 3 because I go close to a electron-electron. So I go to plus infinity, okay? And then P skyrockets, not up but down, okay? So that's not stable. So if you put in a computer, it's not stable. You're going to have your population will fluctuate humongously. And at the end of the day, you want to work with 100, 200, 1,000, maybe we usually use 100, but let's say a finite number of objects which are propagating, which at every time, after a while, will be a good realization of your ground state wave function. So, you project out, and after a while, they will be happy. There will be a good realization of your psi 0. You can start to accumulate and get your averages. And you get the exact ground state. Is that okay? So mathematically is super. In the computer is not good. Okay? Then, then what we do, you say, this is okay, fine, very clear, easy, but bad computationally. Then the point is, let's try to do some very simple manipulation of that equation. So you multiply both sides by psi trial over prime. I can do that. Okay, so I have a psi trial over prime on both sides. And then on the right-hand side, I multiply and divide by psi trial of r. So I can rewrite it as a propagation of pi. Okay? So at the end of the day, mathematically, you still end up with psi trial, psi naught. Okay? But now I have a new green function. Okay? I have a new green function with these guys here. Okay? And if you take the derivative and you do about maybe an hour of mistakes, typical, and you do all your things, you're going to get that you don't no longer, let me see, you no longer satisfy, let me go the big one. Yeah, you no longer satisfy this equation with the Laplacian and the potential, but you satisfy a slightly different equation. Okay? And the slightly different equation has several advantages. You have the Laplacian, kinetic, fine. I have the reweight, but I don't have the potential. I have the local energy. Okay? If I could guess as trial wave function, the local energy is the Hamiltonian acting on the trial wave function. So you did the VNC, and you have local energy of the trial wave function. And this guy is finite if two particles get close to each other. At least that we have, okay? The velocity, moreover, gives you a drift, okay? And if you do the same type of game we did before, so you have a diffusion, you have a reweight, you have this additional term, with some approximations, tau small, you get to this. So now you're evolving something different because you're evolving psi of t, so this object which eventually will become psi naught, your real wave, the ground state, but is always multiplied by psi trial, okay? But the green function is much better, it's much more stable as algorithm. Okay, so at t equal to 0, the best you can do is to sample psi trial squared. You got to put down your walkers. Okay, you put them down and then you start to evolve them as a drift, diffusion, as a drift. So I'm in R, I drift, I diffuse, so I generate a random number, Gaussian distributed, and then I reweight. Okay? And it's all much better behaved. Still not everything is solved when we go to fermions, but it's better behaved. A bit better feeling? Okay. So indeed, so the beginning, remember, is pi what we get. It's not really the number pi, maybe I was trying, I'm not sure why I changed from F. But I'm sampling what will become psi naught times psi trial, which is what I constructed in variation of Monte Carlo. Okay? At time equal to 0, just take psi trial squared. You don't know anything. place down a set of 100 walkers. Very good. I have 100 walkers. I have 100 realization of psi triad squared. Okay? And now I drift them. And I diffuse them by sampling a Gaussian in X, Y, and Z, all of them, all the electrons. Okay, so it's a somewhat different algorithm. I have a drift, diffusion, and then I compute, I can also symmetrize, is the time step error is smaller, I can symmetrize. Instead of computing the potential, I compute the local energy. So what we do here, always in quantum Monte Carlo, differently from whatever you do in Hartree-Fock and everything, we compute the wave function many times, guys. Okay, so so every time you compute your wave function to get your quantum velocity, the gradient of each, the Laplacian acting on each, and that's just a function of the position of the electrons. Okay, so I have electrons here, my local energy is a value, I put them there, there will be a different value. Okay, it's never going to be constant. And then you adjust your trial energy to keep a constant population. But it's going to be much easier to do than if I had the potential going to plus and minus infinity. So it's going to be easier to actually keep my population to be 100 and not to go to 1 million. Everybody okay? Easier. I'm not saying it's going to be much easier. It's much more stable. Okay? Guys, good questions? Who?
This last term in the second row, drift and diffuse the walkers.
Well, that one is a vector. So that's my 3n dimensional. So I really have the electrons. I place, you guys have the electrons. I place you down at this table. Okay. And now what I do is I compute your, so for you and you and you and you, I compute, you know, the wave function and the gradient of the wave function. Can do it. It's going to be something complicated, but the computer does it for me. And you are a 0.1 and she's much more favorable than you. And the gradient maybe pushes me towards the other side of the table. Okay, so so the gradient is a 3n dimensional gradient. Each component will have a gradient. So, and I'm pushing my electron everywhere. Okay, where maybe there the wave function is so much better. Okay, so they're going to be all, you guys are going to slowly, let's say, move on that side. Okay, and then you still have something which you're sampling. So psi is a vector. Psi is a vector. So I sample, you know, all 3n, I diffuse. So I diffuse you all. So maybe some of you are trying to go there, but some of you might diffuse a bit back, you know. You still don't want to go there, you diffuse a bit back, but, you know, so the drift is pushing you on that side. Okay, and eventually, you are somewhere, you will have moved, you know, in things, you will no longer be as ordered, okay? And for each of you, I compute the local energy, which is a function, okay, you're in 3D at least, okay, so the local energy is, you have a lot of position, is, you know, you're all in 3D and you're all my bosons, still haven't done the problem of the fermions, and I can compute the local energy, okay, which is a number, now is a number. Okay, the gradient, the quantum velocity is a gradient. So for each of you and each component of you, I have a gradient. And now the local energy is just -5. Hopefully is as close as yeah, so minus, hopefully it's not plus a lot. Okay, so if you are supposed to be minus something, so like I said, you're going to get a bunch of snapshots. And now using the local energy, you can get an estimation of your total energy. Okay, very much like in variation Monte Carlo. Is it clear? Is it better? So R is a vector, gradient is a vector, local energy is just a number, a scalar. Because it's H operator acting on psi divided by psi. Okay, so it's, okay, good. Okay. Yes, sir.
In case you point at which the number of workers can increase.
Well, okay, so in the simple algorithm is very clear. So let's assume that you're having okay, that's very clear. You are getting close to a nucleus. You go to minus infinity. Okay, so that increases. You get close to your friend, who is also, now let's think about well, okay, so it pass, no, electrostatic, doesn't matter, electrons. So you get too close to your friend, you get close to Victor, you go to plus infinity, it's gonna die. Okay, and now here, of course, look, I mean, I cured these, so we had cured the phase by having the local energy, but still you can get kicks. I mean, it's not constant, we don't have an eigenstage. If we get something which is indeed maybe 3 times adjusted, it is what it is, okay? So you will still have fluctuations. Plus, if they are fermions, so you still have a denominator because it's h psi divided by psi, and psi can go to 0 at the nodes. So you need to do some tricks, okay? So, so you solve many of your problems, is a better object to handle, is a better object than the potential alone. Moreover, if psi is very good, the local energy fluctuates little. And therefore, even though it's an extensive quantity, I have something which I can hopefully control to be less dramatically varying. Okay, let us say. Good? Sure.
So what if I start with the private function which is very far from
well, eventually you're going to get there. But you can imagine that if you're having your bosons and I don't know, you put them, you want to simulate a phase where they are, you know, you're a low density, you want to simulate a crystal, you know, well, it's not really quite a crystal, they move, you know, but something which is a Wigner-like, and you start from something which is very mixed, it might take you some time to get there. Maybe a long time to get there, okay? And vice versa, depending if you are, well, yeah, maybe, yeah, so that's how far, for us, usually, as I said, for electrons, we are having reasonable wave function. But if your wave function, for instance, doesn't have the proper symmetries, I'm never gonna get there. Okay, so if I have a p state and I try to get the ground state S, you know, the symmetry probably will be different. So yes, what you start from is important. But usually, because we're having, you know, all the, you know, we always say all the DFT people, all the quantum chemists have done a lot of work for us to give us a good wave function to start from. Okay, so so we build. You can view it as a, like you talk about a post-Hartree Fock, you can also view us as post-DFT or post-Hartree Fock, you know, post-quantum chemistry. Okay, so you don't start from scratch unless there's something tiny teeny. We're going to get there. We're going to get there. So the double potential in this language would be that you want to do an excited state, for instance. Okay, it's not quite a double potential, you know. So you want to do something which is higher than what you did the lowest one. Let's assume. Okay, yeah, if it is degenerate, of course, you're thinking about something like degenerate ground state. Yeah, you might, well, depends on what you start from, which one you start from. But let's say excited states, we get there in a second. That's also a more easier way of thinking. Okay. Other questions? So as I said, yeah, so other question on this is okay? Yeah. Oh, God. Yeah, so I've been going slower, but then I'm not going to finish, but yes. Chat, if somebody reads it, or if I touch it, it goes into, what do they ask, the chat? What? Is to handle errors, or we just doing by plotting number of walkers? No, we don't plot the number of walkers. Well, you have an average, you accumulate your average energy as you go, okay? And then you have, every walker has a weight, okay? Every walker has a weight, and you have a sum of the weights. And you would like this sum to be equal to 100, say. So you adjust the ref to the average, and then you can rescale your weights. Okay, but that gets a bit technical. Maybe that's for a first pass on DNC, because I think you guys are dying. Yeah? Thinking about lunch or something. I see Danny in the head, very soon it goes. Okay, so let's do that. We look at these as we do the exercise, the hands-on. Okay, because otherwise it gets more technical and there are lots of technicalities we cannot cover. But maybe as we see the program at work, you can see you're going to start off and you're still going to get the right energy. Okay, well, the best energy you can. So now, yeah, okay, okay. So far, DJ. Okay. All right. So far we dealt with bosons, and electrons are fermions. Okay. So you're having a wave function which is antisymmetric and changes sign. Okay. And so all fermionic Monte Carlo methods have a fermion sign problem. Okay, which appears in one way or the other. Okay. So they might look different because you could choose a different basis to work in, like if you're working in second quantization and you move in orbital space, but it's a bit the same flavor. Okay, so you're treating something which is non-positive as a probability density. Okay, I mean, at the end of the day, it's not positive. I mean, they're fermions. Okay, but now, okay, this was briefly shown by Ivan. You can say, yeah, but let's say I am smart, you know, like I'm very smart. So I want to do a fermionic problem. And the simplest fermionic problem I can do in one dimension is to do the excited state of a particle in a box. Okay, that's a fermionic problem. Okay, so I want to do the antisymmetric wave function of a particle in a box, and that's the first excited state. Let's assume that I work very hard, and because I'm not very good with math, I got this as my state. Okay, so it's symmetric, you know, it's symmetric. Actually, I guessed rightly the symmetry, but it's not quite the particle in a box. You will have like something here and something there, more like that. Okay, not so skewed on one side. Okay, but then you say fine, but you know I am smart, you know, so I'm gonna take this guy, I'm gonna flip it up. I call one psi plus minus psi minus. Okay, so plus is the red and minus is the blue, and I give it a name. I call my walker blue and I call my walker red. Okay, and I evolve them. And you say yes, and I'm gonna do it. Okay, mathematically sure you do it, but the problem is that you have to think you're doing it on a computer by evolution. And what you're using the imaginary time Schrödinger equation. Let's forget about importance sampling for a moment. Okay, so let's say you're using things. Okay, and so what you can do effectively, you can evolve them separately. Okay, you evolve them separately, you combine them. Okay, but Schrödinger equation, Hamiltonian, has no idea about plus psi and minus psi are the same solution. Okay, it doesn't care. It doesn't know that you have a plus or a minus walker. So if I keep going, what will happen to psi plus and psi minus? Where will they end up? So I place all my walkers on one side, I call them plus. Place them all on the other side, I call them minus. And now I start to do diffusion rewage. Okay, what will happen? I take the imaginary time Schrödinger equation where on one side I am evolving the blue and the red. The only difference is that some of them will be a bit on the left of the box and some of them will be more on the right of the box. Okay, but I'm evolving them. What's happening? They will spread, but they will spread and then they will go to what? No. Well, okay, you're right that, you know, so let's assume in some way always impose that they are zero at the boundary. We get that in a moment, okay? So you're right, we would do, yeah, so but let's assume that in some way, and I'm gonna tell you, I'm always imposing this is zero there at the boundary, okay? We get that in a second, okay? So somehow I do something in my evolution that I don't let them, I want them zero at the boundary, okay? But then what will happen in the middle? So, very good, they go to the ground stage. Okay, what's happening is, so let's assume I'm able to actually enforce during my object that it always stays, they represent a zero on the boundary. I get that in a second, how you do that. They both evolve to the same, for sure mathematically and also my computer, okay? But if you do mathematically, you can always extract the antisymmetric component. You just take, you keep doing it, and it's okay, you mathematically, you do it. On the computer, I have some walkers, some other walkers, and the symmetric signal will grow and grow and grow for both of them. And now you're taking a difference on a computer using walker, the blue and the red, and very soon your antisymmetric component, which has a higher energy, will be lost in noise. Okay, so I was so smart, which didn't work. All right? Do you get this? So they all start, you started it different, but they don't know. The Hamiltonian has no idea they have red and blue. And they both get the same. Then you take the difference, but you're doing it with walkers, noise. Okay? So you're swamping with noise. Okay, so now, so you're having your random errors, your antisymmetric part will be swamped. And the solution, like Ivan already introduced, is you guess the node, you fix the nodes. Okay? And it means that you guess them. Okay, here is easy to guess. You say, I put a barrier in the middle, which is impenetrable. Okay, I have my red and my red and my blue, whatever they were, but I never make them mix. Okay, well, you know, okay, and then I also got to make sure that it always becomes zero. Okay, then they will evolve in the ground state, but now in half of the box, and that's good. You will get the excitation energy. Okay, guys. So let me see. So I guess. So how do you do it? If a walker tries to cross, if a blue one tries to go on the other side, you say, you kill it. Okay. A red one tries to go on the other side, you kill it. That was and you also had to enforce the cycle to zero at the boundary. Also, you don't want them to get out of the box. Okay. And of course, you need to maybe repopulate your population. You know, adjusting the weights and everything. Otherwise, they all, okay? So, but then essentially what you're doing, you're evolving in each pocket to the ground stage. And this is numerically stable. And of course, okay, in such a situation, I write regress it by putting the boundary in the middle, okay? And so the solution is exact if the nodes are exact. Otherwise, you get the best solution consistent with the nodes you've assumed. Okay. Now, this is, and then I think we should break to lunch. So, okay, so now a particle in a box, thank you very much. We can do it analytically, okay? And now, but what are the nodes? The nodes are the zero the wave function that determine from the equation psi equal to 0. And across the nodes, the wave function changes sign. Okay, so this is from a paper by Sepperley. So he takes a two-dimensional electron gas of 161 spin-up electron. Okay, so your system is 322 dimensional. Okay, 2 times 161. Okay, so there's a lot of dimensions. Now the psi equal to 0 is one constraint. So the nodes actually have a 321 dimensional surface. So guessing it is impossible. Okay? What they did here, they do a slice. So they slice a two-dimensional slice of a 321 dimensional node surface. So it's nothing. Okay? And already this is very complicated. What do? They take the 160 electrons, they place them down. Maybe variation Monte Carlo. Choof, you put them down. And then you keep them all fixed except this guy. You start to move around, and every time he finds a 0, oh, the wave function is changing. You draw your little line, and you can see how complicated a two-dimensional slice is of a 321-dimensional surface. So I let you imagine how complicated it is, the 321 nodal surface. Okay, so yeah, so guessing it is not possible. And yeah, so as I said, you know, so if you're having d dimension, the nodes is dn minus 1, okay, because you have one constraint. And many people think about when the electron gets close to each other. It's true, you know, they can change sign. But that's this one defines a much lower dimensional surface. It defines the dn minus d dimensional coincidence. surfaces, not plane surfaces, okay? And they don't define the nodes because dm minus d is much smaller than dm minus 1. 3m minus 1 and 3m minus 3 is 3m minus 3 is just a sub part of your surface. So the place where the electron gets close to each other is only part of your nodal surface. Okay? And indeed, often you find papers where they claim to solve the fermion-Stein problem, and maybe they put themselves in d equal to 1. But in d equal to 1, meaning 1 dimensions, you have that the nodal surface and the coincident plane becomes m minus 1, m minus 1. Yeah, fine, that's easy. So you know, so when the electron gets close to each other in 1 dimension, you have the nodes. So they define fully the nodes. But if you are in 2, 3 dimensions, that's not the case. Everybody okay with this? What should we do? I break?
Yeah, we are. Yeah, it's actually 1 o'clock, so I suggest.
Very good. Okay. We break. Thank you. Okay, so so we all agree it's a complicated object, 3m minus 1 dimensional. People agree in the back it's complicated? Good enough, okay? Let me see. So now, generally speaking, the nodal pockets can be divided into classes, okay? So here what we are doing, we are having 2 electrons, x1, x2, in a segment, so they are in 1 dimension. Okay, so x1 can range over this value and x2 over that value. And of course, because you are in 1 dimension, you know the nodes, x1 equal to x2. Okay, that's a lucky case where you know everything because the particle lives in 1 dimension. Okay, but let's assume I have these nodes. How do you do it? How do you figure them out? Okay, so there are nodes which are related by permutation and nodes which are different because you are, let's say, in an excited state, for instance. Okay, so what you do is you will put down an R0. So you place your electron down. Okay, so first you place them here. Okay, so you place your R0 there, and then you start to move around. You encounter the 0, you say, oh, nodes x1 equal to x2, I know it. But then I find also the nodes downstairs. And then you permute. Okay, so the 2 of them are equivalent. You know, they got them by permutation. I permute, I get these. Okay, so this is 1 class of nodes. Okay, you can go from one to the other just by doing permutation, x1, x2. Okay, then you place down again R0, and you end up here. Okay, so you end up here, your R0 ends up here, and then you start to move around and you map out all the nodes. Okay, and then you permute. Okay, so and you're gonna get the other pocket. Okay, so this is a yellow. You have the blue and the yellow. Now you place it again, and now you end up in this region. You move around. You say, oh well, one node is shared with the previous pocket. You permute, and you're having the other place. Okay, and then eventually you put it in you put it upstairs there in the green one. You permute, and you get your other pocket. Okay, so but this is clearly not the ground state. The ground state will have x1 equal to x2. Okay, you have 2 pockets which are equivalent by permutation, the half of the box. Okay, so if the 2 particles get close to each other and they cross, the wave function changes sign. And that's the line in between, x1 equal to x2. But it is a higher stage and you're having an equivalent pocket, meaning you cannot go from one to the other just by permuting. Okay? And what you have for a ground state, you're having the so-called tiling properties. So it's provable for so if you're having, let's say, an Hamiltonian, reasonable Hamiltonian, a reasonable ground state, all pockets are in the same class. Okay, and you can think about it is okay, you start from this and now you want to lower your energy. How do you lower your energy? You remove nodes. You remove nodes between, if you remove the lower the amount of nodes you have, the lower is going to be also your energy. Okay, you smoothen it out, you know? So you flip it and maybe you smoothen out where you are the node, okay? So you can start, you know, you leave this guy as they are, and you flip these two, okay? Meaning, you know, you make sure that when you're crossing here and here, you're not changing sign, okay? So I have fewer nodes. Okay, so that's going to be, I'm reducing my energy as well. Okay, you can think, you know, in between, you smoothen or to have, you know, your Laplacian badly defined. Okay, so maybe you make it bosonic between here and here, and then you flip. Well, the other two are okay, good. So, but maybe you smoothen the nodes between here and here, and then you actually flip also the last one. Okay, and let me see, and you end up with one pocket, and the two of them are just equivalent by permutation. That's tiling property. Okay, so for a ground state, you just place down your object, you map out your pocket, you permute, and you will cover all space. It's called tiling properties. To prove it in general is a bit more complicated. Okay. So, which is nice because you don't have to worry, because you're going to place down your walker somewhere. You might wonder, oh my God, you know, I'm doing a ground state. You know, maybe I missed something out. But no, you have tiling properties. If your wave function is reasonable, your Hamiltonian is local. So, okay, let's leave it. So, generally speaking, you know, your walkers will go around, and maybe there's another walker going around. It is not the same pocket, but they are equivalent by permutation. So, who cares? Okay. But now what we do as I said, you know, so fine, we know some stuff about the nodes, and there are people like, there are some of our colleagues like Lubor Schmidt, who spend a lot of time trying to understand the properties of nodes, but it's difficult, okay? And what we often do, actually what we usually do, we use a so-called fixed node approximation, which means that you've done a lot of work in this variation of Monte Carlo. Okay, always you have this trial wave function. Maybe you just didn't stop a bit leap. You put in a lot of determinants, adjust the factor, ultra fancy. Okay, use it. Okay, so what you do is you say, fine, I have my psi. This is a psi trial. I'm sorry, psi trial equal to 0, and you are imposing that your solution has the same nodes, the same 0, as a given trial wave function. So what you have in your B3 leap determinant will determine your nodes, okay? And the way you can think about it, even though we don't quite do that, is that you place down your walker, and around here you have a 0, okay? Of your trial wave function. You hop around happily, inside is greater than 0, and if you're crossing, you kill it. We don't quite do that, okay? But let's say, as a mental representation of the exercise. And in this way, what you're finding the best bosonic solution inside the nodes. Okay? And of course, you know, you are not going to go as if your nodes are good as good, because you're finding the best solution with the same nodes, the same 0 is a constraint as the wave function, your trial wave function, the wave function you have. Okay? And of course, if you're having the nodes are exact, because you're lucky, then your solution is exact. Otherwise, you will approach from above. Okay, we're talking about the ground state here. Okay, and that's very easy to implement in diffusion Monte Carlo, because remember, we are working in importance sampling. So we are not sampling just the psi of RT, which is not sampling but projecting. I'm sorry, we are not just projecting psi of RT, but we are projecting psi of RT times psi trial. Okay, and you can think that you are kind of imposing that this pi, that the product of the trial wave function and the one you are projecting stays positive, so they have the same sign. Okay, effectively that's what you're doing, you know, in doing diffusion Monte Carlo. You're imposing it in the pi is a positive object, and we are happy because we can, you know, we can apply our G, and we can project psi naught times psi trial. But this psi naught will not be the ground state, will be the best ground state with the same 0 as the trial wave function. And now, yes, and now I stop here because otherwise it's too much, and we want to do some exercises. Okay, good. Thank you, thank you. Also, okay. Let me see. No voice. Yes, if you have some question also, you can ask, or you can also discuss it. I can come by and answer questions. Okay, people in the back? It's good. Huh? So for me, it's okay. We can also answer as you guys wish, or you can just raise your hand and I come and we discuss. Is it good? Push through.
Why it's blinking?
Battery? No.
Now,
Okay.
now it's fine.
Okay. Very good. So, can you read the characters at the back, or it's too small? I can make it bigger. Can make it bigger. No.
So here is the theory.
Okay. Okay. So everything is over here. So you should end up on the same page as this one. So we put here everything we are going to do for today and tomorrow. So it's not finished yet. So you will find essentially what we're doing today. So I put here some links for the presentation. So they are not here yet, but the links are ready. So maybe tomorrow the links will be functional. And so this is the hands-on sessions we plan to do for today and tomorrow. So for the preparing the wave functions, we need to have a program to be able to produce a wave function that we give to QMC. So the program we will use is Quantum Package. So it's a program that we are developing in Toulouse and also in Paris. And once we have the wave functions, we can use CHAMP for doing QMC. So CHAMP is Claudia's code for Quantum Monte Carlo. So we have two brief introductions to those codes. And then as you're running on the cluster here, we have some examples for submission scripts so that you can send jobs to the cluster. And then number 4, we will really start to be playing with QMC, because you will first do a calculation with Quantum Package and then transfer the wave function to CHAMP, and then you will apply everything like Claudia talked about this morning. And 5 and 6 will be the subjects that we cover tomorrow. So I will just start with a small introduction to Quantum Package. So okay, so Quantum Package it's a program that is not that was not really intended to be used by end users. It's more an environment to program easily quantum chemistry methods. But it's quite simple to use, so now it's in a state where you can just use it to do some basic calculations. And so here, well, something which is important is that you before using Quantum Package, you need to set up environment variables, and so you need to source in your shell this file where QP root is where Quantum Package is installed. So here on this cluster, I installed it in my home directory. So I need to so I will show you where it is. So excuse me, I will make it smaller because otherwise I don't look the same. So in here, yes. So at this place on the cluster, you have a file with 3 commands inside. The commands are this one. So module load OpenBLAS, you need it because I compiled the Quantum Package with OpenBLAS. So OpenBLAS is a linear algebra library. Then you have the source of the Quantum Package environment variables. And then something related to CHAMP. So every time you log in on the cluster, you should do this command, or you can put it in your .bashrc file. Do you understand what I'm saying, or you're completely lost? Because I mean, if you're not used to these things, I can explain more. But if it's all trivial to you, Okay. So just can you source this thing every time you log in on the cluster? And if you're tired of doing it, put it in your .bashrc, and everything's going to work fine.
Without this, nothing will be working. Okay, so we need to do it.
Exactly.
Yes. Yes. So space mass.
Yeah. And then something you also need to do. Oh. So I put again the website address.
Can you show?
Yeah. Everybody has the website? Good. Okay, so I go back to this. No, wait. So it was, yes. So everybody has a loaded environment? Yes? I see question marks on your face. What's everything?
No. It's, everything is fine.
It's number 3 before yeah. Good. Because now we need to do also something which is a bit more complicated for today and tomorrow. You will need to have installed in your working environment 2 Python packages. So one is TREX.io and one is results file. So you can take these 2 lines in the in section 3, the section about submitting jobs on the cluster. It's written there. So you should install this, and after everything should work fine. Yes.
This. Why should we do this?
So you execute these commands in your terminal on the cluster, right here.
Bar profile to type with
I think yes.
the Python.
Oh no, you could do just the first one. This is the content of the environment file.
We
So
doesn't need the
This is for the script. Yeah.
yeah, so you can do. Yeah.
Once I'm in.
Yes, that's good. So now you pip install TREX.io, pip install results file. Good. Yep. Okay. Yes. Oh no, you are not. Sorry. Okay.
Can you show once again the address of this site? If you still.
Yeah, I'll open it for you. Yeah. You don't have the.
No, non si vede tutti inclusi.
Okay. Everybody's ready? Yes? Okay. So when you work with quantum package, it's not really like the. I'll wait a bit. Yeah. Okay. Yes. So working with content package, you don't have this traditional vision of input file, program, output file. It's more like an interactive way of building iteratively the wave function you want. So all this interaction will be done with the shell. And so you will run different commands and you will modify the state of a database containing all the information of the input that you have. So this database is what we call the EasyFIO database. So EasyFIO is because we use a library which is supposed to be easy to interact with in Fortran. So it's the Easy Fortran Input-Output library. So that's what we use for the database. And so inside we store the orbitals, the input parameters, control parameters of the program, and all these things. So it's all inside. So so what you need to do to start using content package, you need to build an initial database with nuclear coordinates inside, and with the basis set, and eventually pseudo potentials or things like that. So to create this database initially, you need to take an XYZ file, a standard XYZ file. So here I put a water molecule. But you could also use, if you prefer internal coordinates with the matrix, it works also. But you can take this example, put it in an XYZ file, and then you tell quantum package that that you want to create this EasyFIO database. So you have this command that you run in the shell, qp space create EasyFIO, and then you can give some options. So dash basis equals, and then ccpv dz, it's the basis set. And so quantum package has many basis sets available. And so as there is not much documentation, every time you type something, you can use the tab completion in the terminal, and it will propose you different options. So so I will show you an example. I will sit down so that you can see the screen. So where is my? So let me open. Can everybody see? Yes. Okay. So so I log in on the cluster. So here, so I will source my thing. So if you're confused, you type QP and then you it's too low. Okay, wait. I try to adjust so that it fits there. Okay. Okay. So I clear my screen. So if I do QP and then I press tab, so here now I can do QP create EasyFIO. So I can tab complete like this. And once it's done, what can I do next? So I press tab again, and I have different options here. Dash A, dash B, dash C, etc. And so if I want to know what this is, I can always do a dash help. Oh, sorry. Of course, it doesn't work. I changed this yesterday to make it user-friendly, and I shouldn't have done it. So, okay. So this is the behavior you're supposed to have when you to get up. I will fix it, but sorry.
Louder.
Speak louder. Okay. So so if you run qp create EasyFIO with an underscore here and with dash h, you get the help, and it will tell you what you can what options you have. For example, if you have your input geometry in Bohr instead of angstroms, you can use an option for this. You can choose the basis. You can set the total charge of the molecule. You can place some dummy atoms. You can add basis functions to dummy atoms. You can set the multiplicity. So by default, it will be 0, the spin multiplicity. And you can choose the pseudo potential you want to use. And this option is to use Cartesian coordinates for D function, F function, etc. But for the default behavior, we just do QP create EasyFIO. So we use as a basis. So if I press tab again after the -B, it shows me all the bases I can use. And so you can start to type and tab complete the name of the basis. And then you put the H2.xyz, and it's going to create for you this database. So let me just go into a directory where I have tests. So I copy the file here. So I have here the file I have shown you in this directory. So if I run this, where is it? This command. Then it has created this directory. And so this is my EasyFIO database. So if I look what is inside, many directories and many many files in many directories. Too fast. Okay. So now I let you reach this point. Just checking. Good. Okay. I don't put the dollar. No, no. It's because I cut here the segment. That's good. Yes.
I didn't issue this.
Yes.
Okay, I didn't issue this command. Is it
No, this is no. We for the moment we're just here.
Yes, yes. So it's okay.
It's okay.
Just
Yes.
I have the file.
Yep.
But when I add the comment, it's said like that, whatever.
Because here it's even CER.
You improperly
Yes.
copy.
Okay, thank you.
They give you a cake or something. Well, of course, I don't want to be on.
Okay, so let's go back. Yes. So now once you have created, oh sorry, once you have created this this database, there is an environment variable in the shell that is set that tells that you're working with this h2o.easyfio directory. So every QP command that you will run will act into this directory. And so if you want to change, because you're working on two different databases, then you have this QP set file, and then you can change. So that's so we are going to see this tomorrow when we work with the excited states. You will have one directory for the ground state and one for the excited state, and you will switch between one another using the QP set file to specify on which directory you work. So for interactive work like this, we have also the QPSH, which is the Conto package shell. Basically, it's just a bash where we have changed the prompt so that it shows on what easyfio directory you're working on. So if I type QPSH like this, it doesn't change much, but you see here that you have the name of the easyfio you're working on, which appears every time. And the nice thing is that if you change directory, this file is not accessible anymore, and so it becomes red. So as long as it's green, it means that everything is fine and the database is accessible. So now I can show you, for example, I'm going to create so another easyfio database. Sorry. No, but I'm just demonstrating the feature just for you to see what's going to happen. So if I create another one, here you see there is the name here H2O-DFT, which corresponds to this second one. And if I want to swap between one or another, I just do QP set file, and I can go back to the first one, and you see it appears here. Okay, so that's just I just wanted you to show how to change from one to the other one. So we have a few comments with the Quantum package. So now we have created the initial database. So maybe this, yes, this should work. So if you do qp-help, you have the documentation of the QP command, what you can do with it. And basically what we will do, most of the time we'll do QP run a program. So if we want to run a Hartree-Fock calculation, you will do a QP run as SCF, yes. If you want to run a CISD calculation, you QP run CISD. And every time the calculation will run on the database you're acting on. And the state of the database will be the last step that you have done. So if you try just to run a CISD, it's going to take initial guess molecular orbitals that will be bad for doing a CISD. So you will need to do yourself first QP run SCF, you get Hartree-Fock orbitals, and then you do QP run CISD, and you run the CISD with the Hartree-Fock orbitals. And if you change the orbitals and run again CISD, it will do a CISD with other types of orbitals. So that's the way it works. Okay, what else do I have here? Yes, so I can let you now try to run a Hartree-Fock calculation with QP run SCF, like is shown here.
We don't any stop.
It's very small, just to play. So yeah, just to check that it's fine.
Yes.
So here, just to show you here, I use the pipe and T. So T is a Linux command that that allows you both to have the output of the program in the standard output, but also copied into a file. So it's a very convenient command. But you could have redirected with a greater than sign into h2o.scf, but you wouldn't have seen the output in that case. So it worked for everybody? Everybody's here? Yes? Maybe it's because many of you running at the same time. When you run SCF, yes. But if you run something else, it's always the starting point, because Quantum Package is a program to do CI calculations. And so then we have added the possibility to do DFT, but it's more, I mean, if you really want to do DFT calculations, take something else, because it's going to be better with another code. Here it's more range separated DFT combined with CI and stuff like that you can do. So we can do basic DFT, but it will not be the most efficient code. Okay. Okay, so now you have your Hartree-Fock orbitals. So let's just do a simple CI calculation. So I'm afraid you will have for this one to submit to the queue, because otherwise all of you running on the CISD, it will crash. But so if you just run CISD, it will do what you ask for. It will do a CI with all single and double excitations. But usually the default in the codes is to do it only for the valence space. So here you need to specify that you want to do a CISD only in the valence space. So we have a command to set the core orbitals as frozen, so that you will not excite from them. So it's not the default behavior with our code. So you need to do this QP set frozen core. And if you check the output, you should see that orbital 1 is set as a core orbital, but all the other orbitals are considered active. And then you can, if you want, you can do more handmade CI, where you specify you can specify each orbital if it's active or not. And then if you want to do only, I don't know, a CISD in the pi space of a planar molecule, you can, or only in the sigma, or you can really play with your active space by picking the orbitals one by one. They don't need to be contiguous. You just put labels on orbitals, and it will do what you want. Okay, so now let's try to submit. So don't do what's written here. Yep.
Suppose we have I want A1 and also second orbital to be closer. But then can I choose it, or this is automatic?
Yes. So so this QP set frozen core command is just a little script that calls another command where you can re-specify the state of each orbital. And so this other command, so I will show you, I will answer your question. Sorry. So if I do QP set frozen core, sorry, so it's always like this when you do some. Oh yes, I don't have a Hartree-Fock. That's the reason. Sorry. Okay. So it works. So this, when you see this output, it's the same as doing QP set MO class, where you can specify for each orbital to which class it belongs. So you have, so let me show the help. Oh, sorry. So the help, you specify the active MOs, the core MOs, deleted MOs, inactive, virtual, and you give a range. And so the range of orbitals is something like this. It's a string where you can give. So this means from orbital 36 to 53, then from 72 to 107 or whatever. So here we can. So if we do QP set MO class, and I want to set orbitals 1 and 3 as core, I will do this, but then it will crash. It will tell me that I need to specify all the orbitals. And so there is a reason behind this, is that if you specify all the orbitals, you're sure that of what you're doing. But if you don't, it means probably you have forgotten to specify one orbital. So that's why we really explicitly ask the users to specify everything. So here we do, so if I do it like that, yes, it's going to crash. So the problem is that you don't know how many orbitals you have, usually, unless you go into the file, etc. So you can use a -q to ask to the system what do you have inside. So it tells you have 5 up electrons, 5 down electrons, 24 MOs, and this is how it is set right now. So now I see I have 24 orbitals, so I can say from 4 to 24, I choose it as active. And here I see that the core orbitals are 1 and 3, and all the others are active. So, so there was somebody who has used this option to make excited states from core electrons by putting really reversing the core and active orbitals just to make excitations from the core electrons and keep the valence frozen. So you have flexibility to do whatever you want. Okay. So now let's go back to the CISD calculation. So you should go now on the website. So if you go to the top, on the top right, you have a little home button there, and this sends you back to the beginning, and you can go into the job script examples. Okay, and there in section 2, or you can jump from here, you have an example of a job script for quantum package. So, so I put here FCI, but if you want to run CISD, you just do QP run CISD instead of FCI. Here. Okay. So here in this, are you all familiar with these Slurm bash scripts or not? Because I can say a few words about this. You got it? No. So go back to section 3 of the. So you go to home here.
Home.
3 job script.
Yeah.
And then scroll. Yeah, there it is.
Nicola, can you check it? Because I don't really believe that I asked the question. Is there a chart of things that I just not figure out the class in the chart?
Ah.
The partition, because we have a reserve partition.
Ah, we have a result.
Okay, so
tell me. I don't know which one it is.
okay, so just I think we have an email from the Russia who says something about
today.
What they need to do, yes.
Ah.
Talking with Lucia.
Okay, good. There is no question.
It shouldn't be. Let me check there, but it should be the same.
Okay, very good. It's not okay. Well, I was wondering because I saw the number of charts going up, and I was wondering whether there was somebody calling in, but it doesn't seem so.
Okay.
He's trying.
So what are you trying to see the chat? Yeah, for me it's always complicated. No, I don't have anything in chat.
they have create. No. They have put for us the reservation, so I think we need to put also this
okay.
one, just to be sure that everything is fine.
Okay. 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 So give me a second. I update the website with the correct instructions. Ah.
Okay, I might be a little bit ahead, but just like there are these setters, are there also getters if I'm working interactively?
Yes. Yes.
So what are the
You just QP set and then you tab, or QP get.
QP get what?
QP get and space tab.
Ah, okay.
And so you can get. So first you need set file before.
Yeah.
Because you are not set. So now.
Right now I'm in QP.
So set file is not really a set. It's a command in itself because you see.
So it doesn't tab complete. But
Yeah.
okay, I have it.
And if you tab, it should detect which one you can. Yeah. And now if you QP get.
Okay.
Yeah, you can. And so if you
now
say
if I want just my
QP get MO and then you can tab. MO basis tab and then MO coef, you get that. Sorry.
Number, for example.
Yeah, number of MOs.
Nice. Okay.
And so you can really write scripts, bash scripts that interact with it, and you can make loops and whatever. And then you have also a QP edit that reads all this and puts it in a file, and then you can modify. It looks like an input file. Type QP edit, you will see. No, QP edit by itself. So it's going to, and then you can.
And I can just edit it and then select.
You can edit this file, and when you save and quit, it puts it back in the database.
Do that, I would just ask to switch to this.
Yeah. And so, so if you do QP space something, you will have tab completion and all this thing. But if you do QP space edit, in fact, this command just runs the QP_edit program, which is this one.
For this file.
Yes, for this file. So then you so we can speak about this later on. But then if you work with multiple files, then you would prefer QP_edit, name of the file, the name of the directory, and then you can choose.
Okay.
It's
super,
yeah.
Super useful.
So I just updated here on the website. I did on the website the -- account partition, account reserved and partition reserved that you need to put in your Slurm script. Okay. So refresh your browser to take this F5. Oh, excuse me.
This is this script
Yes.
for the new job, right? It's different, like.
So I just added these 2 lines because with this you are going to run on the nodes reserved for the school.
I obtained a message not found, but anyway,
CO2, COH2.
yeah,
Yes.
but I issued the command, this command.
Yeah. Sorry.
And my job, but still,
No, you're right.
still it works. Still it works. File not found, but still it works. Produces.
Yes, but if you look, it should show you an error, right?
No. Real data. It works, but and the message was file not found.
Yeah. Okay. No, the thing is that it's a thing of Slurm because you're an environment and you have QP set file. It has set the file. So you're inside here. We said QP set file COH2 because it was for the COH2 example. This thing. And so there is no COH2. So the QP set file didn't do anything. So it didn't change the file which is set.
Yes.
And so your file set right now is the one where you have run Hartree-Fock. So it has used this one. But it's because Slurm propagates the environment. That's the reason. But so yeah. So this is confusing because this is in another section. So it's in the section where I put the name of a file for what we're going to do later on.
Yes.
So here you the QP set file h2o.easyfio in your Slurm script. Yeah, you can kill it. Yeah. Yeah, I didn't think about doing the CISD with Slurm, so this is for the next step. It's not adapted to right now. You need to tweak it.
So directly, just this is directly like a command, no, right?
No. Okay, I will say a few words. So wait a little bit because things are not working as expected. Because I didn't think that you will send the CISD with a job script. So this script is the script of the next step. And you will have a strange behavior if you run it right now because some files are missing. Okay, so you need to know different things. So instead of COH2 here, you should put your h2o.easyfio. Okay, because otherwise, what will happen is that this command will fail. You will not change directory, so it will. And as you have already done QP set file h2o.easyfio in your shell, the command will run. Okay. But it's an effect of a Slurm that is propagating the environment to the compute nodes. In fact, it should crash here, but it will run by chance. So it's a bit an unexpected behavior. So what you should do for this script, you change here. You put h2o.easyfio here, and there also you put whatever you want as a name of an output file. And I can tell you a few words about these lines, if you're not familiar. So on the cluster you're using, there is a job scheduler called Slurm, and Slurm is just some software to make some reservation of compute nodes. And when you want to make a reservation, you need to specify what resources you want. So this will depend on the kind of code you're running. So here, Quantum Package uses all the possible threads that it can on a compute node. So what you want to do here is do a reservation of one node, so one machine, and use all the possible cores, and you will be running only one Linux process. Okay, so the capital N here is the number of compute nodes. This is number of process. And when you ask for a dash dash exclusive, it means that you will be the only user on the machine. So you will have the whole machine for you, for this script. And the two lines that I have just added here, so those two lines are so that you will fall on machines that have been reserved for the school today. Okay, if you don't put it, you will go in the pool, in the normal pool, and you might wait for 2 hours before having your calculation starting. So if you want the system to be responsive, add the two lines. Okay, and so these Slurm commands, they start with sbatch, and so you have here this sign at the beginning of the line, so that you can also run them interactively. It's treated as comments in the shell. Okay, so I hope it's clearer now.
By default OpenMP or?
Yes, yes.
هي تبقى موجودة في الباك جراوند بتاعت التراك اللي على بتاع ده. ظهري مش قادرة. طب انت عايز ايه من نفس العيله؟ انا قصدي درسناهم.
Yeah.
من
Yeah. Yeah.
It's necessary to put this.
No, you can put whatever you want. You output or it's your.
For non-experienced user, it's better to also specify sbatch plan, how to send it. Oh, I know QSub.
Thank you. Forget. Yes, and also for those of you who are not used to submit jobs on the cluster, once you have built this file, to submit it to the queue, you need to run sbatch and the name of the file. So I will add this thing in the. Yeah.
So, when we say CIST or FC,
Yeah.
we have not yet done the Monte Carlo, like we have.
No. Here we're just trying to prepare a wave function. So a hard report. So here it's even worse because I'm just showing you how to run quantum package, and then so we will go into another section where we run quantum package for champ, then we convert to champ, and then you will run the Monte Carlo after. Yes. Yes. So this is because when you run, so it's just to show the progress, because the thing is that where did this appear? In the error file, right? Where did you get this thing? But can you show me? Okay. Yes. So this is okay. Yes, but you need to do sbatch this file. I'm just I forgot to mention it, but yeah. Non, non, il faut pas faire tout pour faire CISD. Et le truc, c'est que j'ai merdé.
Il faut pas faire.
Non, il faut pas faire tout non, non, non. Ok, on va arrêter là le CISD parce que ça, c'est confusant. Ouais. Ok. Yeah.
Actually, I got the source why it's running from so long time. Because of the default settings is 1 million determinant.
Yes, but the thing is that we should be running CISD.
Yeah,
But it was written SCI, yeah, because I wasn't supposed to. Yeah. Let's move on because it's confusing this. Okay, so please. So let's go back to what we were supposed to do because all this thing was very confusing. So let me clarify a little bit. So the thing is that here you have run the Hartree-Fock in your shell, and I just realized that you are many people running on the front node. So I asked you to use the submission script so that you can use your own node on the cluster. But I didn't realize this yesterday when I prepared for today. So the batch script that you have used was for the next section, okay? Where we run a selected full CI calculation. And here you were, if you just copy paste without doing things properly, you're not doing what is expected. What you were expected to do was to do just a simple CISD calculation. And so if you didn't replace FCI by CISD in the JavaScript, then you're doing something way too expensive. And so I propose that we forget about all this part right now, kill your jobs. But trust me that if you just do QP run CISD, you will do a CISD, you're happy and everything's nice. Okay, so now we can move on now to the, so now you have done a Hartree-Fock calculation, you understood the philosophy of how to use the code. So now we can get into the real work and prepare a wave function for champ. Okay. So we will also. So now we move. So this was just an introduction. So now we're going to skip the introduction to champ. We're going to, because this thing, you can read it later on. I mean, it's repeated in the other part. Okay. So now let's go into the ground state QMC calculation, section 4. So what we are going to do here, we're going to run quantum package, produce a wave function, then export the wave function into a file format which is TREX.io. So it's a file format we develop. which is intended to be like what a JPEG is to images or pictures. We want to have a standard format for storing wave functions. And then CHAMP will read the wave function from this file and produce calculations. So the motivation with TREX.io is that you could use your favorite quantum chemistry program, and then if it can store a TREX.io file, then you can use CHAMP after with it. It's just a way to exchange wave functions. Okay. So here, what we propose to do is to do two calculations. One Hartree-Fock calculation on the water molecule, so similar to what we have done right now, and also to run a single determinant Kohn-Sham calculation with the PBE density functional. And so you have two different sets of molecular orbitals. And so you will have two wave functions with different nodes. And so what we propose here is to make calculations, variational Monte Carlo, Jastrow factor optimization, and diffusion Monte Carlo. And then you will look at the energies you get in diffusion Monte Carlo. And they should be different because you have different nodes. And Claudia has explained that and also Ivan, that the only error of QMC is the fixed node error. So that's why we ask you to do two different calculations. And so two calculations together means two EasyFIO directories where you will have to do basically the same thing in the two directories, except how you generate the orbitals. Okay, so yes.
Good question. Can we somehow quantify the magnitude of difference between those two nodes? How they move between the
by checking the energies, but before running.
But for example, if I'm interested in what part of the phase space have moved from one node to another, basically, what part change the size.
So you can look at the overlap of the orbitals.
Yes, exactly. And basically, and interest only in those that has negative.
It's complicated because you're looking at a 3n dimensional space, and orbitals are 1 dimensional. So you can make orbital rotations and get the same Slater determinant. And so in that case, if you compare the overlap of orbitals 1 by 1, you say they're all different, but at the end the determinant is the same. So it's a complicated question.
And might be that they will have different numbers. So there is not just something like okay.
No, but literally, for example, if you do okay, the discussion for all of them.
Okay. So Claudia this morning talked about this this problem of fluctuations and the variance and all that, and the cusp and the Jastrow, etc. So I just remind you that when we put the Jastrow factor to kill the divergence of the electron-electron potential, we have the same problem for the electron nucleus. Okay, so if you take the potential, it diverges. So there are two solutions for this divergence: whether you use Slater orbitals, which have the proper cusp in your calculation, but we all have codes based on Gaussian orbitals. So another possibility is to remove the divergence from the potential. So if I can, Claudia is not here, so I can hide her homework. So so you have the potential that will diverge, let's say, like this. So what you want that Laplacian psi or psi, you want it to diverge like this, so that the sum will give you something constant. Okay? Is it clear? Because okay, so I recall. If you have 1/2 of Laplacian psi over psi plus v, this you want it to be constant, because if your wave function is an eigenfunction of the Hamiltonian, the energy is an eigenvalue and it's constant. So for any electron positions, you always get the same energy. So it's similar to the conservation of energy in molecular dynamics. Okay, in molecular dynamics, you have your atoms moving around and you want to have the energy always constant. Here is the same for electrons. Whatever their positions, you need to have the energy. And if psi is not an eigenfunction of H, your energy will fluctuate. So if you have Gaussian orbitals, Gaussian MOs, then Laplacian psi over psi doesn't diverge. And so you get, let's say, a Laplacian like this, where the potential is like this. So when you make the sum of the Laplacian that doesn't diverge with the potential, the energy diverges. And when the energy diverges, the problem is that you're trying to average local energies, but sometimes it's very, very negative or very, very positive, and so you have huge fluctuations. So in practice, the computation will have huge error bars because of this feature. So we need in some way to have this energy non-divergent everywhere. So whether you make Laplacian psi over psi diverge in the same way as the potential, so that it's those two terms cancel each other and you can get something which doesn't explode. Or the other possibility, you modify the potential, because if this guy doesn't diverge, you change the potential so that it doesn't diverge. And in that case, you do something like this. This and this will not diverge, it's fine. And so in QMC, the core electrons, which are very close to the nucleus, they have a very high a contribution to the energy. Okay, they are very energetic, and so the fluctuations of this will have a high impact on the fluctuations of the total energy. Okay, so we prefer to remove the core electrons and use pseudo potentials there. Okay, it's just for practical reasons, because if we remove the core electrons and use pseudo potentials, then the total energy will become much smaller. Okay, if you take a copper atom, if I remember, the energy is around minus 1,800 atomic units. But if you use pseudo potential, it can be something like minus 50. Okay, and if you make a 1%, if the fluctuation is 1% of the energy on this or 1% on this, you will see that the fluctuations when the total energy is smaller will be much smaller, and your calculation will converge much faster to the milli-Hartree precision. Okay, so it's a common practice to use pseudo potentials to remove core electrons. So that's what we do, and we don't use the standard pseudo potentials, because standard pseudo potentials they keep this divergence of the potential. Here we use pseudo potentials adapted for QMC that don't diverge. And so we can use Gaussian molecular orbitals, and the energy is smooth and nice. And so Claudia has developed such pseudo potentials when she was young, and when she was a child. And so that's the BFD pseudo potentials. Sorry, I made a typo here. It's Burkatski-Philippi-Doll. Yeah. And so it's the ones we are going to use. So and as you have a pseudo potential here, which is a bit special, you cannot use a basis which is intended for all electron calculations. You need to have the basis adapted to the fact that there is a pseudo potential. So so for these pseudo potentials, there are basis sets that come with them. So we provide here also for you the basis set and pseudo potential for running the yes, hydrogen. So yeah, so if you click on this page here, it will send you to a website where you can select the pseudo potential you want. So it's just an illustration here, but I just want to mention here that the pseudo potential for hydrogen is old, and so you shouldn't use it. Okay. So we give you another one which is better. Okay. so in this page, so we're at section 4 here. So we provide, so this is the same XYZ file as the one you had already. Here you have the pseudo potential parameters for hydrogen and oxygen. You put this in a file. So here I chose pseudo as a name, but you can name it as you want. Okay, and then you have the double zeta basis set going with the pseudo potential. And so I put here the parameters. So before doing anything, you copy paste the pseudo and basis into files. And then here you use the command qp create EasyFIO that we have seen before. But here you specify that, the pseudo potential, you specify here the name of the file containing the pseudo. So I chose pseudo, you can choose something else. And here the basis, you use dash basis, and you put here the name of the file containing the basis that you copy paste from the web. And then the XYZ file containing the water molecule. And from here, it will be basically the same as what you have done in the previous section. The pseudo potential will be stored inside the EasyFIO. And so the system will know that there is a pseudo and will do what's necessary for it. So the next step is to run a Hartree-Fock calculation. And the final step will be to export the wave function into TREX format. So for this, here you just specify the name of the TREX file with this first command, and then you qp run export TREX. It will produce the file for you. That's all you need to know before to produce a Hartree-Fock wave function that you can give to Champ. Mistake? Oh, the link, please. Which link? So potentially is in games format. Let me correct just this typo. So you can click on this thing here to get the website. Yeah, copy link. Where's the chat? I will put also this link here. Okay.
Yes. The potential is literally the same as exactly. Yes, because actually number here is number.
I'm almost done.
Yeah, but my father, yeah, I don't know how to do the chat,
Yeah. I'll stay here if I have questions.
Yeah. But you should do them, give them the homework.
Yes, yes, I had to.
After all, I usually tell them this, like the interaction and the answer. What's going on? But are they also guys get proud?
But it's
Huh?
yeah, I think we have too much.
Really? That we want to do more.
Yeah, just, sorry. I think this-
Is everything okay? Yeah. Well, so on the website, it's the everything about the hydrogen is outdated. Right. But it works, but it's not very good when you want to calculate excitation energies or stuff like that. So we need to update this website. Right. But so I recommend that you use instead the one I give in the. Yeah. Yeah. But all the others are fine.
Sorry, you know, with the original Archibald calculation we did with H2O, did we do that without a pseudo potential?
Yes.
How did you get away without there?
No, it was just a hard report. There is no QMC.
Yes.
So for the divergence, it's not a problem because the integrals are finite, but it's just point-wise there is a divergence. But when you project in the Gaussian basis set, then it doesn't diverge.
Oh, okay. Right.
So this is really specific to QMC, and that's why the pseudo potentials are not well adapted to QMC, because in the normal world you don't care about these problems.
So how does most of the QMC codes they've made their own pseudo potentials, and are you?
So now most of them are using whether the BFD ones that we use here.
Yes.
Or there is a group in the US developing the CCECP, correlation consistent ECPs also, which have the same property of being smooth at the, but they're optimized in a different way.
Okay. Thank you.
So after we do the actual talk now, there will be the DFT part. Okay,
But the FT part is all the same except.
yeah, but no, my question is, when I do here and then when I start doing this,
Yes.
Shouldn't I have changed?
Well, this QP curator changes
it automatically
for you.
change.
Yeah.
Okay. As soon as I create a directory, it changes automatically.
But it's safer to do it. If you are not sure, do it.
Okay. Okay. Okay.
So you have done already the Hartree-Fock. It's okay, great. Can you show me just the energy you get for the H2 HF out? No. This is a binary file. The output .out. So just to be sure that it will be the last line. Yeah. Okay. Yeah. Great. So now you can move on to the DFT.
To create
So just a few words about the next section, even if you are not done with the Hartree-Fock. So the second section is the same idea, but instead of running the SCF, you run the Concham SCF program here. Here you need to set a few keywords because they are not the default ones. So here you can type a QP set DFT keywords exchange functional PBE and also the correlation functional. So you need to set it yourself. So you can do it with in the shell like this. And also the default DFT grid we have is very, very fine. So it takes time to converge, but you can use a coarser grid for what we do today, it's fine. And so you can use this QP set Beacon numerical grid types SGN 1. It's just because the default is not appropriate. And so we meet when we have finished the second
Does it support also hybrid function or only? Okay.
Yeah, I think so. Yes, it does. Because you have a keyword for the Hartree Fock. Yeah. So it's Emmanuel and Julien Toulouse who are responsible for the DFT thing in quantum package. And so they do, so we have a lot of short range functionals and stuff like that. So if you're really into it, yeah, ask them and.
Guys, ladies and gentlemen. So you work, but if some of you want coffee, she's kindly here to operate the machine, okay? So if you want coffee. If you're vegan, it's not good, but it's
Thank you for this. Thank you. No? Okay. C'est pas ça? Ah, tant pis.
Ah si.
Waiting for coffee also. Yeah.
It's okay not too fast.
No, it's fine.
Okay, tell me if I'm fast because
Everything is written on the website, so it's easy to follow.
Can I have a espresso, please? Thank you.
Page my way.
What?
Well, okay, so he was asking so if I want to do a DFT, actually, for to go from TREX.io to Champ, they're called canonical. He generated with the word canonical. So apparently they're saved in
Yes.
TREX.io with canonical. And that's what was a
Yeah.
because it's a rich DFT. But I see that he runs it with canonical.
Yes. That's true. Yeah, we should have a label. We should change the label for.
So you go to put canonical. We need to put it inside. We need to put it inside. We are improving as we go. Okay?
So when you run Hartree Fock, it's RHF? They should have whether the same or one.
DFT or something, but it's what cannot. I mean, he
Yeah.
says that Ravinga told me that that's what is inside this TREX.io, but he doesn't choose a name.
Yes, because it's the name that's in
And
photo package.
apparently, if I go under the setup, I go under the setup of DFT, I never can.
Yeah.
So we don't have that. You know, that's what we can do.
Okay. So, we're not there yet, so I can change. Too fast. Yes. What? Yes. I should have been canonical for RHF. Yeah. Can it make sense not to have the same keyword, because when you look at the file, you want to know if it's artifact or not. And yeah, not yet. Wait. 2-3 minutes. Yeah. Where am I? I'm lost. No? Yeah, no, it's fine, it's fine. Next to the restaurant. When you go to the restaurant on the left. No.
Why we have a different energy for DFT?
Because you mean a different here because this is the Constam energy.
Okay.
And this I'm going to talk about it, but this is the, if you take your orbitals and you apply it to the Hamiltonian, real Hamiltonian, that's what you get. It's a bit above the.
Tu vois, je te dis, c'est beaucoup.
Je me rends pas compte, moi. J'ai oublié de dire S-batch parce que c'est. Thanks for mentioning the S-batch because I wouldn't have thought that it's possible to not know S-batch.
From my experience, a lot of H are familiar with PulseUp, but not with S-batch. Okay. From previous, I think EBS was heavily sampled before other computing become an adequate company. Now it's very costly. More.
Yeah.
and Turkey is not available. I also would like to mention, because I just recall, CI singles and doubles are very slow in quantum physics.
Yes,
It's correct.
it's normal.
But
Yes.
it's really fast. Because there's new algorithm. Ah.
Yes, because the proper way to do CISD is to do an integral-driven algorithm, like you do for CCSD, and you remove terms. But we do it in the basis of determinants, because we use the IPSAS, where we take we have selected all determinants. So basically, our scaling is n to the 8, I think, instead of n to the 6.
Yes, and another observation is that there is a trick to switch quantum package to the CSA basis, right? And in principle, it requires less memory, right? Right? But sometimes it fails with the error, empty error.
Yes.
Also correct.
That is being tested also.
If I just now go for your,
Give me a few days more. After what?
after what? Ah, okay, what in July and 1 week.
2 weeks. 2 weeks from now. 20, because I don't have my passport.
Because memory is the it's the most
Yes.
costly resource now.
Yeah. But if you want to do complete CISD, or don't use quantum package. Quantum package, use it for when you want to do selected CI and little things where you have a lot of control. But if you want to do standard methods, use standard codes.
No, you quantum package.
No, but
After what?
yeah, but if you want to do CCSD, I mean, there are codes which are designed for this. This was designed for doing selected CI, and so it's a bit a hack to do standard methods inside.
What about couple cluster plugin? Is it so slow, or it's?
So we have one which was okay.
And I think in your GitLab,
Yeah.
there is a plugin about plugin.
Ah, yes.
And I think it's the kind of implementation of couple cluster architecture, right?
No. It's CCSD only CCSD, and so it's written in it's not the fastest, because in the fast codes use canonical orbitals and then lots of simplification, and it goes straight. And so we implemented it in a way where you can use any orbitals and it's going to work.
For
Any orbital. So you can you can no orthonormal, but non-canonical.
We have clock operators.
Yeah. So it's slower, but it's more flexible.
It's more flexible. Okay. Like function mode.
Yes, you could do CCSD on top of functional orbitals to work,
I will check.
or localize, or let me know, because I don't know. No, it's very experimental.
Oh, I like it actually. It's very
You use it?
No, I mean I like quantum very much.
Me too.
But it's not quite popular.
Not yet. It's a young code. Yeah.
I think 15 years, right?
No, not that much.
No,
12.
8 years.
8 years. Yes. It was the code of one PhD student.
8 years.
So
8 years is nothing.
yeah, we didn't intend to make it a big code at the beginning. It was just a little code, and then.
But people can do very good science based on those both. Very nice research.
It's one of the best codes in Europe.
And when you told me that you implement selected sizes of eyes, it's very good.
Terrible.
For segmentation.
Yes.
Ah,
Yes.
really?
Yes, that's my part. But I'm correcting that. Yeah, I'm connecting. So there is a trick. You have to put, there is a keyword called buffer length. Yes, put that to a large number. I'll send you an email. I have your email. Yes, that is nice. You can tell me more, give me more.
Another issue is the number of orbits. The number of orbits, right? But I like in quantum package in principle, if you have fixed machine, you can create a lot of orbits. No problem. Just need physical faults. But in Orca, First of all, it requires much more memory. Yeah, but it's not a problem. I have access to large memory. Yes. But then there is a strange problem with the number of factors. I can run calculations without any problem up to 100. And if it's something like 140 or 150, it's always stage errors.
That I need to check. That I need to check. I will check. Because I never did more than 120.
I think about 150.
No, I never did.
Okay, nice.
Because algorithm.
Yes, I know, but I really don't know. Any of them for CSS.
Yes. The theater one is the one that you the least in number.
Yes.
So if you have a large number of operators, you should be able to. Send me an email. I can send an email.
So where are you? You're in Sweden?
Yes.
But where in Sweden?
Lund University.
Huh?
Lund
Lund.
University. It was famous because of your.
Yes, yes. So you're in the same lab?
There is no such one. I mean, there is no method development. Okay. It only applies to the formula. And Mocos. You said a talk.
Yes, yes, yes. I'm not a Molcas user, but
Mocos. Open Mocos is okay.
Yes,
it's open source project now,
Yeah.
but the original Mocos introduced by Bjorn Roos is dying.
Okay.
It's a commercial. It's sad, but we have a nice application. And my professor has a lot of ideas.
Is it very different from Open Mocos?
Mocos? First of all, Mocos is an outdated snapshot of Open Mocos. I think 3 years ago.
okay. So are you a developer of Molcas? No?
I was. Originally, I think I spent.
Valeria Gagliaso, old developer. Is he still developer?
He was CIO. CEO of the time. Yes, I think it's the proper description of his role. Yes, I think 5 years back I implemented kind of global arrays on top of NPI. Because that time global arrays was famous, not famous, but it was our concept. And it was a bit surprising. So we implement kind of J on top of NPI. I think that's only different because you know, I suggest this small whatever like that. But now I always recommend people to use J if you can.
J
global arrays. Always.
Really?
If it works, let's say like that. It performs extremely
okay
for an event if it works.
Okay, could be a good thing to try with quantum package.
And there is another implementation by Fraunhofer Institute in Germany. It's Gatsby.
Yeah, Gatsby is fantastic.
Gatsby is also good.
Yeah.
But I don't know, is it open source?
Yeah. Very easy to install. It's yeah, I tried it at the very beginning where they didn't have the TCP IP interface. It was only for InfiniBand. So I went to a training and very nice. And then, okay, so I want to try it at home, and we had a TCP cluster, so we don't have InfiniBand. Sorry, guys, I will go back to another way. And then they implemented it, and but yeah, that's why I use ZeroMQ, because at that time, Gatsby didn't, GPI didn't support.
Yeah, but now it's,
but now it's too late. I've written my of course.
But you don't use NPI.
A little bit, but also this thing of ZeroMQ in quantum package is more an experiment, because everybody does things in the same way. And in research, it's a bit stupid because there is no new knowledge about using MPI. So I just wanted to try, can we use some grid technology to do quantum chemistry on grids? because I had a book about high performance computing in quantum chemistry, and it's written explicitly computing grids are not adapted to quantum chemistry. You will never do anything on it. So one challenge was to demonstrate that you can do a calculation, a CI calculation distributed on. Yeah. And so with quantum package, I've done an experiment like this with one cluster in the north of France, one in the south, so 700 kilometers, and doing a quantum package calculation distributed on the two clusters, and it worked. The speed up was you didn't see the difference with.
It works in practice. That's
yeah. You have all the tools to do it yourself. Yes.
I mean, is it really needed?
Yes, but if you're suppose you're an industrial, that's what we like, and you want to run an Amazon Web Service or whatever, then you can. Yes. Back to work. Takes off. Okay. No, but you're right. But they should be ready for QMC now. So now it's they should have TREX files for DFT and HashiCorp, and I do it, and if they have complicated questions, you answer. Yeah, I can do that part because I've done it myself. Oui. So no, I'll do it now. So, have you all been able to do the DFT calculation and create TREX file? Yes?
Actually, I have an issue that has appeared, and when I write, there.
Because you probably don't have any orbitals in your, because you have a capital O.
I can have a capital O.
But do you really have a, okay. Do you run a HashiCorp calculation inside?
No, not really.
So you cannot set foreign cores because you don't have orbitals.
Oh, okay, I see. Okay, this is very.
Okay, so now we are ready to go to the QMC. So you have two sets of orbitals, the cone-sham orbitals and the HashiCorp orbitals. So to obtain the cone-sham orbitals, you have run a calculation with a cone-sham Hamiltonian. So you had an energy of minus 17 dot something. And so the thing is that when you will run QMC with these orbitals, you will not get the same energy because you will not use the same Hamiltonian. And a way which is quite convenient is to know what is the energy of the Slater determinant with this set of orbitals using the standard Hamiltonian. So we have a little program in quantum package, print energy. It will just read the wave function inside the FIU, compute the energy, and give it to you. So although we have prepared the orbitals with the cone-sham Hamiltonian, if we run print energy, it will just print the energy with a standard Hamiltonian. And so I put somewhere, yes, here, the two sets of energy. So with HashiCorp, you get 0.95 something, and with DFT, 0.946. So it's a little bit above, but that's correct, because with the HashiCorp, you should get the lowest possible single determinant. So all this makes sense. So, okay, so the important part you can skip because we have done it already. So now we need to create all the input files for CHAMP. So there is a magic script for this here, where you ask here to this converter TREX to CHAMP to produce all the files for CHAMP. So there is a little difference between the HashiCorp and the DFT. Here, the MO type is RHF for HashiCorp, but for DFT, it's canonical. So it's written below, but I just warn you right now. So all these files will be produced where you are. So I recommend that you first create a new directory, go inside. You can copy the TREX file also inside, and you start from something empty, and then you produce all your files locally. Because if you do it at the top, it's going to be complicated. And this is not obliged, but a common practice when using CHAMP is to create a directory named pool and to put the basis set information and the pseudo potential inside the pool. So it's not necessary, but it's recommended. So we put it here. And once your files are well set up like this, you can create an input file for CHAMP. So we call it here vmch2hf.imp, which contains multiple sections with different keywords inside. So here the first module, in the first module you give some general information, the title, or the name of the pool, also some so the prefix used for the files containing the pseudo potentials and the basis. And mode VMC1 MPI1, this is the name of the VMC executable. So it's a bit complicated. It might change in the near future, maybe in 2 days. But this is how you switch from VMC, DMC, you change this thing. And then you can you tell CHAMP to load the molecule from this XYZ file. You tell CHAMP to load these different files for the molecule, the JASO orbitals, determinants, whatever. So then you have, yes, the JASO stuff we'll see it. So module blocking VMC, this is information for how you are going to run your trajectories, numbers of steps. So for it's information for how to compute averages. Want to?
Well, okay, so
it's better if you do it.
okay, so it is related to what we were discussing before, that you know, that these are open. So what we do usually, what you should do, you should introduce it, or you should evolve your system, well, move your walker and bring out your local energy, and then you should play and decide to use position. But let's say, so how should one way people do classical moving art is having your data, so that's all your history, so that's all the stats. So those are all the data, but you know that there are different angles done. But let's say they're correlated, right? So if you keep for sure, let's say they're going to be correlated from one to the next. Right? But then what you do is you block them. For instance, if you block them in groups of two, right? And consider your effective number of points and two. So we have your average. Okay? So you consider these as your data. You do block it. So you take two of them, you consider the average. Okay? So and then you okay, you have the probability of two. But then you can do 4 of them, and 8 of them, and you can increase your blocks. And what you can see, if you're blocking the size of the block versus the estimation of the error bar, you can do something like that, and then you become this. Okay, so this is the error. Okay, so the point is that I have n local edge, 20 times the 20 times. Okay, and then you can say I consider every local edge as an independence. But it's wrong. They're not. You're underestimating. They're correlated. You move the current, set the average. Okay? So you can say, fine, maybe 2 of them are you start here with 1, you go to 2, maybe you start with 2 blocks, and eventually you're able to go up and you can. Okay? And then, of course, if you keep making your data point larger and larger, I mean, if you're having 2 blocks, eventually your distribution will have the error, it's crap, it's bad.
Okay, so the idea is all these points, but you block them and you consider the average inside the block as your data. Okay? But eventually, let's say your size of the block will be such that you will have a good estimation of the other part. Okay? And then eventually your block will become so large, you have 4 data points enough. Okay? So your error will be replaced depending on what you want to do is you would like that to be this is 20. Assume that the plateau around 20. It's okay, 20, it takes 20 steps to go. Okay, so it will mean that I have all the sequence and I consider 20 of them. My data. So the averages are over 20. Okay, so that's every step. But you should do it as a post processing, but because we know a bit our system is done as such. Okay, so for values like system, considering the type of transition matrix we have, a factor of 20 is a step of 20 is useful. Okay, so it means that it's going to consider that the average of 20 is independent of the step. And sometimes it's true, sometimes it's not true, but in average it's good enough. But people understand this concept. That's also okay. So now you're doing a run, which is 20 times 20,000 multiplied steps. Okay? And from by which you mean that from one step to the next, you move all the electrons. Okay? So you start with pushing electrons, you move them one at a time, new step, new local energy, one at a time, new local energy. You're doing it for 20 times 20,000. But then when you compute the error, you are blocking them. You block 20, 20, 20, 20, assuming that after 20, I'm the correct. I'm just giving you this, and then we're going to double check it and fix. Okay? So what you're doing, you're doing one block configuration, which is from out. You can put 2 or 10 information, and the whole length of the round is 20 times 20. But in computing the error, you are considering as independent data points the average for the 20 steps. So those are your data. Okay, to get the error. This is also done in classical. So that's the VNC and equilibration and block equilibration. You can push it, so you throw away, at the moment we're considering one equilibration block, which means we throw away 20 steps. If they are correlated, it is good enough. But if 20 are correlated, you can throw away one block on the head. Okay, you can be stayed with 2 if you want, with 4, it's more than enough. Okay, and now we're going to look at the error transfer value. So there are 20 steps times 20 times. Okay, so Monte Carlo moving all the electrons. But then to compute the error, you can consider them as independent. You're not. And so you consider as independent with averages. Okay, because from here to here, you probably this one. From here to here, you have the correlate. Okay? So that's a so-called blocking techniques. Intrinsically, you should do blocking analysis, chunk reduction. So you cannot know anything. I don't know. So I put it in. Okay? ESP and config new is gonna be used to, so you're moving, right, eventually you want to bend 100 to a 5 to do the diffusion. Okay? So we're gonna put it on range, the one you see. And the equilibration is what you don't include in the energy. Okay? So you don't include the first 20 steps, you don't put it in your energy. Yeah, you can do if you want, you right over time and not over 20,000 in a month.
So here, so what I said, we're just going to run chump to check that we we sample the wave function and check that we get the same energy as what you expect. Okay, so the first one we're going to do is without a just throw factor, just to calculate the energy of the wave function and compare it to what quantum package gave. And so you're supposed to find the same energy. And so running without a just throw factor is equivalent to run with a just throw factor, which is 1 everywhere in space. You multiply by 1. Okay. So so here, when we specify the just throw here, so this just throw start, we will set into this file the parameters such that it's a just throw equal to 1 everywhere. So that's what we propose here. So so that's the file that you can copy paste, and we explain it just below. No, it's explained in the next section. Okay, so yeah, no, it's explained below. So we'll see this later. You will understand later what are all these numbers, but for use it like this for the moment. Yeah. So then we tell you to create the submission script now for CHAMP. So it will be a little bit different. So I go back. So I clicked on this section 3 that sends me back here. And so you had here the example of quantum package that we have seen. And below there are examples for CHAMP. So you should take the variational Monte Carlo run example. So here it's different because CHAMP doesn't use the same technology for using the parallelism of the compute nodes. So quantum package uses OpenMP and CHAMP uses MPI. And so with MPI, you parallelize among Linux processes. And so here you need to specify that you want to use multiple processes. And so on the machine you're using, they all have different numbers of, you have different compute nodes. So some have 12 cores and some have 16. So I put here 12 because you're sure that you can use all the possible machines that are on the cluster. They all have at least 12. So you ask for one node and 12 cores, and so this is to run on the partition. But if you want, I don't know if it's authorized by the system for us, but you could use here a number larger than 12 with different numbers of nodes, and you would parallelize among different machines. So the command to run the VMC, it's a bit complicated. You have many things, MPI run, etc. So to simplify, I just have set an environment variable input here, where you put your input file, and so this shell instructions here tells that output will be the environment variable input that's defined here, and the %sign means remove the suffix .imp, so it will be so this part will be equal to VMC H2O HF, and then you put .out, okay? And so we give the input and output into the command below, and so basically when you change your input, you just have to change this line, and it's going to work easily. Too fast. This is no, but we open the file. Okay, so that's how to run CHAMP. And I think that's all you need to know. Yes. So normally, if you submit your job, you should recover the VMC energy of the Hartree-Fock. Open the output. Huh? Okay. Where is it? So I will just show you what the champ output looks like, so that you know that everything's fine. So at the beginning, you have lots of text recalling what you have in the input. Then if you advance more and more and more, you will have some a big part like this. Yeah. So in this big section here, it corresponds to all the blocks.
Yeah, so the first columns are the boxes.
Okay.
The block packages. So 1, 2, 3, so the first column, and the second column is the coolant package. Okay, so the average doesn't care if you're block on the block. The average cares, so that I call my average is the average of the track. Okay, so what is used is the computation, which is treating a single, let's say, data point and average. Okay, so the first column are the block averages for the 20. The second column is the cumulative average with an error. Okay, and the error bar is treated in a way that it refers to the last digit. So see that the error bar is going down because you're accumulating, and now you know we're having only on the last 4 digits. Okay, and now if anything goes ahead, average not is the average is compared to the average. And you're going to do that. Because you have class functions. You are not keep because we are not involved in the class function. So once in a while, the vocal energy will be huge. And because it will have not close. So let's say that actually, I think we will talk. So what that
Go to one.
59 on the last stage, and that's the case. Here are research. Usually. Okay, so totally, now this is the treatment. So this is really the fluctuation. This is the correlation. Okay, so you can see that it takes having two say multi-color specs when you move all the electrons to be the correlation. We have chosen as the dimension of the block 20 or 10 times long because we can add. Okay? Is it clear that the one was not involved? That's the correlation part. So the correlation part well, I told you that you block over 20 and I have an error. Right? So 1.7 comes from the fact that I can also estimate the error without blocking. And then I have an estimation of the error of blocking 20. And the difference between two is related to the fact that I have a code. So you can do, let's say, you can compute the error with a block. Okay? So you're having the sigma divided by the square root of 20 times 20 times. Okay, so here you're doing as if they are root. Okay, and this is an error 1. Okay, well, you know that in reality, you compute an error with the block. And I just know because I run the course many times, if you're having a balance system, with the type of T that we have. Okay? And the error dot in reality is a sigma, so
Sigma B
by the square root of 20 times 20,000. But now here I have to code. So it's a bit of a, is not really precise, but the precise information. Okay?
But you can imagine, so I can compute the error bar, let's say just by taking the sum over the I block of the block energy squared, 1 over the number of blocks, minus D, blocks squared, okay? And then take the square root and I put a 1 over square root and the minus 1. Okay? My point is that so you're having 25,000 steps. So we block them. Each block is equal. Okay, so very good. So I've tried to take 20,000. I can say I don't block. Okay, but then I'm treating them all as independent. Not good. And in reality, what we know is that you have an effective number, which is less. And we define the core to these things. But now you need to estimate the IRB. And how do we do it? I just for chunk create me some data points, which will be 20,000 data points, because these will be my block averages. Okay? Because I just blocked it. And with the block averages, I can do the error of the blocks. And so I have an estimate for EP. Now I know things from the computer, from the blocking. I know things that define the correlation by the iteration of the two animals. Okay, is it clear? I know. It's very nice. For the others, maybe ask me if it is not clear, then I can discuss it and sit down and see what can say. If this is the time in steps, okay, is a matrix, it has an error. Also, the correlation time is an error. All have an error. So if I repeat it, I'm not going to get 1.74, maybe I get a 1.8 or but it's not your truth. Okay, so it means that after twice that I moved all the electrons, I'm decorrelating. Therefore, if I consider as data point, I move it 20 times, is enough. Okay, so my estimation of the error is reasonable. Okay. No, it's every and the core, the correlation depends on the quantity. The local energy might have a different correlation than a diode, or than I don't know, whatever. So every quantity has its own correlation. This is for the energy. Okay, so but then okay, so my point is because we know that the code we kind of input it 20. Okay, so consider that as the block average. But then you have to say, oh, I want this, I'm okay. If you got in a 4, you say, well, 20 minutes is too small. Let me do 40, 50, and then I'm happy. Okay, so in DNC, we'll have to do something. Good? Huh? There is no time. Okay. I'm not using it. Okay, here is so we're having the definition properties of time. So it's very complicated. The very complicated properties. Because we around grouping so there are standard parameters. Yeah, you might want to do that. You might want to do together and sometimes what you have to do. And the zero will be close. Because yes. Good. And it is that one good actually.
Yes. It's I took a note. No, I think it's with the other wave function with the other hydrogen pseudo potential this time. Yeah. You could check. At the end, if the correlation time is larger than a step, you can put a message saying it's too small.
Yeah. Yeah, great. Hello.
Ask Ravinder.
Yeah, but we should clean the zero. I always want to do it. Also, I have the matrices. I need to just clean it.
It might break some scripts that you have to. You don't have scripts that reads columns and.
No, just we do the stuff of what's called the abstract things. So we complete this B matrix, which contains all the derivatives. And the moment I have it intermediate, but then it's summing up, just Christmas and done a lot. So next Christmas.
Next school.
Huh?
For next
Yeah,
school.
next Christmas. Yes, when I have time.
Okay, I have a question. So in this case, the gestures are stored, set up in the gesture tab.
Yeah.
So if I edit the gestures tab, I can just, but the actual values are stored in where?
Just to start. So you have a just, and that's it. That's the way it is. We are not optimizing. We're optimizing later.
Yeah, but for example, if I have a free body gesture, it should be.
The order of the polynomial. At the moment, we put all order to 0.
Okay.
So we don't even impose a class condition. It's terrible. Okay.
Okay.
So it's really 0. And now the next exercise, but give it a moment, we're going to make you turn it on.
Okay.
It's a simple gesture, but
Okay. Okay. I'm going to wait for.
your gesture is much fancier.
Sorry.
The gesture that Sandro has is much fancier.
Yeah.
Because you really have the whole. It's a simple one.
For the 10, all that.
Yeah. Okay.
So you have the symmetry of the spherical, on the chart, you have the symmetry of the molecule, but it's more your main parameters.
Yeah.
Fancier gesture.
Well, now, some months ago, we just checked out the parameters, and basically we were checking the sensitivity of energy. Just check,
Yeah.
and basically these numbers of parameters basically that doesn't know anything. So basically, so in order to make more efficient the gesture, also basically how to find out the trees basically lower the number of parameters. We will have a lot of that, then optimization can be more complicated.
No.
Yeah. Just using the mathematical reaction.
And that was steps. Something not really okay. So you can have one is estimate, nothing, I will be estimated in the way that, and then you square it in the back. So be like that, and it's an estimate. It's not very precise definition. And should be resolved.
Can I run the diffusion numerical run in the same direction after completing this one? I have completed.
Yes, you can. Yes.
And, but I should read this input.
So
There is no such.
no. I think it's well. You should the information for the DMC. You put it in the VMC H2O input. You put here the information for the DMC.
Yes. So
Okay. So copy this one. Yes.
Copy one, this one.
Or you can run or in the script you specify the VMC. Oh, be careful, you have a
Yeah.
dot at the end.
But I think I changed the list.
Yes.
This
Yes, you put DMC,
DMC.
and you need also to add a block for the containing the time step of the DMC, if I remember. Probably at the end. So I don't know it, because I'm not an expert of chunk. So there is, but so you so.
Okay, I will.
Yeah, I remember we have we have changed something here, but I don't remember if we need to specify a time step somewhere or not. Check on the web page at the bottom, because we.
Okay.
Go down. Claudia, to run the DMC, do you need some extra information, or you just run the DMC with the
No,
same?
you need to have these configs.
Ah, yes.
But didn't we put it? We put it
Yes, I
yesterday.
remember we put something, but it was not the time step. It was you tell it to write configs to
Yeah,
part.
you need to have all the walkers, otherwise doesn't know what to start. Usually, you could do it automatically, but
Okay, so it's not so simple. Just okay. I will
no,
not
you
try.
follow the instruction. Try to follow step by step.
Okay, but
Okay.
because it's immediately after the variation of Monte Carlo, so I.
No, because it's here just on the page of all the
Yeah.
scripts.
Yes.
These are the scripts, but
Yeah. But go back to the previous page and you will see. Yes, yeah.
Okay.
And because here you will have first the just road optimization, etc., and then the DMC comes
Yes,
at the
so
end.
I completed. I think that. Thanks.
the new ones. Yeah, they're very good at selling themselves. Max. So these are the ones who made it. So that's the more. Let me see what you're talking about. So that's the more assisted one, and these are the non-assisted one. And who didn't make it? The one who didn't make it. I don't know who else this is. These others. Yeah, we're gonna have to get back to it.
Focus COE, alors still.
Let us see. They don't really have it yet. They're waiting. It was just sent by G.
I got an error.
I just
Hmm.
don't miss one.
What did you try to do? Can you LS? So you put everything in the pool?
And the policy.
Yeah.
Maybe I can.
Can you? Yes. Can you show me your VMC.int?
I think.
I told you there was something about symmetries and determinants in our message. That symmetry is missing.
Because they're trying to optimize everything. It's still the stupid thing. So they're trying to optimize everything.
You're just trying to run the VMC.int.
May I?
So where are you in the thing? You have run the VMC without just row, it was fine? Or you're on the first VMC run that you're trying to do? First, oh no, first there's something wrong.
The input.
Yes.
Because I mean, I just ran, you just ran it, I just ran it.
Yes, on the
all
so there is a mistake somewhere in the input.
And maybe also something we learn. No,
no, it's okay. It's what you will give.
Do you have the just for the start file?
The error, ignore what's in the error. There's an error. Huh? You ignore the error.
Also.
Ah,
Ignore the errors. Yeah, ignore them. That has to be clean. It's hidden from your side. Okay?
okay.
But then the question, no.
Okay, I didn't check the error because it went fine. So
Yes, the error contains some information about some blocks being absent, but then it's doing things by default.
Okay.
Okay, it's more that, or if you are, you say, oh, I didn't put that, but, took care of it.
Okay.
Okay, but now it should run. Did you run it all? Do you have something down?
I thought that they.
No, of course, it's very reasonable if it's more for the developer or for the more experienced user. Okay, go to the bottom. Good, it's done.
it worked.
953, is it an agreement?
Yes.
Not in the other classes, because I cannot see.
No, you don't. It's 950 here, but you have 953 with an error of 3. So it's yeah.
Well, that's not a you go down by a square root.
Without.
Yes, you go out not by factor 8. I'm sorry, you go out by a factor of 4, so your error goes down to the square root of 4, so 2. Is it clear? So because of the error was 1 with square root of steps, if I go from 20 to 80, I can go 4. So my error will be reduced to 4.
Yes.
The U had
No, here. Yeah, right here.
Yeah, so if you put an extra 4 here, then your error will go down. Okay, well, there is the block, and then pushing you go down.
And so in the next section, you will optimize the just row factor. And so in the next section, you optimize the just row.
In the same direction.
Yes. And it will have the effect also to reduce, you will improve the wave function. So you will make it closer to an eigenstate or with a 0 variance. So the variance is supposed to decrease. And if the variance decreases, the error bars will also decrease. And so you will converge faster to, because in QMC, the better the wave function, the smaller the run. So sometimes when you take a quadruple zeta by this set, your run is faster than with a double zeta because the fluctuations are smaller. Yeah.
And yeah. They don't equal, they differ by a family effect.
Oh, could you be able to explain the locking again?
Yes.
I'm still a bit confused. No.
So the idea behind this is that when you make an average over some, let's say you make the average over 10 elements, okay? So let me write down. Somewhere there.
So you have to focus on potential, but you're not just seeking the.
So I need to write down. Okay, new page. So, when you do, suppose you have a sum over I, AI over N. Okay, so that's how you compute the average. So 1 over n, you can put it outside. Here, the sum over I, you can split it into groups of 10. Okay, so you can say it's sum over j, and here you have a sum over j prime, where you have a I j, and so here you have, so these are the j, the I are the individual ones, and the aij are it's the number inside. So you see, so, and here you would, so this can be completely equivalent. It's just a way to renumber things differently, and it's always 1 over n. So blocking is this. It's because here what you can do here is you can say, okay, here I say that this is now the sample. So let's say you sample over, you take groups of 10. So here you do n divided by 10, and here inside this thing you put 1 over 10. Okay, so it's completely equivalent, and so this means that the average of the averages is the average. It doesn't change.
Yeah.
Clear?
I'm clear. Yeah.
So it means that you can take the data and make groups of data and average over them as you wish. And so when you do the QMC, you're making a trajectory, okay, like this in space. And so you have points like this, and suppose you have a nucleus there. So you will see that the energy of this point will be close to the energy of this one.
Local energy.
Yeah. But when you are here, there are many different paths that could bring you here. Okay, in a point of space, you have an infinite number of trajectories that bring you here. But the thing is that the energy you will have given a given trajectory will depend on the previous point.
Okay.
Because we use this Markov chain where we have this way to move electrons. So the points are not independent from each other because of this property. But if you take very large time steps, okay, and you jump here and jump here, then they start to be more and more independent. But if you take tiny time steps, they will be very correlated. And so if the points are correlated, you will have the illusion that the error bar is smaller than what it is really.
Yeah.
Okay. Because so with very tiny points, you will have some an error that will look like something like that. And so from this point to this point, there is correlation. It would not be, you will not have noise. But if you have something like completely noisy like this, it's completely decorrelated, and that's what you want. Okay. So to remove this artificial correlation that is here, we say, well, the energy, instead of taking the points one by one, I will take the energy of this piece of trajectory, average it, and it will give me a number. Then I take this piece, and it's the same as having large steps, but with more resolution inside. And that's why we do the reblocking, is really to see how the error, to get a good estimate of the error bar. Okay, because if it's too correlated, the error is too small. Then you put them 2 by 2, you have another estimate of the error. 3 by 3, 4 by 4, and then at some point it doesn't depend on the reblocking because you're in the regime where you estimate correctly the error bar. But then if you increase it much more and more, you don't have here enough samples, and then you cannot estimate correctly the error bar because you don't have enough points. So you need to be somewhere in the middle.
Okay. Yeah.
Okay. And so what Claudia said at the end, so the error you estimated as sigma over square root of n, and sigma is the variance of your samples. So if you say my sample is 1 Monte Carlo step, then you have a sigma 1 over total number of steps. But then if you say now my sample is not one individual Monte Carlo step, but it's a piece of trajectory like this, then you have a sigma 10 over square root of n divided by 10. And so if you're in the regime where there is no correlation, these two should match. And the ratio between this and this is the number of steps needed to decorrelate. basically. Because this is too small and this is too large, so if you take this is larger, so if you take this divided by this, it will tell you how much you need to. I think you need a square somewhere because you can. Yeah, I think it's the square of the ratio of this and this that gives you the autocorrelation time, because this is too small to get the correct error bar.
Why is that too small?
Because there is not enough fluctuations.
So is that one? Is it?
One is one step.
I thought that-
One step. And this is 10 steps.
Yeah. Okay.
So the true error, okay. So this should be equal to the true error, but it's not. So it's multiplied by the true error multiplied by alpha, which is less than 1. So this so let's say it's so this alpha, you can put it right here. Okay. And if you put alpha squared inside the square root, which is less than 1, then this alpha squared multiplied by n, it gives you the number of effective blocks, which will be smaller than n. Okay, and this is how you can find how many steps I need to do. Look, it's a bit unclear. So suppose you have 100 steps.
Yeah.
And this alpha is 0.9.
Yeah.
So it tells you, well, the error bar you get an underestimation of the error bar, and you should rescale your n here. If you take, instead of taking 100, if you take 0.9, you get the correct one. So it's equivalent to say that you can change the number of steps by by 1 over 0.9, and this will be the autocorrelation time. Okay.
Yes. Yeah.
Something like that. And that's the 1.74 that you obtain in the output.
Yes. Yeah.
So if you get something like this, you say, well, if I take 2 steps is enough to decorrelate.
Yeah. Yeah. Is it normal to get something as small as just 2 steps? That seems very.
It depends on the time step.
Yeah.
And also here it's normal because you move the electrons one by one, and so so once you have moved all the electrons, you're far away from the initial position, because when you move electrons one by one, you can make large steps, and so you make a large step, a large step, a large step, a large step, and then when all electrons have moved, you're very far from the initial position. So that's okay. But if you were moving all electrons together, you would need more, because you would make smaller time steps, and then they will be more correlated.
Thanks very much.
Okay.
Thank you.
No, I'm trying to explain the autocorrelation. It's a bit tricky.
Yeah. It's hidden from you. The choices about T, they're all default. You could play with that.
ماشي بس احنا ما خلصناش حاجة. لسه شغالين وما بيزهقوش اصلا، بيرغوا كتير قوي والله بجد، وبيرغوا بيحكوا فاهم. ومشكلة النت مش ستيبل، انا شغالة داتا فداتا مقرفة شوية. الداتا فضلت اشتغل من على اللاب، خلصتها بعد ما كان معايا 7000 ميجا، 7000 يعني هي اصلا 8000 كان معايا 7000 كنت بقى شويه. ما يا دوب هتقضي النهارده. طرش هذا لا حتى كويس من 20 ل 23.
Yeah.
Just give it a chance. You got to give us at least 6 months. Is it too optimistic?
Yeah.
Am I optimistic?
Tomorrow you can use TurboRVB No, in 2 days, and they can do solid.
لا اصل هروح كل يوم الجنيه اوفر بصراحه قوي بس في نفس الوقت ان الموبايل مش دايما ما اعرفش عشان احاول
I'm trying to.
Mhm.
So,
Yes.
we need to add this section in what start point.
No, no, this thing in just for the start, and this thing in the input. Because you know, in your input file, you had somewhere a load just for start. And so here you just need to say this file for the derivatives, which is the other file that you created.
انا عايزه اكل كلام
So in the VMC h2hf.in.
تعالى نعمل ساندوتش
Just below this load just for. Here.
Add that module.
Because the first line here, load just for start. So just below you add this. 6 months, Claudia.
Oh, but yeah.
In 6 months, you will be able to run, but you will not be able to give the code to somebody. In 6 months, we have
Business.
Christmas, and before we have 2 deliverables and meetings. And,
Yeah, that will. But I think also we are too serious. Come on, let's just take a break. No?
yeah, for the summer.
Christ.
It's
Well,
in
I'm
the
not going to
stocks.
be there. You don't go as well. Then he's alone, you're going to stop. No?
Ah, you saw it.
Let's relate the question about, because I want to think about the on my machine as well.
On your machine, yes?
Yes, and the point is, the compilation failed because it's 2.5 and the point
Yes.
is,
Clone the dev branch.
okay.
Yes. Because I think I fixed this. Now I call it Python 3 by default.
Yes, yes.
So git checkout dev. And git pull. And then try to redo the configure from scratch. I'm not sure.
How could you make it very clean, like if to
no, it's not needed, but because it detects things well. But you
okay, so
do configure -i all.
okay. Actually, I did it already.
Yes, but the thing is that the dependencies repository, I think, is not well. The dependencies are also different with the def branch. I need to merge, so you probably need to redo lots of stuff.
Actually, I did only I couldn't install.
okay
Okay, because if you do this, you're sure it's going to work. It takes a long time, but at least it works. When do we stop? Yes. Anything?
هي عملتها
Yes. Yeah, I will put it on the GitHub.
ساندوتش طعمها
It is working for me. It's working. So. All good? No problem? Yeah, I think we'll not be able to finish today. We can finish tomorrow.
من كتر ما بتحكي عن الموفينج دور.
Other people on Zoom, they're doing it.
ازاي يعني؟
They're logged in, but they are checking emails and sleeping probably.
هي فسخت ازاي؟ كلمتها؟ ما عرفت منين؟ كنت ما ادخل اخد لفه عندها.
مش مدفع في الدفع، هي بدأت تظهر لي بوست بتاعتها. فبعدين نزلوا بوست مثلا هو اعتذرها هي تزعل عن ايه ومش عارف ايه.
لا هو اصلا ما بيزعلش محمد.
بس مش على انفعالها ولا على الكلام واحده ماشيه اللي هو دس على كتفي ومش عارف ايه. فبعدين
انت بعتي لها؟
لا بعدين بص
It's normal. Me too. Claudia,
بس هي
that's a question for you.
بس انا عارفه انهم عاملين كده من زمان.
No.
في حاجه انت وقتها.
Ah, can I take the chair? Because show me. So
انا على فكره حاسه ان انا ما شبعتش قوي.
oui. On peut parler français? Alors, le Artrifoc, ça a fonctionné le Artrifoc ou pas?
Je le fais.
Ouais.
Enfin, en différents.
Tu peux parler anglais si tu es plus à l'aise.
Okay.
We can speak.
If you speak in French, I can understand, but it is easy to find the words in English. I run the Artrifoc in a different direction.
Okay. Okay.
And now I am in QMC. Champ.
Okay. So all the all the Artrifoc part was okay. I mean the H2HF, this one,
Yeah.
with a slow potential for champ and everything, it was okay.
Yeah, this is with the champ. This is the champ.
Okay, okay. Let me just check. But I think I looked on your over your shoulder, and I think it was okay. Yeah. No, I'm not sure. I think this is the DFT one. Not sure. Not sure. Because you have the A shape and the DFT here, and I think you made a mistake because with the DFTMOs you get 0.946. Okay, and with Artrifoc you get 0.950. And here in the VMC.out you get 0.943 with an error bar of 4. So it seems to be the DFTMOs. So I think that you were confused somewhere, and you mixed up the directories, and that's why you. I think you made probably a confusion at the beginning, and then it gets all messed. But it's good. When you do mistakes, you learn. If you don't do any mistake, you.
Yeah, I'm trying to understand.
Yeah.
Okay, this is the Artrifoc.
No, that's the DFT.
DFT with NOS. Yeah.
Can you check because maybe it's a problem of name. Maybe you swapped the names. With VI. Yeah.
الفكرة ان انا ماشيه كده عادي. انا عارفه ان هو بيعمل براكتس.
This is the open society. Linux was not Ubuntu.
لكن انت عارفه لما بيدينا فرصه نجرب ونرد عليهم كلهم بيكتبوا.
I only use it for Ubuntu. Okay.
Okay, that's the DFT calculation.
Yeah.
0.248. Okay.
Also the energy.
Okay, so that's the energy, the Koncham energy.
Okay.
So it's slower than Hartree Fock because you have electron correlation.
Okay.
But then you produce Koncham orbitals, and then if you calculate the energy of the waveform, so if you calculate the energy not with the Koncham Hamiltonian but with the standard Hamiltonian, you should get something which is higher than Hartree Fock, because Hartree Fock is the optimal one. So you can do this thing and QP run print energy. Sorry. And just to check, yes, you get 9.8, and that's the energy we have here.
Yeah.
So okay, that's it's all good. So this is really the DFT calculation. That's fine.
I did also
For Hartree Fock.
Yeah.
Okay. So Hartree Fock was task 2, I guess. Yes. So let's check just the QP. This thing and energy, and if we get 950, it's okay. Okay, so to here it's perfect. So now you in this thing you okay, so, yes. So to do the champ, so you copy these files in the task 4. Yes.
And this is for these.
Okay.
For Hartree Fock check at least for the
Yes, because I think you probably forgot to switch directories. Have you overwritten something or? Okay. So I propose that we redo a new one. New. We're going to HFU. So we copy this. What was it? No. Task 2, task 3. 2. H2. HFU here. Okay, so now we can copy this thing seems to be okay. So okay, good. So we needed to add the just for create the input. So you did exactly the same as what I'm doing.
غلط دخلت رقم غلط قلبت دماغي.
Okay, and then adjust for factor. Start. Okay.
Then you will use the script here.
Wait, I forgot to change something. This should be canonical here. I wrote it there, but I didn't change it here. No way. No, I didn't change it. Okay. So the submission script. So I think you have it in the H2OHF.
OX1.
Okay. H2O here. So no, I forgot. No, it's okay. So S batch.
طب ما خليها لبكره ما تخافوا
Ça marche.
Voilà, ça, je sais plus, il va
48, 940.
إذا ما فهمت لك خلاص كنت راجع أقول
Parce que là, so we have 954 with an error bar of 5. So the 950 that we have here is compatible with the error bar, and so it's going to. It's possible it was correct, but maybe it was not long enough. Maybe we need to run longer. Because you reduce the number of cores.
Yeah.
So when you reduce the number of cores, it's like if you're 12 with those. Okay. Okay. No, so it's possible that it's a problem that it's not well converged because the error bar is too large. Let's try to do 12 here. Ah, yes, you're right. What was the problem?
No, my hand sometimes are USGB, but I cannot see them.
Okay. No, we don't get the heart-to-puck energy. It's strange. But she reduced the number of MPI processes from 12 to 6. But yes, but I think the
huge error. You have an error of 5.
yes, but then
I cannot quite read because I have the brown glasses.
But the thing is that
okay. It's okay.
Yes, but because now we're running on 12 just to check if.
Okay, show me the results on 6.
Lost. Oh, I'm overwriting. But the result on 6 was 953 with an error bar of 3.4. So it's with 2 sigma, it's okay. Yes, but yeah, but the others they had something which was closer. But we have the same random numbers. No? Yeah, 953 with an error of 3.8.
Yeah, fine, but it's all compatible. It's huge, the error. You got to make more blocks.
Did you reduce the number of blocks? No, you took.
Okay, so let me see. So I never remember the.
But
I think at 30% of the time you can be assigned 1 standard deviation.
Yes.
And then
95.
You can be assigned 2 standard deviation, which is still a lot. This 120 is nothing.
Yes.
And then okay, being outside 3 becomes very unlikely. I mean, you are within 1 standard deviation. Or 2.
Okay. What we if we increase the number of MPI ranks,
they should be the same.
Yeah, we will get the same. We will multiply by.
They're just treated as in all the blocks independent data. So
Okay.
you can do it sequentially or okay.
You're not shortening the number of blocks when you. Yes, I remember the. Okay. Okay. So let's multiply by 2 here. So we take 2 nodes. Just to.
Space to get ranked for more.
So yes, to run quickly. Yeah. And also in the input, I multiply by 2, so that we really decrease the error bar.
This command will run is the same as control R.
Yeah.
Okay, so you see here we run 2 nodes. I just want to see if we can log on the nodes and check if everything is running. No, we cannot log in.
It won't jump. Now it's running.
Because maybe it was all good what you had. It was just bad luck.
She had an error.
I had an error.
In DFT, he is trying, repeating the one with hard reflux now.
Yes, just to be sure, step by step. Okay. So while it's running, we can go back to the DFT. Another terminal? Okay. I'll let you do it.
Yes. This is what is yes.
No. Like, it's not able to find the geometry. Like, yeah. I can't find it.
The canonical, you did it? Okay, that's it. Yeah.
Even if you were
understand it. Yes.
This is at least your this. So
The mistake that we did was
You copy pasted the block. Yeah, I forgot to change it. Yeah.
Python
Ah.
one.
yeah, it's in
Ox.
script.
Ox or Ox? Perfect. Yes, that's the mistake. This should be canonical because RHF means you want the Hartree-Fock orbitals, and you don't have them, so this should work. So we can execute it.
One. You want to execute?
Yeah. No, just want to execute this too.
Okay.
Okay. Yes, I didn't source the environment. Oh.
What happened? Did you change it canonical? Okay, well, let's check and then we'll decide. Wait, I will ask you.
Okay. So I think now you can children. Let me check just the Hartree-Fock again.
Wait.
It's on the other.
Yeah.
Oh. H2O, HF, new. Yeah. 9469. Yeah, it's hard to say. They're so close, but it makes sense. At least it's not nonsense. Okay. So now you can try to run the GFT because you made the VMC input already.
Yes.
We didn't move into the pool. NV, does it work? No. So NV, so it's TCP star, what else? BFD star and the champ and BF info also. Bye. Okay, so Ox1 was the DFT. You can take 12. Yeah. Okay. In the meantime, I correct my, I put the canonical on the.
I think we I don't know. Like
Yeah, very good. No, no. Oh. It works. Ah, such as DFT here. VJ?
Maybe this check
The scripts? What? The Slurm scripts? It's in section 3. Go back to the home and section 3. On the top right, your home. Ah, no. No.
And the determinant part is only fixed. If you don't know, you let's say there will be fake flow or there is some way how to calculate that. Just some calculation. Just based on the project.
So this one runs. It works here. So so I really don't understand what's going on. Ah. Didn't see H2O DFT.in. Ah, it's HF. It's in the input file. It's the name of the input file that had an HF inside. So what in the aux1, this file didn't exist. That's why it crashed at the beginning. So I think if you submit this one, it should work.
Now I should I remove these?
Yeah. No, you can remove them. It's yeah. And also the H2O HF determinant orbital XIO, you can remove them. Everything which contains HF, you can throw it away. Yes. Next one. Next one. Next one. This one. Also the TREX file. Yes, this one. You can release. Yeah. Yeah. Also the output, because you might. Yeah. Yeah. So it's much. It's about box one. Yes. And so you can say minus f. But out. Ah. Works. It was just the input file name. That was wrong.
Change the file. But you didn't change it.
So I think you, yeah, you changed it in the file system, but you didn't change it in the source script. You forgot to change the input file name in one file.
But do you think you can also use without canonical? What I told you about changing the file? Just let me compare my account.
Yeah. Yes, yes. Because this thing about canonical, I'm not sure, because it's so I'm not an expert in CHAMP, so I don't know. Yes, but I'm afraid that the error bar will be too large. So oh yes, here the error bar is small. It's 1 milliHR3. So here you really have a 944 with an error bar of 1. And so this is compatible with no, it makes sense. This is the energy of the I mean the R3 fork energy cannot be in this, because it's beyond the I mean, you have an error bar like this, the DFT energy is somewhere here and the R3 fork is here, so your error bar is really small, so it's perfect. Merci. So when the name of the input is wrong, so suppose you do vmc.int,
yeah,
and you do vmc move one or toto.int, it's going to crash with because the name of the input file is inexistent. You see when you make a typo in the input file, and so we didn't understand because yeah, because in the source script he forgot to change, and
yeah, understand. Then it becomes automatic, and then you check anymore.
yeah, and then you question? No.
I'm a bit low, I'm a bit tired. So I'm not sure if it's getting the FTM.
FT 945.
This is my class.
Yes?
Yeah.
No, but I changed.
Yeah, no, we have another file, but you are going to
Okay. You have an output. Okay, so it's not the same. Yes. Okay, I think this is the canonical problem. Yes, because this is yes. It is. Okay, because let's check what's inside the TREX file. No. Yes, because in the TREX file, MO type is canonical. So it didn't find
Yeah.
Yes, because this thing is because you need to build a stator determinant with some orbitals, and so you need to inform all this complicated line tells Champ to take orbitals somewhere and to build a determinant with a set of orbitals which is RHF or canonical. So here he didn't find the orbitals, so he didn't build the determinant group. Yes.
And here it's like copy of the wave function direction is this file, right? With the
Yeah.
And then here also we should copy the last Castro.
So you redo everything the same as well. No, sorry. No, you can copy everything. You copy the directory.
The directory.
Yeah. It allows you to redo the setup, but you can redo the. It's the same. It's the same.
And then change the
Yes. So here you just change. You reduce the number of you make the number of blocks smaller, so that you just do a little VMC, and at the end of each block is going to write the coordinates into a file, and so this will constitute a set of electron positions, which will be your workers for DMC.
I just repeat the previous small plots. Why should I use just this run start DMC?
Sorry, I don't get so.
What is the difference between this short preparatory run and
What we did before?
Around
Yeah. So the difference is this. So here you have nconf new 100.
Yes.
And you had 0. DMC nconf new.
Yes.
So go up. You had 0. And here we ask only 200 blocks.
So this is
yeah, so you can change, but if you want in the same directory, you can change the input like this, and then you can run the DMC. It will work.
بهزر.
So, how are we doing?
تفضل. عليكم السلام.
How many people only are for the presentation?
شوف حاجة في عبد الله؟ مش بعرف من غير كده.
personaggio.
Vai, ma c'è un servizio.
Ok, so we mix.
So if you're tired, what you can do, you can make a little break and then you can continue in your room for the whole night. No, we can continue tomorrow.
Yeah, you're gonna talk to me. It's good to be medicated. Can you stay?
Medic?
Here. Eva, you're the boss. Can you stay here? Very good. I go to cool. Yeah, but maybe here they can talk to each other and they can talk to each other. So if you guys want to stay and give an allowance, they can stay.